In the past few years, artificial intelligence has moved incredibly fast. We now have models that can write, translate, see, hear, and even reason across multiple modalities. But one question remains for most developers and learners. Where do all these models live, and how do we actually use them? That's where Hugging Face comes in. Hugging Face is more than a library. It's the open platform that connects AI research, real models, datasets, and applications into one ecosystem. If GitHub is where software lives, Hugging Face is where modern machine learning lives. In this course, we'll take a practical end-to-end journey through the Hugging Face ecosystem. We'll start with the Transformers library, where you will learn how to use state-of-the-art language, vision, and multimodal models, and how to use them for tasks like text generation, classification, translation, and question answering. Then we'll move into Diffusers, the library behind modern image, video, and generative AI systems like Stable Diffusion. And we'll learn how these diffusion models work and how to use them to generate and control high-quality outputs. Next, we'll dive into Gradio, the tool that lets you convert or turn any machine learning model into an interactive web application in minutes without any front-end experience. We'll also deal with audio and video models, and including tasks like speech recognition, audio generation, and many more. By the end of this tutorial, you won't just understand Hugging Face, but you'll know how to navigate it, use it, build with it, and how to deploy real AI applications into Hugging Face. Whether you are a beginner, developer, or researcher, this course will provide you solid and future-proof foundation into open source AI. Let's get started. What is Hugging Face? Hugging Face is an open source, first artificial intelligence platform that provides the infrastructure, tools, and collaborative ecosystem required to build, share, fine-tune, evaluate, and deploy machine learning models. It places particular emphasis on transformer-based architectures, generative AI, and reproducible research. In practice, Hugging Face functions as the central distribution and collaboration hub for modern machine learning, often described as the GitHub of machine learning. Founding and evolution, it was founded in 2016. The founders are Clement DeLong, Julian Chomond, and Thomas Wolfe. Hugging Face originated as a conversational AI startup. Its strategic pivot occurred with the open source release of the Transformers library in 2018 and 2017, which rapidly became the standard interface for transformer-based models, BERT, Roberta, Albert, Electra, and so many models like GPT and Qwen, DeepSeek, Llama in both academia and industry. This release catalyzed Hugging Face transformation into the leading open platform for AI research, development, and deployment. Core users. You can see here the most core users here is a model hub, so host and version, pre-trained and fine-tuned models, datasets hub, libraries and tooling. Hugging Face offers us multiple libraries like Transformers, Diffusers, Accelerate, and so much libraries like Gradio, Spaces and Gradio, inference and deployment, research and education, reproduce papers, benchmark models, and teach modern AI workflows. The importance and impact of Hugging Face: democratization of AI lowers barriers to entry through free, open, and standardized tooling. Open science leadership encourages transparency via model cards, dataset cards, and reproducible benchmarks. Industry adoption, trusted by startups and enterprises for rapid prototyping and production deployment. Research acceleration, ecosystem standardization establishes common APIs and workflows across frameworks and modalities. Community scale hosts millions and millions of models and datasets maintained by a global contributor base. And here we have the images of the authors of the Hugging Face platform. Hugging Face philosophy and ecosystem vision. Why Hugging Face exists? Hugging Face exists to make state-of-the-art artificial intelligence accessible, reusable, and collaborative. Its core mission is to remove friction between AI research and real-world application by providing a shared platform where models, datasets, and applications can be openly published, discovered, improved, and deployed. Rather than treating AI artifacts as closed products, Hugging Face treats them as living research objects that evolve through collective contribution. Here you can see democratization of AI and open science, open source libraries. So their libraries are all open sourced that lower entry barriers for learners, researchers, public model and dataset sharing that enables reproducibility and transparent comparison results. So there are so many datasets available on Hugging Face as well as models for free, model cards and dataset cards that document training data, intended use, limitations and ethical considerations, open access to research artifacts that accelerates innovation across regions, institutions, and economic contexts. Community-driven research versus closed AI platform. Hugging Face represents a community-first paradigm for AI development. Researchers publish pre-trained models together with code and weights. So there are so many pre-trained models like text-to-image models, image to text, video to video, text to video, and also we have image to video. Practitioners fine-tune, evaluate, and adapt existing models to new domains. Improvements propagate rapidly across the ecosystem through reuse and remixing. Hugging Face as GitHub for machine learning. Hugging Face fulfills the same role for machine learning that GitHub fulfills for software development. Repositories for models, datasets, and machine learning applications, versioning, updates, and collaborative workflows, discoverability through search, tags, leaderboards, and benchmarks, standardized documentation, licensing, and attribution. This analogy reflects Hugging Face's position as the default distribution, collaboration, and archival layer for modern AI artifacts. So here you can see the relationship with academia, startups, and enterprises. Hugging Face operates as a neutral, connective layer across the AI ecosystem. Academia enables reproducibility of papers, and there are so many papers hosted on Hugging Face, open benchmarks, and rapid dissemination of research outputs. Startups supports rapid prototyping, fine-tuning, and deployment with minimal infrastructure overhead. Enterprises provides secure and scalable solutions for private models, managed in inference endpoints, and production workflows. And then we have the Hugging Face platform architecture. So how the Hugging Face Hub works internally. At its core, the Hugging Face Hub is a Git-based, content-addressed platform designed to host and serve three first-class AI artifacts: models, datasets, and spaces. And if you visit the homepage of the Hugging Face platform, you will see these three tabs at the top navigation bar: models, pre-trained weights, configurations, tokenizers, and inference metadata. Datasets, structured data with schemas, splits, streaming support, spaces, executable applications, Gradio or Streamlit built on top of models. Each artifact is stored as a repository. So keep in mind, each artifact, whether it was a model or dataset, it will be stored as a repository with standardized file layouts and metadata, enabling discoverability, reproducibility, and seamless integration with the Hugging Face libraries. And then you can see here we have the versioning aspect, commits, branches, and model cards. The hub adopts familiar Git semantics for machine learning assets. Commits and branches track changes to model weights, configurations, and supporting code. Tags and revisions pin exact versions of models or datasets to ensure reproducibility. Model cards and dataset cards, structured documentation describing intended use, limitations, training data, and evaluation results, biases, licensing, and ethical considerations. This design ensures that models are not merely downloadable files, but auditable well-documented scientific and engineering artifacts. Model lifecycle upload. So first we start by uploading that model, then we have a version, then we have inference layout, and then we have deployment. Hugging Face supports the full end-to-end lifecycle of machine learning models. First, we start by upload. So push models or datasets via CLI. So it's called CLI, command line interface, GET or API. Versioning, iterate through commits and branches as models evolve. Inference, run models through widgets, pipelines, interfaces, or hosted inference APIs. Deployment, serve models using spaces, managed inference endpoints, or self-hosted runtimes. This unified workflow removes the traditional gap between research, experimentation, and production deployment. And you can see here we have some public, private, and gated repositories. So keep in mind, this is a really important note. We have public repositories, private repositories or private models, and also we have gated models or gated datasets. Hugging Face supports multiple access control. We have some control access modes to balance openness with responsibility. Public repositories, fully open and accessible to everyone. Private repositories, restricted access for individuals and or organizations. Gated repositories, publicly visible metadata, but access to files requires approval or license acceptance. So there are some public repositories which are fully open, fully accessible, and to everyone. We have private repositories. These repositories are restricted to some individual people or some organizations. Gated repositories, publicly visible metadata, but you need to if you need to access it, you have to provide some approval or license acceptance. This flexibility enables ethical data sharing, controlled model release, and enterprise-grade workflows. Then here we have the authentication, tokens, permissions, and organizations. Security and collaboration are managed through a robust access control system. User tokens, authenticate API, CLI, and programmatic access. Fine-grained permissions, assign, read, write, or admin roles. Organizations enable shared ownership of models, datasets, and spaces. Team collaboration, role-based access for scalable multi-user workflows. These mechanisms allow Hugging Face to function as a secure collaboration platform from individual researchers to large enterprises. Hugging Face Hub. The Hugging Face Hub is a central registry and distribution layer of the ecosystem. It hosts models, datasets, and applications as versioned, documented, and reproducible repositories that integrate directly with the Hugging Face libraries and external machine learning workflows. Model Hub, model repository structure. Each model is sold as a Git-backed repository containing standardized components. Model weights, so you need to upload a file that contains model weights, configuration files, tokenizers for or feature extractors. So if you are uploading an LLM, large language model, you need a tokenizer or a type of tokenizer, metadata for inference and evaluation. This structure allows models to be loaded programmatically with a single identifier and reproduced reliable across environments. Model cards, purpose, limitations, ethical notes. Model cards are a core design principle of the hub. They provide structured documentation covering intended use cases and target domains, training data sources and assumptions, known limitations and failure modes, bias, fairness and ethical considerations, licensing and citation information. Model cards ensure transparency, accountability, and responsible reuse. So first we have the model weights. You can see here typical model repositories include weights in a .bin, .pt, so short for PyTorch, or .safe tensors. This is also a package inside Python called safe tensors. You will see it a lot common in Hugging Face. Configurations, here we have config.json defining architecture and hyperparameters. So the configuration file, which has the extension .json JavaScript object notation, defines architecture and the hyperparameters, tokenizes vocabulary files and tokenization rules, safe tenses, secure, memory efficient weight format, preventing arbitrary code execution. These components enable safe and efficient loading across frameworks and deployment targets. Inference widgets. The hub provides also built-in inference widgets that allow users to run models directly in the browser, test inputs and outputs interactively, validate model behavior without writing code. So the inference widgets, like for example Gradio, it provides the ability to run models directly in the browser without the need to download any model, test inputs and outputs interactively on the web, validate model behavior without writing code. Widgets act as instant demos and lightweight validation tools. Supported frameworks. So the supported frameworks and libraries are PyTorch, TensorFlow, JAX, and Flax. The Model Hub natively supports PyTorch, TensorFlow, JAX, Flax. This framework agnostic design allows researchers and engineers to work in their preferred ecosystem. So whether you are excellent at PyTorch or at TensorFlow, no worries, you can upload your PyTorch model or your TensorFlow model onto Hugging Face Hub. This framework agnostic design allows researchers and engineers to work in their preferred ecosystem. Then let's dive into Dataset Hub. Dataset repository structure. Datasets are stored as repositories containing raw or processed data files, loading scripts or dataset builders, metadata, and documentation. They integrate seamlessly with the datasets library. So there's a library called datasets, and then we have the datasets card. You can see dataset card document, data sources and collection methodology, dataset structure and features, licensing and usage constraints, biases, ethical concerns, and limitations. Then let's dive into splits, features, and schemas. Datasets are defined with standard splits, training dataset, validation dataset, test dataset, explicit feature types and schemas, and also automatic validation and consistency checks. And also we have streaming datasets. Hugging Face supports dataset streaming, allowing loading data without full local downloads. So you are also able to load a data without the full local downloads, training on massive datasets efficiently, and reduce storage and memory requirements. And also Hugging Face supports large-scale dataset hosting, terabyte-scale datasets, high throughput access, global availability. This makes it suitable for both research benchmarks and industrial scale corpora. Then also we have the Spaces Hub. What Spaces are and why they matter. Spaces are hosted machine learning applications that turn models into interactive demos or products. They provide a fast path from model to user-facing experience. So you are moving from a model in a Google Colab into a model that faces the user, a user-facing experience. Gradio versus Streamlit spaces. We have two types of spaces. We have Gradio and we have Streamlit. Gradio spaces ideal for ML-centric, component-based interfaces and demos. Streamlit spaces better suited for data, dashboards, and analytical applications. Both options enable rapid deployment with minimal infrastructure setup. Hardware options. We have GPU, we have CPU, central processing unit, GPU, graphical processing unit, 0 GPU. Spaces can run on CPU, lightweight demos and inference. So if you have a lightweight model, for example, a model that is used to classify rows, a structured data, or for example, a model that is using a regression algorithm, you can run it on a CPU. And also we have GPU, heavy models and real-time generation, where you have computer vision models, NLP models, LLM models, reinforcement learning models. They all are heavy models that need real-time generation. Zero GPU, shared on-demand GPU resources for cost efficiency. So the hub summary, the Hugging Face Hub unifies models, datasets, and applications under a single versioned and documented platform, making it the global backbone for sharing, testing, and deploying modern AI systems. Transformers Library. One of the most important libraries inside Hugging Face is the Transformers Library. Architecture of the Transformers Library. The Transformers Library is the core execution engine of the Hugging Face ecosystem. It provides a unified abstraction layer over thousands of transformer-based architectures, while remaining frame agnostic. Internally, it standardizes model configuration and weights, tokenization and feature extraction, task-specific heads on top of shared backbones, consistent APIs for training, evaluation, and inference. And keep in mind, Transformers Library is framework agnostic. This design allows a single model to be reused across multiple tasks and domains with minimal modification. Then we have some classes like the auto model and auto tokenizer philosophy. At the heart of Transformers is the auto abstraction. Auto tokenizer, auto model. Auto model selects the correct model class based on the configuration. Auto tokenizer loads the matching tokenizer automatically. This removes architecture-specific by boilerplate and ensures correct pairing between models and pre-processing logic, enabling rapid experimentation with minimal code changes. So we have pairing between models via auto model and pre-processing via auto tokenizer, where you pre-process some text data. Pipelines abstraction. Pipelines provide a high-level, task-oriented interface that bundles pre-processing, model inference, post-processing. So if you use a pipeline by going from Transformers import pipeline, this pipeline function provides a high-level, task-oriented interface that bundles pre-processing. You don't need to execute any pre-processing code anymore, model inference, and post-processing. They allow users to perform complex tasks such as translation or summarization in a single line of code, making Transformers accessible to beginners while remaining powerful for rapid prototyping. Training versus inference APIs. Transformers clearly separates concerns between inference APIs, training APIs. Inference APIs optimize for speed, simplicity, and deployment. Training APIs designed for flexibility, customization, and large-scale fine-tuning. This separation ensures that production inference remains lightweight while training workflows remain expressive and extensible. Trainer API versus custom training loops. The library supports two complementary training paradigms. Trainer API, a high-level training loop handling logging the values, for example, loss value or the accuracy value. It logs it into some form of list, evaluation, checkpointing, and distributed training. Custom training loops, full control using native PyTorch, TensorFlow, or JAX for research and advanced optimization. This dual approach balances ease of use with research-level flexibility. Tokenizers integration. Transformers integrates tightly with the tokenizers library. Fast, Rust-backed tokenization, and you know Rust is the most fastest language in the world. Support for byte per encoding, word piece, unigram, and sentence piece. Consistent pre-processing across training and inference. Tokenization is treated as a first-class, reproducible component of every model. Supported tasks. The Transformers library supports a wide range of AI tasks, including text generation, autoregressive and instruction following models, classification, for example, sentiment analysis, topic classification, intent detection, question answering, QA, extractive and generative AI, QA, named entity recognition, NER, structured information extraction, translation, neural machine translation across languages, summarization, abstractive and extractive summarization, multimodal vision, language, audio, text, and video-based models. And here we have the paper of BERT, bidirectional encoder representations from Transformer, which uses the encoder-only transformer architecture by Jacob Devlin and et al. BERT fundamentally changed language modeling by proving that deep bidirectional pre-training yields richer contextual representations, setting a new standard for transfer learning and becoming the backbone of modern NLP systems. And here, feel free to read this paper in your own time. You can see here we have view inline, and it will shows us a model or opens up a model containing the BERT paper. And you can see here we have the BERT paper. And this is the architecture of BERT. Pre-training followed by fine-tuning. And also, here we have an implementation of BERT. If you go to Colab, it will direct you to our Colab environment that we will explain the Transformers library using it. So you can see here, this is the Colab environment for Transformers library, and we will explain this code step by step, line by line, code by code in an upcoming section. And also we have here the Hugging Face that directs us to the Hugging Face model card of the BERT model. You can see BERT base model uncased, and he has used this model. It says Transformers library. If you open this, it will show you a model that contains two distinct ways to load in the BERT model. You can see Google BERT/BERT base uncased. Now let's go to the next idea here, and also we have the GitHub that directs you to the GitHub repository of this course, Hugging Face course. Here we have the Transformers library tutorial that we will explain it in this course, where we performed here machine translation, named entity recognition, sentiment analysis, and also tokenization and generation via a GPT-2 model, and also RAG with question answering model. Now let's dive into model families and architectures. This section categorizes the major model families and architectural paradigms supported across the Hugging Face ecosystem. The goal is to provide a clear mental map of architectures explaining why different models exist and which problems they are designed to solve. Encoder-only models, BERT-like. Encoder-only architectures process the entire input sequence bidirectionally, producing rich contextual representations. Optimized for understanding tasks, so they are optimized for natural language understanding, NLU, common uses, classification, NER, named entity recognition, sentence embeddings, extractive question answering. Examples: BERT, Roberta, Distelbert, Albert, DBERT. These models excel at representation learning rather than text generation. Then we have decoder-only models, GPT-like. Decoder-only architectures generate text autoregressively, predicting the next token given the previous context. Optimized for generation and reasoning. Common uses: text generation, chat, code completion. Examples: GPT-style models, Llama, Mistral, Falcon, Quinn. They form the backbone of modern large language models, LLMs. So here we have encoder-only, like BERT, Roberta, Distelbert, Albert, DBERT. They are optimized for understanding tasks. They understand the language very well. Common uses: classification, named entity recognition, sentence embeddings, extractive QA, question answering. But here we have decoder-only, which excel at text generation, chatting, code completion. Optimized for generation and reasoning. The core idea: autoregressively, they generate via an autoregressive mechanism and algorithm. And also we have encoder-decoder models like T5 and BERT. Encoder-decoder architectures combine bidirectional understanding with autoregressive generation. And here, keep in mind, here we say BERT, not BERT. Input is encoded into a latent representation. Output is generated conditionally from the encoded input. Common uses: translation, summarization, text-to-text tasks. Here you can see the main use cases are not text generation, but rather translation, summarization, text-to-text input tasks. And if you know the paper, attention is all you need. In that paper, they proposed a transformer architecture which was consisting of an encoder and decoder the same as this, and they used it for translation task. So the encoder-decoder architecture is best suited for translation and summarization. Examples: T5, BERT, and Meridian. These models unify many NLP tasks under a single sequence-to-sequence framework. So the sec-to-sec, where we receive a sequence, we encode it into very rich representation vectors, then we guide the decoder produces another sequence. And also we have vision transformers, VIT and SWIN. Vision transformers adapt the transformer architecture to image data. Images are split into patches and embedded as sequences. Self-attention models global visual context. Examples: VIT, vision transformers, SWIN transformer, and DIT. They replace convolution inductive biases with attention-based perception. And also we have multimodal models like CLIP, Flamingo-like. Multimodal architectures align or jointly process multiple data modalities, text, image alignment and grounding, cross-modal retrieval, and multimodal generation. Examples: CLIP, Flamingo sound models. These models enable vision, language understanding, and generation. Also, we have speech models, code models, diffusion models. Like diffusion models generate data by iteratively denoising latent representations, high fidelity image video generation, controlled generation via conditioning signals. Examples: Stable Diffusion and other latent diffusion variants. These models dominate modern generative vision workflows. Let's dive into the Diffusers library. Diffusers library, generative vision, and multimodal. The Diffusers library is Hugging Face's core framework for diffusion-based generative modeling. It translates diffusion theory into a modular, production-ready system for high-quality image, vision, audio, and multimodal generation. Diffusion theory, DDPM, so denoising diffusion probabilistic model, DDIM, SDA's stochastic differential equations. Diffusers is grounded in diffusion probabilistic modeling, where generation is framed as a gradual denoising process. DDPM, denoising diffusion probabilistic models, learn to reverse a fixed noise schedule through iterative denoising. DDIM, denoising diffusion implicit models, deterministic or semi-deterministic sampling for much faster inference. Score-based models, SDAs, continuous time formulations, enabling flexible noise schedules and stronger theoretical grounding. And also here we have the Diffusers pipeline abstraction. Diffusers introduces a modular pipeline abstraction that cleanly separates concerns, model components, unit, VAE, variation autoencoder, text encoder, noise schedulers, conditioning inputs, sampling logic. This design allows rapid experimentation by swapping components without rewriting core generation code. Stable diffusion ecosystem. Diffusers serves as the reference implementation for the stable diffusion ecosystem. Latent diffusion for computational efficiency, text to image, image to image, in painting and out painting, seamless integration with community checkpoints and extensions. Also, we have ControlNet, LoRa, and Dream Booth. Diffusers supports advanced conditioning and fine-tuning techniques. ControlNet, LoRa, Dream Booth. LoRa is a parameter-efficient fine-tuning with minimal memory and compute overhead. ControlNet, structural control via edges, depth maps, pose estimation, or segmentation. Dream Booth, subject-driven personalization using small, curated datasets. And here you can see image, video, and audio diffusion. The diffusion model is best suited for image generation, video generation, and in some cases, audio generation. Diffusers extends diffusion modeling beyond images. We have video generation with temporal coherence and motion modeling, audio generation with waveform or spectrogram-based diffusion, multimodal generation with joint text, image, and audio conditioning. And also we have here performance optimizations, memory efficient attention, mixed precision inference, model sharding, and CPU/GPU offloading, optimized schedulers, and sampling strategies. And also you can see here we have a paper of pre-training of deep, or the paper that is of deep unsupervised pre-training using non-equilibrium thermodynamics, and feel free to read that paper in your own time if you like. Here we can open this paper and we'll see deep unsupervised learning using non-equilibrium thermodynamics by Josh Dixon and et al. And you can also go to the Hugging Face. It will direct you to the Stability AI Stable Diffusion XL base 1-0 1.0, the base model of Stability AI, or the major model of Stability AI for generating images using a diffusion latent model. And also, if you go up here, you have use this model. It will open up here diffusers. You can see now we have here diffusers, and you can feel free to use that model in your own environment collab, and it will work for you. And if you go to GitHub, it will direct you to the materials for our course. If you go to the diffusers, here we have the GitHub file or the notebook file stored on GitHub, that what we will explain in this course about the diffusers library of Hugging Face, where we are generating some faces and also generating images using a prompt with diffusion models using a Stability AI model. And if you open in Colab, it will direct you to the diffusers notebook that we will explain in this course using this notebook. You can see now it's loading. Image processing using Python, where we load an image. You can see we have showed here red channel, green channel, blue channel, and also here we have the diffusers library to generate some faces. And also we have used some prompts to generate and produce some images using Stability AI Stable Diffusion. Now, if we also go down here, we have the datasets library. The datasets library is Hugging Face's data backbone designed to make dataset loading, processing, and benchmarking scalable, reproducible, and framework independent. It abstracts away data source complexity while remaining efficient enough for large-scale training. The main ideas here: load local files, use the same code for small experiments, no change required in downstream pipelines when data source change. And also we have here Apache Arrow backend, zero copy reads, efficient memory usage, fast scaling, filtering and batching, language agnostic data representation. And also dataset transforms and mapping. You can see datasets can be transformed using functional reproducible operations: map, filter, shuffle, select. These are different operations to apply on the dataset and to manipulate the dataset for data ordering and slicing. All transformations are tracked, ensuring consistency between training, validation, and evaluation workflows. And then we have some integration with PyTorch, TensorFlow, JAX. You can see we have data loader, direct compatibility with PyTorch, which is nice. The data loader class, seamless conversion to TensorFlow. If you are working with TensorFlow, you know that TF-data is the pipeline to work with data in TensorFlow. So this framework agnostic design ensures datasets remain reusable across diverse training stacks and across different libraries. And also we have here Gradio or Gradio, interactive ML interfaces. Gradio is an interface framework designed to eliminate the gap between machine learning models and usable user interfaces. Its core goal is to make any ML model testable, shareable, and interactive within minutes, without requiring front-end development expertise. Gradio philosophy: ML turned into UI, user interface, in minutes. Gradio is built around rapid iteration and human-in-the-loop interaction. Researchers and engineers can expose model behavior immediately, enabling fast validation, feedback, and collaboration. No front-end or JavaScript knowledge required. Immediate interaction with live mode outputs, designed for experimentation and rapid prototyping. Core components: we have text boxes, images, audio, chatbots. These components abstract away UI complexity while remaining expressive and flexible. Blocks API. The Blocks API also enables more advanced layout-driven interface design, and later we will see how to use this blocks class by going with gr.blocks as demo. It composes complex user interfaces for modular components. Second, control layout grouping, so how to group some elements, and conditional visibility. Build multi-step and multimodal applications. Blocks allow production-grade interfaces while preserving Gradio's simplicity. And also we have some event system. Gradio uses an event-driven execution model, tightly coupled to model inference. Use the actions, trigger, for example, submit, change, click. So when you change the value, do the following code, or when you click on a button, do the following or execute the following function. Python functions are bound directly to events, supports synchronous and asynchronous execution. State management, maintain conversation history, track intermediate variables, enable multi-step interactive workflows. And here you can see authentication and deployment. Gradio includes built-in deployment features like local hosting for development, public sharing links. You can share the links publicly, authentication for private demos, seamless deployment via Hugging Face spaces. And also here we have research demos versus production tools. Gradio excels in research demonstrations. So if you are publishing a machine learning research paper and you want to create a demo that demonstrates how your model works, you can create that easily. Model validation and comparison to compare between different models, educational tools and tutorials. While suitable for lightweight production use, Gradio is primarily optimized for experimentation, prototyping, and human-in-the-loop interaction rather than large-scale consumer applications. And here, if you go to click on Hugging Face, it will direct you to the Gradio main website. Build machine learning apps in Python, create web interfaces for ML models in minutes, deploy anywhere, share with anyone. And here we have plenty of explanations on how to use Gradio. And also if you go here, we have open in Colab. It will direct you to the Colab environment that will contain the code of Gradio that we will explain together in the course. So we have here plenty of cells that explains the functionality and how to use Gradio from the start until you become a professional in Gradio. Now let's go to Hugging Face spaces. Hugging Face spaces act as the deployment and application layer of the Hugging Face ecosystem. They transform trained models into runnable, shareable, and scalable applications, bridging the gap between research prototypes and real-world AI products. Space templates. We have Gradio templates, Streamlit templates, and Docker spaces. Gradio ideal for ML demos. Streamlit suited for dashboards and analytics. Docker full control over runtime and dependencies. Hardware scaling. We have, as we said, CPU, GPU, 0 GPU. GPU is high performance generation and real-time interaction. 0 GPU shared on-demand GPU resources for cost efficiency. And here we can see persistent storage, model checkpoints and fine-tuned weights, cached datasets and intermediate artifacts, user-generated content and application state. And also here we have a very important thing, CI versus /CD. Spaces follow a Git-based CI/CD workflow. Every commit triggers an automatic rebuild. Continuous deployment without manual intervention. Version history enables easy rollback. This provides a simple yet powerful deployment pipeline for ML applications. Spaces as prototypes, minimum variable products, proof of concept demos for stakeholders, user testing environments before full production rollout. And here, if you click on Hugging Face, it will direct you to the spaces page. You can see here we have we have a plethora of spaces here. You can see we have mountains of spaces, and you can try them one by one. Inference and deployment stack. The Hugging Face inference and deployment stack provides multiple layers for serving machine learning models, ranging from simple serverless APIs to high-performance, enterprise-grade inference systems. This flexibility allows teams to balance ease of use, scalability, cost, and latency. Inference API. The Hugging Face Inference API offers a managed serverless way to run models without maintaining infrastructure. So you have the ability to convert whatever model you have, to convert it into an API interface using the Hugging Face Inference API. Instant inference via HTTPS, supports NLP, vision, audio, and multimodal, automatic model loading, ideal for prototyping and low to medium traffic applications. Text generation inference, TGI. Text generation inference, TGI, is Hugging Face's high-performance inference engine designed specifically for large language models, optimized for decoder-only LLMs, supports batching, streaming, and KV caching, designed for high throughput and low latency, production ready for large-scale deployments. Endpoints versus local inference. Hugging Face supports multiple deployment strategies depending on operational needs. Inference endpoints, local inference. Inference endpoints, managed scalable cloud-hosted deployments with SLAs. Local inference, self-hosted models running on local or on-prem hardware. Quantization, INT8, GPTQ, IWQ. Quantization reduces model size and computational cost by lowering numerical precision. So we have several ways to reduce or compress the model size. One of them is quantization, and quantization is the process of lowering numerical precision from, for example, float 32 into floating point number 16. INT8, general purpose quantization with minimal accuracy loss. GPTQ, post-training quantization optimized for LLMs. AWQ, activation-aware quantization for improved performance. These techniques enable large models to run efficiently on limited or commodity hardware. Accelerated inference, ONNX, and TensorRT. ONNX is really important. It's called Open Neural Network Exchange. Hugging Face integrates with acceleration frameworks to improve inference performance. ONNX, cross-framework optimization and portability. TensorRT, NVIDIA optimized runtime for maximum GPU performance. Cost versus latency trade-offs. Inference decisions require balancing several competing factors. Model size versus response time. Numerical precision versus accuracy. Managed services versus self-hosting costs. Batch size versus real-time responsiveness. So keep in mind, these are trade-offs. When you increase one of them, the other will be decreased. So when you have a large model size, then the response time will be slower. But when you have a smaller model size, the response time will be faster and quicker. Numerical precision versus accuracy. The more the precisions there are in your number, the more the accurate your model is. And the less the precision, the less the model accuracy is. Managed services versus self-hosting costs. So when you host by yourself, then you have some costs, whereas when you have managed services. Batch size versus real-time responsiveness. Hugging Face provides multiple layers of the stack so teams can optimize for their specific costs, latency, or reliability constraints. Training, fine-tuning, and optimization. Hugging Face provides a comprehensive training and optimization stack that supports workflow ranging from lightweight fine-tuning to consumer hardware to large-scale distributed training of foundation models. These tools enable practitioners to balance performance, efficiency, and resource constraints. First, we have full fine-tuning. Update all model parameters for maximum task adaptation. Task-specific head tuning. Freeze the backbone architecture and train lightweight task heads. Continual fine-tuning. Incremental updates while mitigating catastrophic forgetting. These approaches allow teams to trade off accuracy, training cost, and time efficiently. And we have here PEFT, parameter efficient fine-tuning. Parameter efficient fine-tuning, PEFT techniques adapt large models by modifying only a small subset of parameters. LoRa, adapters, and prefix tuning. Let's take a look at LoRa. LoRa, low-rank adapters injected into attention layers. Adapters, lightweight modules inserted between transformer layers. Prefix tuning, learnable prompt vectors prepended to model inputs. And we have Accelerate library, which is one of the most important libraries in the Hugging Face world. The Accelerate library abstracts away hardware and distributed training complexity. Unified API for CPU, GPU, and multi-GPU setups. Simplified mixed precision and distributed execution. Minimal code changes required for scale training. Distributed training. Hugging Face supports scalable training across multiple devices and nodes. Data parallelism, multi-GPU integration with PyTorch. Mixed precision training. Mixed precision training improves speed and reduced memory usage. So we have mixed precision, so you are improving speed and reducing memory usage because your numbers are less precision. Combines floating point 16 or BF16 or floating point 32 numerical stability, enables faster training and larger batch sizes, supported natively via Accelerate and Trainer APIs. Checkpointing and resume strategies. Robust checkpointing mechanisms are built into Hugging Face training workflows. So if you aren't familiar with checkpointing, sometimes when you train large models, you won't train these models in one setting. You need to pause the model training and later you can continue. This is called checkpointing. Periodic saving of model states and optimize the parameters. Resume training seamlessly from intermediate checkpoints, versioned checkpoints for experiment tracking and comparison. Evaluation, benchmarks, and metrics. Hugging Face treats evaluation as a first-class component of the machine learning lifecycle. Its ecosystem provides standardized, reusable, and transparent evaluation tooling that integrates directly with training, inference, and deployment workflows. We have built-in evaluation tools, unified APIs for computing metrics, seamless integration with transformers and datasets, support for batch and streaming evaluation, reusable and shareable evaluation pipelines. We have also community benchmarks, public leaderboards, community-maintained benchmarks across NLP, vision, and speech, open comparison of models under standardized conditions. And also, Hugging Face has task-specific metrics. We have some metrics for classification, accuracy, F1 score, precision, recall. We have some metrics for text generation like BLEU, RUG, Meteor, perplexity, question answering like exact match and F1 score, speech like WER, CER, and for vision we have MAP and IOU. And also we have some model comparison on the hub, consistent metadata on published evaluation results, benchmark, tags, and public leaderboards, versioned results linked to specific model versions. And also we have reproducibility and reporting, version pinned models and datasets, documented training and evaluation settings, repeatable pipelines and standardized metric definitions, transparent reporting via model cards and dataset cards. And also here we have safety, ethics, and governance. Hugging Face treats safety, ethics, and governance as integral components of the AI lifecycle. Rather than enforcing a single ethical stance, the platform provides infrastructure, documentation, standards, and access controls that enable responsible development, sharing, and deployment of machine learning models. Model cards, ethics sections, explicit documentation of intended use and potential misuse, disclosure of known biases, limitations, and failure modes, description of trained data, assumptions and scope, guidance for responsible deployment and downstream use. Dataset bias and documentation. Since datasets strongly shape model behavior, Hugging Face emphasizes dataset transparency through dataset cards, clear documentation of data sources and collection methodologies, explicit identification of known biases and representational gaps, licensing terms, consent considerations, and usage constraints. And also keep in mind there are some gated models that you have to get some approval to be able to use them, and responsible access. Hugging Face supports gated repositories to balance openness with risk mitigation. Access may require user acknowledgement, approval, or license acceptance. Usage conditions and legal constraints can be enforced. Sensitive models can be shared without unrestricted distribution. And also we have some alignment considerations like clear definition of intended behavior and scope, mitigation of harmful, misleading, or unsafe outputs, evaluation against misuse scenarios and edge cases. Open versus restricted models. The platform supports a spectrum of openness tailored to a contextual risk. Open models, fully accessible weights, code, and metadata, while also we have some restricted models, limited access due to safety, legal, or ethical concerns. Here you can see we have Hugging Face for research. Also, you can use Hugging Face as a platform for research if you are a researcher or if you are a machine learning researcher. Hugging Face has emerged as one of the most important infrastructures for modern AI research. It enables reproducibility, open collaboration, and large-scale dissemination of research artifacts, transforming how machine learning research is published, validated, and extended. Reproducing papers. Hugging Face is the primary platform for reproducible AI research. Researchers publish trained model weights alongside code and configurations. Exact model and datasets states can be pinned using commits and revisions. Standardized APIs reduce implementation ambiguity across frameworks. Research repositories, experimental models and baselines, official implementations released by research labs, community replications, benchmarks, and appellation studies. And also we have open weights movement. Hugging Face is a central driver of the open weights movement in AI, public access to model parameters and configurations. So we have public access to model weights and model parameters, transparent comparison between open and closed models, accelerated collective progress through shared security. Collaboration workflows, shared repositories and organizations for teams and labs. They provide version control for models, datasets, and experiments, issue tracking, discussing, and community-driven improvements. Citations and academic usage. Citation metadata embedded directly in model and dataset cards, extensively referenced in top-tier conferences and journals, increasingly used as the default distribution layer for research artifacts. Here we have Hugging Face for industry and startups. Hugging Face plays a critical role in translating AI research into production-ready systems. Its ecosystem supports startups and enterprises across the full lifecycle, from experimentation to secure, scalable deployment while maintaining flexibility and cost efficiency. Production pipelines. We have model discovery, fine-tuning, and version management. So you can discover models, you can fine-tune them, and you can also manage the versions. Integration with CI, CD, and MLOps, machine learning operations workflows, smooth transition from research experiments to deployed systems. Private hubs. Also, we have some private models, some private datasets and spaces, controlled access within teams and departments, secure sharing of proprietary and sensitive assets. Enterprise security. Token-based authentication. Some models need some token-based authentication for APIs and services. Role-based access control. If you are admin or if you are non-admin, there are some role-based access, control access organizations, compliance-ready deployment options for regulated environments. Model monitoring, versioned model deployments, performance and quality tracking over time, controlled updates, rollbacks, and release management. So production systems require continuous visibility into model behavior. Cost optimization. Methods like quantization and optimized inference engines, flexible hardware selection and auto-scaling options, trade-offs between managed endpoints and self-hosted inference. Hugging Face enables cost-aware deployment strategies. And there are some real-world case studies: NLP-driven search, recommendation, and customer support systems, computer vision applications in healthcare and manufacturing, speech and multimodal AI products in consumer and enterprise settings. And here we have Hugging Face for education. You can use also Hugging Face as a platform for educating yourself. Hugging Face plays a central role in modern AI education by providing open, hands-on, and scalable learning resources. Its ecosystem enables learners, educators, and institutions to move from foundational concepts to advanced real-world AI systems using the same tools employed in research industry. Hugging Face supports structured learning paths that guide learners progressively through the AI landscape. Step-by-step progression across NLP, vision, speech, and generative AI, hands-on interaction with real models and datasets, clear linkage between theory, code, and deployment. Courses and tutorials. We have structured tutorials for transformers, diffusers, and datasets. Code-first explanations using notebooks and runnable examples. Content tailored for beginners, practitioners, and advanced researchers. Community notebooks. Also, there are reproducible experiments and research demos you can benefit from. Fine-tuning, inference, and evaluation examples. Step-by-step educational walkthroughs for models and datasets. Teaching with spaces. live demonstrations of models and algorithms, student accessible applications without local setup, visual experiential learning that complements theory. And here we have also open curricula, freely accessible educational materials, community reviewed and continuously improved content, adaptable resources for universities and professional training programs. Here also we have Hugging Face plus AI agents. Hugging Face plays a foundational role in modern AI agent systems by providing open, composable, and production-ready models that act as the cognitive and perceptual core of autonomous and semi-autonomous agents. And here we have also so many points about the agents. For example, large language models for planning, reasoning, and multi-step decision-making, fine-tuned task-specific models for specialized skills, open weight models enabling transparency, inspection, and control. Also here we have, you can see, function calling via structured prompts and output schemas, models trained specifically for tool identification and API interaction, reliable parsing of model outputs for downstream execution. Also we have RAG, retrieval augmented generative or generation pipelines with Hugging Face, embedding models for semantic retrieval, vector database integration through open standards, generative models grounded in retrieved external knowledge. Multimodal agents, we have vision language models, audio text models, multimodal fusion enabling environment-aware agents. Here also we have some frameworks to deploy agents, LangChain for tool orchestration, memory, and planning, compatibility with other agent frameworks and planners, standard APIs enabling plug-and-play interoperability. Here also we have some Hugging Face ecosystem libraries. Beyond model hosting and inference, Hugging Face provides a rich set of supporting libraries that together form a complete modular machine learning ecosystem. These libraries handle pre-processing, training, evaluation, optimization, alignment, and secure model distribution. For example, tokenizes, accelerate. We have the evaluate library, optimum, PEFT, PFT, TRLF, RLHF, Safe Tensors library, and also here we have ecosystem summary. Together, these libraries form the invisible infrastructure, the hidden infrastructure of Hugging Face, enabling speed, scalability, safety, and reproducibility across the entire AI lifecycle, from pre-processing and training to deployment and alignment. And here we have Hugging Face and research papers. Here we have some papers. For example, what papers on Hugging Face means. On Hugging Face, a research paper is represented through a dedicated paper page that aggregates everything required to understand, reproduce, and extend the work. A paper page typically links the original research paper, usually on archive, associated models hosted on GitHub or on the hub, datasets used or released with the paper, interactive demos and spaces showcasing results and the model, community activities such as likes, downloads, and discussions. Ways papers appear on Hugging Face. We have author-published papers, also have institution or industry releases. We have community-driven references and replications. There are also trending papers and discovery. You can also discover models via some criteria. Hugging Face maintains a dedicated papers section that highlights trending papers based on community engagement, newly released or rapidly adopted research, papers connected to fast-growing model repositories. Relationship with papers with code. Hosting with the runnable artifacts themselves, models, datasets, demos, enabling one-line loading of research models, making reproducibility a default, not an afterthought. Paper cards and metadata. Paper pages on Hugging Face include structured metadata that makes research actionable. Title, authors, and publication source, abstract and concise summaries, linked models and datasets, citations and bibliotecs entries, community signals such as likes and activity. And this website, which is called here the Hugging Face Paper Hub, previously was called Papers with Code. So if we search into here, Papers with Code, it will direct you to the trending papers section on Hugging Face. Here we have a page on Hugging Face dedicated not to models, but specifically or particularly dedicated to papers. Here we have also daily papers. You can see there are daily papers. You can also sort by weekly papers. And also you can sort by monthly papers. And here we have a search bar. You can search any paper with AI. For example, the paper Attention is All You Need. Here you have the paper Attention is All You Need. You can go to it. Here they provide you the authors. They provide you with the title, as you mentioned, some description or the abstract of the paper. You can see the dominant sequence transaction models. And also here we have a link to archive page, view archive page. You can be directed to archive to the Attention is All You Need paper by Ashish Vaswani et al. And here we have also a view PDF. It will show you a PDF file of the paper directly. And also we can go down and add to collection. Also here you can see the community. They are posting some comments on this paper. Also you can post some comment here and submit your comment, and your comment will show up over here. Okay, so this is the papers code currently hosted on Hugging Face. Here if you go to community, we have blog articles, social posts, and we have here daily papers. So you can access that via the homepage of Hugging Face. Go to the community tab, then open the drop-down menu, go to the daily papers, and it will direct you to this page that contains these papers. And you can see by AK and the research community. Now let's go ahead to our atlas and complete here. So you can see we have so many of the Hugging Face stuff here about the papers. But let's go to recommended academic work on Hugging Face. This section curates foundational and influential academic papers that directly underpin the Hugging Face ecosystem. These works define the theoretical, architectural, and methodological foundations of the libraries, model families, and workflows supported by the Hugging Face platform. Here we have Transformers library, for example, Attention is All You Need. We have also BERT, Roberta, Decoder Only, for example, GPT model by Alec Radford et al. And also we have the GPT-2 model, encoder decoder models, model families, for example, vision transformers, multimodal models, speech models, code models, audio models, diffusers library that contains foundation models, diffusion models, for example, denoising, diffusion, probabilistic models, DDBM, and DDIM, denoising, diffusion, implicit models. So you have here probabilistic models and implicit models. And also we have score-based and STE frameworks, score-based generative modeling through stochastic differential equation by Yang Song and Stefano Ermon. And also we have here latent diffusion / stable diffusion, which is a latent diffusion model. You can see high resolution image synthesis with latent diffusion models by Rombach and et al. And also we have conditioning and ControlNet, Dreambooth, and LoRa. And here we are. Now we have finished discussing the Hugging Face theory. You can see this is a comprehensive journey and a comprehensive atlas that combines all that you need to have to know about Hugging Face in one page. It's poloclub.github.io Transformer Explainer. So here you can see, first of all, we have some slides that explain the architecture of the transformer. We can close them now, but let's focus on the interface. First, we have an input that will generate. You can see here, data visualization empowers users to visualize. Here you can write whatever sentence you need or whatever sentence you would like, and then you can click generate and it will generate. So let's click generate. You can see now it do one forward pass and then it tries to generate, and now the model generated that. Let's click another time. You can see it will generate another time to visualize the world. So data visualization empowers users to visualize the world, and then click generate around them. First here you can see we have some embeddings. So we first start by inputting some sentence, inputting a sequence. As we said in here, we first start by inputs. These inputs will be processed by two steps. If we click on the embedding here, you can see we have two steps. We have token embeddings, which are here. We have these IDs. You can see 6,601. So these words, these tokens are mapped into integer IDs. Then these integer IDs are poor representations. They don't convey the semantic meaning. We need another way to represent them. So the best way to represent the words is via the token embeddings and turn them into embeddings, into dense vector embeddings. After that, we preserve the position encoding. Here you can see we have this input embedding layer, which will turn the token IDs, integers, into vectors, high, rich representation vectors. Then we preserve the contextual meaning via this layer, positional encoding layer. Here, this position encoding layer will preserve the meaning. You can see data is at the first position, visualization is at the second position, 1, M is 2, powers 3, uses is 4, 2 is 5, and so forth. So we have token embedding, and then you can see here tokenization splits input text into tokens. Tokenization segments input text into tokens, small units like words or subwords or parts of the words. The GPT-2 small has 50,257 token vocabulary, each with a unique ID. In the token embedding step, every token is matched to a 768 number vector. So each token is converted into a vector of size 768 number inside the vector from a large lookup table. And these vectors are land. These are land vector representations. The model will, when we train the model later, the model will adjust and fine-tune these values inside each vector to best represent the words. And then similar words will be clustered together. Dissimilar words will be clustered far away. These vectors are learned during training to best represent each token's meaning. After this, we have this position encoding layer, which we can see here. Word order matters in language. So the word order or the order of the words matters. Position encoding gives each token information about its place in the sequence. So since transformer as a standalone architecture doesn't learn the order, doesn't capture the contextual meaning, we need to preserve them. GPT-2 does this by adding a learned positional embedding to the tokens embedding. But newer models may use other methods like rope, which encodes position by rotating certain vectors. All aim to help the model understand order in text. After this, after we have processed the text, we can input this processed text into the encoder, which contains the multi-head attention layer. Here we have the you can see we have now the transform block, which is this area that is bordered. If you close this, we have the transformer block. The transformer block, which is the bordered area. We have multi-head self-attention alongside with the multi-layer perceptron. And if you go down here, we have after the embedding, so here we have embedding and we have tokenization, we have token embedding. Here we have the transformer block. The transformer block consists of two things. We have the multi-head self-attention, and then we have after this, we have the multi-layer perceptron. Here, multi-layer perceptron MLP. So these are the two main components. As you can see in the image, we have multi-head self-attention alongside with the feed-forward network. The first thing here, let's start by the first thing, multi-head self-attention. Multi-head means we apply several numerous attention processes in parallel. So here, if you click on them, self-attention lets the model decide which parts of the input are most relevant, are most significant to each token. This helps it capture meaning and relationships, even between far apart words. In multi-head form, the model runs several attention processes in parallel. So in multi-head form, the model runs several attention processes in parallel, each focusing on different patterns in the text. And here you can see inside the multi-head self-attention, we have three key matrices, three important matrices. We have the key matrix, query matrix, and value. The key here, if you click on this, we have query, key, and value. So the key and Q and value are three learned vectors that the attention will learn and update them. To perform self-attention, each token's embedding is transformed into three new embeddings. So each token's embedding, the data, visualization, each word will be converted or transformed into three new embeddings: query, key, and value. You can imagine this as an analogy. We have the search engine Google. when you type in the text, the type in text that you type into the search bar, this is the query. So here we have this search bar. You can search in here, what is machine learning? This is the query. This is what you are looking for, what you are searching for. What do you want? What you are looking for behind the scenes. This is the query, the queue. When you click enter, Google suggests multiple websites, IBM blog, Wikipedia blog, Datacam blog. These are the case. These are the case that suggest themselves, that say, I have, choose me, I have the answer, I am fit to you, I am appropriate to you. Then we try to multiply, here you can see, we try to multiply the K by Q and see how much or how far or how close these two together. Then when we decide that this is the closest K to Q, we choose, or we assign them the highest weight to its corresponding value. The value is the actual content, the actual information inside the K. So K will provide us with this V. This is the V, the actual content that will be used or will be passed. So here we have, you can see these parameters, weight and biases. So this transformation is done by applying different weights and biases to each token embedding. These parameters, weights and biases, are optimized through training. Once created, queries compare with keys to measure relevance, to measure similarity, and the relevance is used to weight the values. So if it represents a higher measure, a higher similarity rate, a higher closeness rate, then we assign a high weight to the value. If it's a low relationship or a low correlation between K and V, between Q and K, we assign a low weight to the V. You can see here, them is assigned a high probability, whereas us is assigned a low probability. So you can see here, the V is passed through here, and then we have data moves through the residual connection, then we have them as 98.32% as a high weight. So we say that the Q is multiplied by the K, and then we scale it via, if you click on here, it will multiply the K by the Q, then it scales that via this equation, Q multiplied by the K transpose divided by the square root of the dimensions of K, then we plus the mask. So here we have the dot product, the multiplication, we multiply Q by K transposed, and we transpose the K because in the multiplication of algebra, we need to transpose the other matrix in order to be compatible to multiply the two matrices or the two vectors. Then we mask it to prevent access to future tokens, and then we have the softmax. We apply the softmax on this masked addition. Then we have a probabilities here. You can see we have some high probabilities. For example, the word visualization is assigned a higher probability. You can see 84, whereas some words here have low probability. For example, 0.03. Then we have this value. We will take these values and then will be passed as the output here. Then we'll go through the multi-layer perceptron. So the main idea of the attention here is that it's a mechanism in machine learning that directs deep learning models what to focus on, what to prioritize. So which parts here should we prioritize? Should the model prioritize and gives the most attention and pay attention to? After this, we have the multi-layer perceptron. The multi-layer perceptron is a feed-forward network that refines the learned representations by the attention. Here we have, you can see MLP. So the attention output goes through an MLP, multi-layer perceptron, to refine token representations. A linear layer, which is a feed-forward layer, a simple feed-forward layer, changes embedding values and size using learned weights and bias. Here in the MLP, also we have learned weights, learned biases. So the embeddings here are learned, the KQV are learned, the MLP weights and biases are learned. So you have here three main areas that those areas are learned. A linear layer changes embedding values and size using learned weights and bias. Then a nonlinear activation decides how much each value passes. Many activation types here in the MLP exist. GPT-2 uses GLU, which lets small values pass partially and large values pass fully, helping capture both subtle and strong, robust patterns. After this multi-layer perceptron, here you can see we have this residual connection, and also here we have a residual connection. You can see we have this residual. We pass the raw input as it is without any transformation as the output of this attention or multi-heads of attention. So we combine the transformed data that goes through this attention layer, we combine it with the raw unchanged input from here, we pass it as a residual. You can see residual connection. What is the main idea of residual? Residual connections helps to stabilize the training and the gradient flow of the neural network. So transformers have extra features that enhance the model performance, but aren't core to understanding the basics. For example, a residual connection adds a layer's input to its outputs, keeping information and learning signals from fading, keeping them to not fade, to not vanish through many layers. In GPT-2, it's used twice per block to train deeper stacks effectively. And the same idea, we apply another residual connection in the multi-perceptron. So we take the inputs of the multi-layer perceptron and then we pass them here to combine them, to add them with the outputs of the multi-layer perceptron. So here you can see we have residual connection. And also here you can see the layer normalization. So if we return to the image, here we have the inputs to the multi-head attention. We add a residual connection and combine the untransformed version with the transformed version, and then we have the normalization layer. The main idea behind the layer normalization helps stabilize both training and inference by adjusting input numbers so their mean and variance stay consistent. This makes the model less sensitive to its starting weights. This makes the model less sensitive to its initialized weights and helps it learn more effectively. In GPT-2, it's applied before self-attention, before the multi-perceptron, and once more before the final output. Then here you can see we have 11 more identical transform blocks. So we have the same block as this, but multiplied by the nx11. So we can slide between them. You can see we have another block, a third block, and each block tries to learn different representations, different patterns, different weights, and trying to capture the semantic and syntactic representations of each sentence. So here, this block here, you can see, is multiplied nx times. They multiplied this block, you can see here, the transformer block, they multiplied this 12 times. So we have 12 of these blocks that will learn the representations in parallel, fully parallelizable manner. After this, so we have here 11 more identical transformer blocks, and then we have the probabilities. You can see here we have the probabilities, and then probability of them, the word them here, token being sampled. We have some sampling techniques here to choose the best next word. You can see we have the scaled logit. So here, temperature hyperparameter. Temperature is the most important hyperparameter in the transformer architecture. It works by scaling the logits before turning them into probabilities. A low temperature, for example 0.2, makes large logits even larger and smaller ones even smaller, favoring the high scoring tokens and leading to more predictable choices. A high temperature, for example 1 or above, flattens the differences, making less likely tokens more competitive and leading to more creative outputs. So if we decrease the temperature, you can see the model is the most deterministic approach. So it takes a strong deterministic approach. So here you can see the word them takes 100%. Whereas if we increase the temperature, the model becomes creative and creative and creative. So the more temperature, the more creative the model. The more creative the model. You can see here the probabilities get distributed over the tokens. And here you can see again we have the top k filtering. We choose the k equals 5. Then you can see the sampling strategy. Finally, we need a strategy, an approach to pick the next token. Many exist, but here are common ones. Greedy search picks. You can see here we have the greedy search. You can change the k. So we can choose the first k, just only the first k. We can choose just 2 k's or 3 k's. You have k equals 3. We choose the 3 highest performing k's. And if we increase them, it increases. So here, the top k keeps only the k most likely tokens. And top p keeps the smallest set whose total probability is at least p, trimming unlikely ones early. Then softmax turns the remaining logits into probabilities, and one token is picked at random from the allowed set. So here you can choose whether it was top K or top B. If you choose top P, then it is there. Then it generates the word there. Whereas if you choose the top K, then the top K here is the word, you can see the top K, K equals 1, it chooses the word them. So you can play around with that in your own free time. And then we can slide between the transformer blocks. We can go to the third block, fourth block, and see the attention weights here change. You can see here, the attention weights here are different from here. Every block learns different patterns, learns different representations. Until we have, then we have here some examples. For example, IEE, this conference highlights the, then it tries to generate, highlights the importance, generate of, generate. So it moves through all these steps, multi-perceptron, residual, probabilities of the, then it generates. Also you can write your own text. For example, I like reading, generate. Then it tries to generate here, you can see the Q, K, V vectors. I like reading about, generate. You can see here, I like reading about the, generate another time. Now we have the V here combined, I like reading about the history, which is a really nice topic. Then if you go down here, you can read more. What is a transformer? Transformer is a neural network architecture that has fundamentally changed the approach to artificial intelligence. Transformer was first introduced in the seminal paper, Attention is All You Need, in 2017. So you can feel free to read this paper, Attention is All You Need paper. And then we have, and has since become, and since then become the go-to architecture for deep learning models, powering text generative models like OpenAI's GPT, Meta's Llama, and Google's Gemini. Beyond text, Transformer is also applied in audio generation, image recognition, computer vision, protein structure prediction, AlphaFold, and even game playing, demonstrating its versatility across numerous domains. And here we can see we have the Transformer architecture. We have embedding layer. The input text is divided into smaller units called tokens, which can be words or subwords. After this, we have the transformer block. The block consists of two important mechanisms, the attention mechanism and multi-perceptron. So inside each transformer block, we have two important core things, attention mechanism and multi-perceptron, and hence the name attention is all you need. We remove recurrence, we remove convolution, we just attend to the most important significant parts and pass them to a multi-perceptron that refines the gradients. Then we have outer probabilities, the final linear layer, and softmax says transform the processed embeddings into probabilities. And you can read the rest in your own time. So you are more than welcome to explore the rest of these. And here you can see we have the main idea behind residual connection. Residual connections were first introduced in the ResNet model in 2015. This architectural innovation revolutionized deep learning by enabling the training of very deep neural networks. Essentially, residual connections are shortcuts that bypass one or more layers, adding the input of a layer to its output. This helps mitigate the vanishing gradient problem, making it easier to train deep networks with multiple transformer blocks stacked on top of each other. In GPT-2, residual connections are used twice within each transformer block, once before the MLP and once after, ensuring that gradients flow more easily and early layers receive sufficient updates during backpropagation. In this section, let's dive into one of the most brilliant tasks in the world of natural language processing, which is text generation. We will download and load the model GPT-2 from the Hugging Face platform and use it to do this task, particularly text generation. So the first thing, let's put a title here, a nice title, as text generation using GPT-2 model from Hugging Face library. And let's put here the icon Hugging. As you can see, then let's dive into the first thing, which is importing the libraries. How to grab or fetch a model from inside the Hugging Face platform. So first, here we have the main page or the home page of Hugging Face. You can see here we have models, datasets, spaces. These are the three main components inside Hugging Face. Models, which are machine learning, deep learning models. Datasets, which are the datasets, the data that you want to use to train a model and to test the model. Spaces, which are a visual Gradio interface that visualizes the model and how it works, how it operates. So let's go to models. Here you can see we have the models number. We have 2,285,909 models, a large number. Let's search into here GPT-2. You can see here we have OpenAI-community/GPT-2. Let's go and click on it. Here we are directed to the main page, the main model card. They call it model card. As you can see, model card. This is the model card of GPT-2. And you can see here how many likes did they get. They have 3,000 likes. You can follow that if you like. I can give this a like. You can see. Now I liked it. Here you can see we can copy the name of the model, OpenAI-community/GPT-2. And if you go down, how many downloads did they have? Downloads last month, 8,868,469. Okay, and then you can go here. You can see the number of parameters, the model size, and here feel free to read about this. This is the explanation and the description, some meta information about this model. So you can see here how to use it. Actually, there is some cells that explain how to use this model. You can see generator equals pipeline past text dash generation. This is the name of the task. The task you want to conduct is text generation. Model equals GPT-2. Then you can see they have passed some info here, some prompt. Hello, I am a language model, and this is the answer of the language model. Okay. Let's go ahead and use this model by going here and then click on transformers. Here we have a model that shows two blocks or two sections. The first section uses a high-level helper, which is a great option, and the second option is load model directory. This way, the way that we will use in this lesson and that we used, we saw that from transformers import auto tokenizer, auto model for causal LM, and this way uses a high-level wrapper or helper called pipeline. Let's use both options. Let's copy this, go ahead and paste it over here. From transformers library, import pipeline. This is a high-level helper. Then we use that function and pass here two arguments, just two parameters. The task you want to do, text dash generation, and the model that you want to leverage, OpenAI-community/GPT-2. Let's run that. You can see now it is trying to download this model from using the pipeline function. Now it's connecting. Okay. Here you can see it's now loading the model. The task, as we said, text generation. So this model tries to generate some text. The model that we need to leverage or use is GPT-2. Now it takes some time to download and load the model into the environment Colab. And you can see here now it's executing. It's taking 27 seconds so far. By the way, you can go to Hugging Face and then models and then go to tasks, then choose the task text generation from here, NLP, natural language processing. Go to text generation. Here we have plenty and a plethora of models, of text generation models that you can use. Okay. So for example, we have this model from OpenAI. It's called Circuit Sparsity. NVIDIA also has a model called Neometron Orchestrator. Non-biggie. You can see Llama. Also, you can use Llama model. So these are all the text generation models. You can see here we have text generation. How many models do we have? Well, we have here 303,000 models, all dedicated to the task of text generation. Here we can see that the model is loading currently. You can see it's trying to load some libraries, some, for example, model.safe tenses. This is a sub-library, generation config.json, and we have all this. Then device set to use CPU. So this is the process to load a model using the pipeline. Now as you can see, the model now is successfully loaded. Let's use that model by going to here and calling pipe. You can see pipe and then pass into here some text. Consider this as a prompt. So you can define a variable called prompt equals what is machine learning, then pass this prompt directly to the pipe. That easy. It's easy as that. So you can see now the model is trying to pass this prompt to the pipe. You can see here the benefit of using the pipeline here is that you don't need to tokenize the sentence. So you don't need to pass this sentence as we did to pass it to the tokenizer. Then you get token IDs, then you pass to the GPT model. No, here you can see we have a list. Inside this list we have a dictionary, then we have the key called generated text. Now to fetch that key specifically, we can go ahead and store this inside a variable called output, like that. Okay, then we can step through that output, step into it, and fetch the value of the text. Okay, so we can go output and then at index 0 to get the dictionary, then we can go the key called generated underscore text. So wait until this finishes loading. So you pass the sentence to the pipe, then we store that value inside the variable, then we can use that variable freely. Now we can see, run that. Nice. Now we have this text. What is machine learning? It's not very hard to understand. This is the answer of GPT. You can see this is my prompt. Okay, then this is the answer. It's not very hard to understand. It's one of the reasons that why we've been able to develop the neural network for some time and blah blah blah. Now if you want a nicer and neater format of this, we can pass this to the print function. Okay, so pass this, because why? Here you can see we have \n, and it's not interpreted well. So yeah, here we have \n. So print function will interpret that into an actual line, into a new line. Print, you can see we have a nicer output, as if you ask GPT in its interface and it answers like that. What is machine learning? It's not very hard to understand. It's one of the reasons why we've been able to develop the neural network for some time, and you can feel free to read that. So give whatever prompt you would like, and the GPT will answer, GPT-2. The second approach is that we can go ahead, go up, use this model. You can see the library here is transformers. Then we have another option here, which is this, from transformers import auto tokenizer, auto model for causal LM. Let's go ahead and use that approach. Run it again. You can see this approach is a lot faster. Now we have a model, this model. Okay, we can go ahead and this is the architecture of the model, GPT-2. But keep in mind, you have to tokenize your text before passing it to this model, as we saw before. So that's it. That is for text generation. You can go ahead, as we said, models, and then choose the tasks from here. Choose the task as text generation. Now let's move on to another task in Transformers library. Now, as an alternative way, rather than copying those codes from Hugging Face platform, we can write them straight away in here. In this section, we will use GPT-2 model from Hugging Face platform. So the very first thing we need to do is to import the Transformers library. So let's go from Transformers, import auto tokenizer. So this is auto tokenizer class from Transformers library. Then we will call the method from pretrained and then pass in GPT-2. So as you can see now, it is trying to import the class auto tokenizer from the library Transformers. Then the next step is to instantiate a new object called tokenizer equals auto tokenizer, and then dot from pretrained pass into here GPT-2. So as you can see, and then run that. So now we are fetching the model GPT-2 using the method from pretrained that is coming from the class auto tokenizer. As you can see here, this class, this is a generic class, tokenizer class. as you can see, that will be instantiated. Then we call the method from pre-trained and then use one of the language models that is provided in Hugging Face. For example, in this example, or in this case, we use GPT-2. Then we have a tokenizer ready. So let's try this tokenizer by giving sentence or sentence equals unsure. Okay, then we need to pass this sentence to the tokenizer object by going input underscore IDs equals tokenizer, and then pass into here the sentence. Then I want you to notice here, if you pass this sentence, as you can see, sentence, then we didn't specify the parameter return tenses as PT, it will return list. So let's take a look at this, input underscore IDs. We pass the sentence into here, as you can see. Now we have, this is a dictionary, then the input IDs are in the form of list. So if we go ahead and access this key, input underscore IDs, then we will get here a list. If you want to return these IDs inside of a tensor, inside PyTorch tensor, let's specify return underscore tensors equals PyTorch, PT. So PT is short for PyTorch. And then let's run that again. And as you can see, successfully, now we have PyTorch tensor. Now let's take a look at unsure word. Why unsure word is splitted into two numbers or into two IDs? Well, because unsure is a word that is divided using the sub-word level tokenization level. So we have un as a separate token, which is this ID 13,271. Then we have sure. Sure, a separate word, a separate token, as the ID 495. Okay, so some words you have to keep in mind that some words will be splitted, will be segmented into more than one segment. So not necessarily one word is one token. Maybe one word generates more than one token, generates more than a single token. Okay, so as you can see, we have now IDs. How to get back to the word unsure? Well, to get back to the unsure word, we have to use the method decode by going tokenizer.decode, as you can see. Then we pass into here the input underscore IDs. Then let's access at index 0. It decodes that into the word unsure. So we got back into the word unsure, as you can see, by passing the IDs to the method decode. Okay, then it gets back to the unsure word, as you can see. The next step is, let's try another word. Let's try, for example, the word unbelievable by going, for example, sentence equals unbelievable, like that. Then we pass this sentence to the tokenizer by going input underscore IDs equals tokenizer, and then pass into here the sentence. Then we specify the parameter return underscore tensors equals PT for returning the tensors in the form of PyTorch tensor. So here we are saying, hey, please tokenizer, return the IDs stored into a PyTorch tensor. Then dot input underscore IDs, so we get right up the PyTorch tensor. Then we have the input underscore IDs. As you can see, we have these IDs. So as you can see here, we have the word unbelievable, and it is divided into 3 tokens. Let's figure out what are the actual parts. What are these actual parts by doing a for loop. So for token ID, for every single token ID in these IDs in input underscore IDs, as you can see, at index 0 to get this segment here, this list, the inner list. Then we go ahead and print tokenizer.decode and then pass into here the token underscore ID. So if you run this 3, 2, 1, we have the actual segments, the actual parts that these IDs correspond to. So 403 correspond to un. Then we have 667 corresponds to bill. Then we have evable. So as you can see, unbelievable. Then let's figure out another word. Let's take another example. For example, the word homoskedasticity by going word, for example, equals homoskedasticity, like this. Then let's pass it to the tokenizer by going tokenizer.decode and then pass word. Then let's set the parameter return underscore tenses equals pt, short for PyTorch, dot input underscore IDs. And let's store this value into a variable called, for example, my IDs. Then let's print that, my underscore IDs. As you can see, here you have input IDs. Let's run that. So now this tokenizer will work on the word homoscedasticity and tokenize it, segment it, and return the IDs. Let's see what this error is. So IDs can't extract string to Vic. So yeah, I think here we have to return tenses pt. We pass, yeah, we need to specify the function as tokenizer. Okay, so now we have these IDs, as you can see. So I used .decode, and in fact, I have to pass the word straight away to the tokenizer. So as you can see here, we have these IDs, 26452, 418, 771, and to the rest. So the word homoscedasticity is being divided up into 1, 2, 3, 4, 5, into 5 different tokens, into 5 different words. So I want you to imagine or have an idea that a single word doesn't necessarily represent one single token. It could be split up into several tokens. It could generate multiple tokens and generates multiple segments. Okay, so let's take also another example. Like, for example, let's decode it. So tokenizer.decode, and let's get back to the real world homoscedasticity. So now I have IDs. How do I know what these IDs correspond to? What is the word behind these IDs? By passing my IDs to the function decode, and we have to specify here at index 0, or for example .squeeze, okay? Then we can pass it here. We have here homoscedasticity. So if you use here at index 0, it will also work in a nice way. And if you specify here .squeeze, so you squeeze it, you get rid of this outer list brackets, then it also works. Homoscedasticity. Okay, and feel free to use this tokenizer. So this tokenizer is based on what? Based on GPT-2. If you call this tokenizer on its own to get some information about it, you can see that name or path is GPT-2. So this tokenizer is based on the tokenizer that OpenAI used for GPT-2 model. The vocabulary size here, so the number of vocabulary words is 50,257 tokens. So keep in mind, these are not words, these are tokens. So maybe there are words that was splitted into multiple tokens. So these are the tokens, 50,257. Then we have model max length. So the model maximum length is 1024. This is in terms of GPT-2. But here you can take a look at several information about this tokenizer. So this tokenizer now is using the GPT-2 model tokenizer. Feel free to change it to any word. Now let's try a long word. For example, the word pneumono ultramicroscopic silicovolcanoconiosis. If you go to Google and write in here pneumono ultramicroscopic silicovolcanoconiosis. So this is the longest word in the English language. Let's copy it and go word variable equals this word, and then let's tokenize it. So I wonder how many tokens this word results into. Let's figure that out together by passing this word to the tokenizer. So let's go my IDs equals tokenizer dot tokenizer, then pass into the word. Pass here the word, this variable, pass it to the tokenizer. Then let's specify here return underscore tenses. Should I return tenses? Yeah, and in the form of PyTorch dot input underscore IDs. Then print out my IDs. Show me your IDs. Wow, you can see here we have multiple IDs. So 1, 2, let's get the length. We have the length method. We have at index 0. We have 15 different tokens. So this word, this long word, this is the longest word in English, actually. It results into 15 different segments, 15 different tokens. Okay, and if you want to see them, they are as this: my IDs. Then these are my IDs: 79, 25668, 261. So these are IDs. So the first thing, we have tokenization. tokenization is the process of tokenizing or segmenting or breaking up the sentences, the words into tokens. Then we map these tokens into IDs. Then after that, we pass these IDs to an embedding layer. The embedding layer maps these IDs into vector embedding representations. Then we have vector representation objects. We can preserve the positional encoding, then pass these embeddings to the transformer encoder. Then we have a GPT model, okay, or to a decoder. Then we have a GPT model. So the first thing, we tokenize the text into tokens, into segments. We map these tokens into IDs. We convert these IDs into vectors. Then we preserve the positional encoding. Then we pass it to an encoder or decoder, depending on the architecture you are using or leveraging. So now that's enough for the tokenization process. We saw multiple words. Also, we can do a for loop on this by going for token ID. So for every single ID in my IDs dot squeeze, okay, let's go ahead and print tokenizer dot decode, tokenizer dot decode. So decode it, and then pass here token underscore ID. These are the segments. You can see numino. P is a separate token. Num is a separate token on numino ultra microscopic silico volcanoconiosis. So GPT model sees this long word, sees it as these segments. Okay, so it processes the word numino ultra microscopic silico volcanoconiosis as these segments. You as human, you see it like that, in a string fashion. Numino ultra macroscopic silico volcanoconiosis. But for the GPTs, they see it as these segments separately. Now let's move on to the word, for example, anti-disestablishmentarianism, by going sentence equals, and then let's search on Google anti-disestablishmentarianism. Let's copy this word. This is, I think, the second longest word in English language. Let's paste it into here, then pass it to the tokenizer. Let's discover how many tokens that will be resulted when we pass this word, pass it to the tokenizer object. So by going my IDs, or for example, let's name it token IDs. Let's verify the name of the variables. Then pass here tokenizer, pass here the sentence, then comma return tenses equals pt dot input IDs. By going dot input, the attribute input underscore IDs. Then let's print this variable token underscore IDs and see how many IDs that are being generated. Well, as you can see, we have these IDs. And if you get the length, and then pass token IDs at index 0, we have 5 different tokens. So 1, 2, 3, 4, 5. So this word is being splitted up into 5 different tokens. Also, there's a last word called floxino-synhelibification. So let's go word equals, search here, floxini-synhelibification, which is also considered one of the most longest words in English. And then pass this to the tokenizer by going my IDs equals tokenizer dot, and then pass word, comma, return underscore tenses, specify it as pt for PyTorch dot token dot input underscore IDs. Then let's print out my IDs. And these are my IDs, as you can see. And how many IDs we have? Let's go my IDs at index 0 dot, or pass here the length to get the length. I have 9 different tokens, 9 different segments that this word is being splitted into. As you can see, these are the IDs, and we can loop through it as we saw before for each token ID in my IDs at index 0. Then go ahead and print the tokenizer.decode, and then pass into here my token underscore ID. So we have FL is a single token, OC, so floxino-synhelibification, as you can see, which is a word that indicates nothing. Then let's move on to another section, which is how to generate. Now we saw how to tokenize the words, we saw the IDs. Now what if I wanted to generate, to use GPT-2 and actually generate using GPT-2? Well, we have to import another class. So let's go from transformers, import auto model for causal LM. So we have a class, we have a nice class called auto model for causal language model. So this is a real causal language model. Let's import it. Then let's instantiate a new object. Let's call it GPT-2 equals, so my nice GPT-2 model equals auto model for causal LM. I like that class name. Then let's pass into here GPT-2. Run that. As you can see, we have to call the method from pretrained. So we have to go from underscore pretrained and then pass into here GPT-2. So do not forget, you have to call the method from pretrained always when you use a class from Hugging Face. Now as you can see, we have a warning. Don't worry about this warning. It just warns you that detected node written. No worries. As you can see, now we have successfully downloaded the model GPT-2. Okay, let's go ahead and see the architecture. So what is the architecture looks like of GPT-2? If we type here the name, just the name, GPT-2, and run that, you can see we have the real architecture here. So this is the architecture. First we have embedding layer, then we have another embedding layer. I think this is for converting IDs into vectors, and this is for adding the positional encoding. We have drop out, then we pass it to the GPT-2 block, and we duplicate this block 12 times. Inside this block we have layer normalization layer to normalize the inputs. We have GPT-2 attention, we have conv layer, conv, we have drop out, then we have convolution. So this convolution is the attention. They implement the attention via a convolution layer. Okay, so feel free to explore this architecture on your own, but now let's dive in and use this architecture, use this really clever architecture to generate. So the first thing we need to build a sentence by going sentence equals, and let's use a sentence that has a tendency for ChatGPT to complete it. So if you say that I like machine learning, then we ask GPT to complete, then GPT will complete onto this sentence. Okay, then let's go ahead. So I like to machine learning too, for example, to do something or to be able to do something. Let's figure out what GPT will generate as a next token prediction. So let's go ahead and use GPT-2. As you can see, we have GPT-2, then pass into here this sentence. Just all we have to do is pass this sentence to the model GPT-2. Then let's run that. As you can see, here we have to, so the size, string has no size. Yeah, we have to tokenize this string. Yeah, we have forgotten an important step. Before we pass this sentence to the GPT, we have to tokenize it. So we have to get the IDs as we did before. So here we have token underscore IDs equals tokenizer, then pass my sentence. Then this tokenizer will work on the sentence and then return underscore tenses equals PT, PyTorch, and then get the input underscore IDs. Then we have here token underscore IDs. So these IDs now has the capability to be passed to a GPT model. So don't pass the string straight away to the GPT model. You have to tokenize it. Why we explained this tokenizer before? Because we need to tokenize any string before passing this string or this prompt to the GPT model. So this is a prompt. We tokenize it, we process it. So this is a data processing technique. Then after we process it, we could then pass these to a GPT model by going GPT-2 and then pass token underscore IDs. Hooray! Now we have here the output of GPT-2. Here you can see we have logits. Let's access the logits. .logits. Now, how many vectors do we have? The same number as the word here, as the words. So we have 1, 2, 3, 4, 5. Here we have 1, 2, 3, 4, 5. So the same number of words you have here, the resulted logits will have the same length as the number of words you have. So we have 5 words, and also we have here 5 corresponding vectors. Okay, I care mostly in the last vector. So let's get at index 0, comma, -1. So because my vector of interest is the last vector. So let's tap into that and get it. And now we have it. Now let's store that inside a variable called outputs. Outputs. Okay. After that, let's show it. Outputs. Then let's call the function argmax. The argmax function. It will give me the index at which the highest probability exists. Okay, so let's pass this to the tokenizer.decode to decode it. So this is a token ID. We pass it as we learned before. We pass it to what? To the decode function, and then it decodes it. B. Now, I like machine learning too. Let's put here B. Able to predict the, then we put this to predict the future. As you can see, we have the word future. Okay, then we have a dot. So as you saw, we predicted the next token using a GPT model. Here we have logits. Okay, then we got the argmax. So give me the position. So returns, this function basically returns the position at which the highest probability exists. So GPT model generates probabilities. Then we decode it, and then we generate. Okay, let's take another example. For example, the sentence I learn machine learning to enhance. Then let's ask GPT to generate the following words, the following tokens, by passing this sentence to the tokenizer first to do data pre-processing. So we have token IDs equals tokenizer, my little tokenizer, and then pass in here the sentence, comma, return underscore tenses. We have to specify it as PT, short for PyTorch, dot input underscore IDs. Then let me scroll down here to see the output. Then let's pass these token IDs to the GPT model by going outputs equals GPT2, and then pass in token underscore IDs, then get the logits, tap into the logits, and index 0, -1 to get the last token, to get the logits of the last token, the last word, for example, enhance. And then we have tokenizer.decode, and then pass into here the outputs, but please give me or return the argmax, the position at which the highest probability exists. Run that. We have here to enhance hour. So you can see here GPT-2 now is predicting the next token as hour. So let's put in here hour to enhance hour. Understanding. So GPT now is predicting the word understanding as the next token. Understanding of, so you can see, of the world around. Let's inject that word to around us. Then we have a full stop. So you can see this is the way that GPT is running, the way GPT works, the way GPT operates. It predicts the next token. So it chooses the highest probability of the token that it thinks or it believes that this word should be the next word. Okay, so this is another example. Now, what are the sampling strategies? Well, we have many sampling strategies, the ways you can extract the token to be selected as the next token, to be chosen as the next token. First, we have a function inside Torch called topk. So let's use that function by going. Let's first use our sentence. For example, sentence equals I learn machine learning to enhance the same sentence, and then let's tokenize it using the tokenizer by going token underscore IDs equals tokenizer, and then pass into here the sentence, comma, return underscore tensors equals pt PyTorch dot input underscore IDs. Input underscore IDs. Then let's pass these IDs to the GPT-2 model by going outputs equals GPT-2, pass into here the token IDs. So remember, you have to pre-process your sentence by passing it to the tokenizer. Then let's get the logits at index 0, comma -1, and then at the last tokenizer.decode, and then pass here outputs.argmax. Here we have the outputs.argmax. Let's read the error. Pre-trained our unexpected keyword argument. Yeah, we have a typo in the return underscore tensors parameter. So we have our. Now let's apply the torch.topk by passing the logits into the topk function. So you can see, let's get here the outputs final underscore logits equals torch.topk, and then pass into here the logits, the outputs, and then comma 10. So we need to choose the first top 10 logits by passing the outputs to the torch.topk. And remember, we have to import the library torch by going into here, import torch. Run that again, and now we are able to use that function. Now let's first visualize those final logits. As you can see here, we have a tensor, a nice tensor with 10 logits. Okay, so we have -100, -100,4, and so on. What if we limit this to 1? Well, we have then just one logit. Okay, so this is the way of topk. Topk is a strategy of sampling, or it's a sampling strategy that selects the most top k highest probabilities from the token pool, and then we limit it to a specified k number. For example, 7. Then we have here 7 tokens or 7 logits. We just have 7 logits. If we make it here, for example, 30, then we have 30 logits. If we limit it to 3, then we have just 3 logits. Okay, as you can see, this is the way of operating with topk. Now let's decode them by going for index. So for each index, now let's visualize what are these tokens, what are these chosen tokens, by doing a for loop. So for index in top 10, which is this final logits dot indices. So let's get the indices. Do the following: print tokenizer. So as we saw before, tokenizer dot use the function decode and then pass in the index. So all we're doing here is we are looping through the final logits dot indices. Then we are storing that index step by step into the index variable, then pass that variable to the decode function. Run that. Nice. Now we have our, the, my. So these are the top most tokens that the model thinks that this is our token, is the most high, is the highest probability. The second highest probability is the third highest probability is my. So to enhance, this could be to enhance our, or this could be to enhance the world, for example, or this could be to enhance my understanding or my skills. So let's put here my, then it will change as you go. We have work to enhance my work, or to enhance my own things, to enhance my own life, or to enhance my skills. As I told you, to enhance skills. So I predicted that. I didn't know that GPT will output the word skills. To enhance my skills, as you can see, and in comma. So let's choose, for example, and my, for example, life. So I learn machine learning to enhance my skills and my life. So this is the way that topk sampling strategy works. It limits the outputted logits or the outputted tokens to a specified number called k. Feel free to play around with the k value. It's very fun to play around with the k value. Let's change it to 7 to suggest 7 candidates. Then we have here 7 candidates. Let me get rid of this to trigger GPT to complete this sentence. So as you can see, I learned machine learning to enhance our, the, my, your, human, to enhance a, and, for example, let's choose human, to enhance human life, for example, human intelligence, or human performance, or human cognition, or behavior, learning, cognitive, understanding. So now we have 7 candidates here. Let's make the list bigger, and let's, for example, go crazy, 20. Now we have here 20 candidates inside the list. GPT now will choose one of these candidates, okay? So, and then if we choose, for example, performance, then it will also suggest another 20 logits or another 20 tokens. For example, let's here choose the word intelligence. Intelligence. Then we have, these are the candidates, and in, by, is, and you can see, but based on what the previous word is or was, the tokens here changes, or the tokens here change. They are varied depending what is the previous token was. Okay, let's take another example. Now we have the top k. The top k is a function, remember, inside Torch library. Let's search into here, Torch top k. Remember, always the documentation is the reference. Please feel free to read here in your own time, but you can see here top k returns the k largest elements of the given input tensor along a given dimension. So from this definition, we have a full summary of what this function does. Returns the k largest elements of the given input tensor along a given dimension. We give it the input tensor of logits, then it returns or gets back the k largest element of a given tensor at a given dimension. And then what you pass here is the input tensor. Just you provide it with input tensor, and keep in mind you have to provide the number of k, the k in top k. Let's go ahead and see what are the remaining sampling strategies are. Let's take a look at what are the different sampling strategies are. So we have many methods or methodologies to sample using different methods from the token pool. The first method is greedy _ decode. This function receives from me logits, and then let's put a nice documentation here. It returns or return token index with maximum probability. So all it does, this function, it returns the token index with maximum probability. So the index or the position at which the maximum probability exists and lives. So let's return torch.argmax and then pass into here the logits, comma, dimension equals -1. So keep in mind, -1. You have to provide here -1 as the last dimension. Then let's use this nice little function by going greedy _ decode and passing here my outputs, so the logits. Let's read the error. Torch has no attribute argmax. Yeah, I have a typo, a small typo in the function argmax. Classic error. Argmax. As you can see here, we have the tensor at index 13. So now it is indicating that at index 13, the maximum probability exists. The maximum probability lives. So I wonder what is this token. By going tokenizer.decode, let's decode it. Let's visualize it. It's a full stop. So now GPT is suggesting that the highest probability token should be full stop. Okay? If we change this sentence here, for example, to enhance human intelligence, to enhance, and then run that again. These are the candidate tokens. Let's do a greedy decode. Now we have our. As you can see, this is the greedy decode. It simply returns the token index that has a maximum probability value. Then we choose that token. Let's visualize another sampling strategy by going def top k sampling. So this is the strategy top k sampling. So we are limiting the top k, the tokens to the top k. Okay, top k sampling, and then let's pass into here logits, comma, and then you have to define the k. So how many tokens you want to keep, how many tokens you want to preserve. I want to preserve 50 tokens. The rest will be set to 0. The rest will be discarded. Then we have here a nice documentation. This method keeps only top k logits, normalize them into probabilities using the softmax function, then sample one token from the filtered distribution. Okay, so this is a nice little explanation of what this sampling strategy does. This sampling strategy, which is top k sampling, keeps only top k logits, normalizes them into probability using softmax function. Remember, logits are unnormalized scores. Then we pass them to softmax. The softmax takes care of them and normalizes them. What is the normalization process? It makes the sum of all those values add up to 1. And all those values will be limited between 0 and 1. So currently, if you see here, these are the logits. You can see that they are negative. They are unnormalized scores. But once we pass them to the softmax function, so let's pass this value to the softmax function by going torch.softmax, and remember, we have to specify dimension equals 0. Here we have normalized scores. So softmax now makes the sum of all these values add up to 1. This is the first point. The second point is that every single value is limited between 0 and 1. So we don't have negative values, and also we do not have values that are larger than 1. What is the proof? Well, if you try to take the sum of these values, I think sum like that, well, it is 1. So the sum, or the total summation of all these values is 1 because they are normalized. Unlike when we just have the final logits, which are unnormalized scores. They are ugly. You can see dot values. These values, when we take the sum of it, it is a unnormalized value. But once we pass them to a torch.softmax, this is a magical function. Softmax, the most important function in the world of machine learning. Then we specify dimension equals to 0. So here we have to pass into here dot values, okay? Then here, like that, dot values, okay? We have a sum of 1, okay? As you can see. So let's delve into the top case sampling by going values, comma, indices equals. So we are unpacking the returned values into a values variable and indices variable. And let's go torch.topk. Let's use the topk function from PyTorch library and pass in my logits, my magical logits, comma k. So the k will be defined by the parameter k equals 50. The second step is that props, we want to normalize them into probabilities. Hence, we wrote here normalize them into probability. So we have to pass these values into torch or f.softmax, and then pass into here values, my literal values, comma, dimension equals -1. And remember, we have to import at the top there the f function from the PyTorch by going import torch.nn as .functional. So import torch.nn.functional as f, like that, to be able to use this f in here, f.softmax, and then pass in my values and then specify dimension as -1. Then lastly, sampled equals torch.multinomial. Let's use the function multinomial, and then pass into here props, my probabilities, comma 1. At the end, return indices, and then indexing on the sampled, like that. So you can see sampled, we are passing this as an index to the indices variable. And then we have here multinomial function. Okay, run that. So now we have top k sampling. This function expects from me logits. Let's pass my outputs here. You can see it chooses the tensor at the index 674. If we pass this to a tokenizer .decode to visualize what is this token, what is this winning token, well, it is hour. So top K sampling now chooses the token hour. If we change slightly this function to enhance, for example, hour, it will give me another candidates or results into another candidate words. Let's run that again to see this is a dynamic function, dynamically changing. Run that to change our customer. So if you want to see this word into here, this is the chosen word, customer. Understanding, ability, work, lives. If you write into here customer, for example, to enhance our customer, then it will give me another candidate, you can see. And then if you choose this tokenizer.decode, run it again, experience. So one of the words here is experience, and I saw it here, experience. Okay, this is the way of operating using top K sampling. It just returns the top K logits and then samples from it. The third step is that we have the top probability sampling, top B sampling. And then it takes from me logits, comma, P equals 0.9. And let's write a little comment into here to separate the code and make it neat by going top P, which is called also nucleus sampling. So you can name it nucleus sampling or top B sampling. This is a nice method to sample from the token pool. It is called top P sampling, and it returns the smallest set of possible tokens whose cumulative probabilities add up to a specified threshold called P. So let's go and write a little documentation or documentary here by going star or sort tokens by probability, keep smallest number whose cumulative probability exceeds the threshold P. Then sample one token. So this is the explanation of what this top B sampling does. All it does, it sorts tokens by probability values. So the model, when it generates logits, it says, okay, I need to sort these tokens based on their probability values. Once the probability values are sorted from highest to lowest, keep smallest number whose cumulative probability exceeds the threshold P. And it's right here, threshold. Exceeds a threshold value P. This P is the hyperparameter that you need to specify. Here, I'm specifying it as 0.9, 90%. Then sample one token. So the first thing is we need to sorted underscore tokens or logits. Let's call it logits. It's better to call it logits, comma, sorted underscore indices equals torch.sort. Let's use the function so and then pass into here logits, that is passed to the function logits, pass it to the function sort it, and then descending. Do you want to sort it descending or ascending? Well, in my case, yes, I want to sort it in a descending order, in a descending manner. Then let's go ahead and sort it underscore probabilities. Let's normalize these logits by passing them to the softmax function. So all we need to do is pass the logits to a softmax function. Hence, the softmax will normalize these logits and make the addition, or when you sum these values, add up to 1 by going sorted underscore logits. Pass it to the function softmax, comma, dimension equals -1. So we have to specify here -1. Then we have to calculate the cumulative probabilities. So cumulative underscore props equals sorted underscore probabilities dot CumSum. So I like the name of this function, CumSum, meaning cumulative sum. So we have to CumSum, cumulative sum. and then pass dimension equals -1. So cum is short for cumulative summation. Okay, this is the cumulative probabilities. Then we need to mask tokens outside nucleus by giving mask. So a little masking here operation equals cumulative underscore probabilities that is larger than the p. So please go ahead, and if this cumulative probabilities exceeds p, is larger than p, then mask. So then we have here the variable sorted underscore logits, and then pass the mask equals float, and then pass into -infinity. So I want to explain this by going to the Polo Club here, because I have a little explanation. You can see we can go to Polo Club transformer explainer of Polo Club. You can see when we go to the top P probability here, we set the value as -infinity. If we choose top B, let the tool work. Now it tries to generate, as you can see, data visualization empowers users to visualize, and now the tool is trying to generate the next token. Now if you go to top P, and then probabilities, you can see here, if you choose the method top P and go to probabilities, it sets the rest of the, let's make the sampling here, for example, like that. So the rest are here 0%. As you can see, if you choose top K, then we choose the top K 5. So the K now is set to 5. Whereas if you set the sampling strategy as top P, it sets the rest as 0. And then it just chooses the smallest set of possible tokens whose cumulative probabilities add up to a specified threshold, for example 0.5. Okay, so the sum here, you can see the sum is 0.5, around that. And if you increase that, the sum takes more logits, takes more tokens, until it satisfies the cumulative probability that is you are specifying here. So the sum is 0.81, close to this value, 0.8. Okay, this is the idea behind this. The rest, we are setting them to what? To 0%. Here we are setting them to -infinity. At the end, let's sample from filtered logits by going filtered underscore probabilities equals f.softmax. So this function softmax, and then pass sorted underscore logits and specify the parameter and dimension equals -1. Then sampled equals torch dot multinomial function, and then pass into here the filtered probabilities. We can copy that, comma 1, and here remember to add a equal sign. So sampled equals torch dot multinomial, and then pass filtered probabilities, and then specify the dimension as 1. At the end, return token index in original vocabulary by going return, and then we have to specify the sampling here as sorted underscore indices, and then pass the index here as sampled. So this is the variable that we have to specify inside the square brackets, the variable sampled. And that is top P sampling. That's it, top P sampling. Now we have a function that uses the top P sampling strategy and samples from the token pool by keeping the smallest set of tokens or of logits whose cumulative probability value exceeds a threshold P value. After we wrote this function, top P sampling, let's try it together. So let's call this function top P sampling, and then pass into here my outputs, which are the normal logits. You can see my logits, pass it to the top P sampling function, and then specify the P as a threshold value equals 0.9. Let's run that. As you can see, it returns a tensor with the value 1920. 98. So I wonder what is the corresponding token value or the corresponding word value. By going token or tokenizer dot decode and then just pass in here the token ID, it will simply return the corresponding token or word that corresponds to this ID value. Experience. So now the top piece sampling shows us the experiences word. If we go ahead and, for example, to enhance our customer, to enhance something, let's try this together. You can see the sentences I learn, machine learning to enhance, then these are the candidates. Performance to enhance learning, to enhance user, to enhance data, social. Let's see what is the chosen word using the top piece sampling strategy to enhance human. So the top piece sampling thinks that the most word I believe should be the next token is the word human, which exists here, human. Okay, then if you write here human, it suggests another set of tokens to enhance human. You can see creativity, to enhance human health, judgment, knowledge, interaction, skills. Let's see here, what is the chosen token or word? Judgment. So as we saw, it chooses the word judgment. But the top K, let's compare this to the top K earlier here. It chooses to enhance performance. So the top K sampling thinks the most high probable value should be performance. But the top P sampling suggests that judgment. So you can see the difference here. Top P chooses empathy. Well, it's random. So when you run it multiple times, maybe it will change its sensitivity to another word. Okay, the top K sampling is also random. Okay, so you can see here when you run it again, it changes its decision. Now let's go ahead and go to the another sampling strategy, which is called temperature sampling. So this is one of my favorite strategies. It's called temperature sampling. The temperature is a hyperparameter that specifies it, and it changes and it redistributes the probability distribution. What it does is that the higher the temperature value is, the more creative and the more random the model outputs are. And the lower the temperature values are, the lower you set the temperature to, then the model will be deterministic. The model is deterministic, and it isn't creative. It just does what it thinks is more deterministic. So let's call it temperature underscore sampling, and then pass in my logits, comma, set the temperature value as a default value equals to 1.0. So feel free to play around with the temperature value. It's fun to change and adjust this value to different values, the temperature. Then let's write a nice little documentation here by going scale logits. So remember, temperature always scales logits. It returns a scaled version of the logits. Scale logits by temperature before sampling. So before it samples, it scales those logits. Then lower temperature, this is a note, lower temperature, keep in mind that lower temperature values leads to sharper, more deterministic distribution. So if you search here in Google, sharp probability distribution to see its image, go to images. This is a sharp distribution. So it's a sharp probability distribution. But if you search here flattened probability distribution, this is a flattened one. You can see here, you can see this. These are the different probabilities there. We have here a sharp probability distribution, and we have a flattened probability distribution. Okay, and this is also the image of a flattened probability distribution. Okay. The steps here are simple. We have to create a variable called scaled equals logits, and then divide the logits by the temperature value, and then we have probabilities props equals f dot softmax, and then pass into here the scaled variable, comma, specify the dimension as -1, okay, -1. So these are the settings or the steps. First, we divide the logits by a temperature value, this value. You specify it as 1, 0.5, 0.3. Then we take those scaled logits and pass it to the softmax function to normalize it, and then store this returned value into a variable called props. At the end, we have to go ahead and return torch.multinomial, and then pass probabilities props, comma 1. And that's it. We have a temperature sampling strategy. Let's try it together by going ahead and call this function sampling underscore or temperature underscore sampling, and then pass in my outputs, as you can see, and then let's specify the temperature value, temperature equals to, let's try first 1.0. So let's try to set the temperature as 1. So remember, when you divide anything by 1, it will be the same. So if you take the logits and divide it by 1, then it's the same, okay? Let's go ahead and run that. Nice. Now we have a tensor of 4,430. I wonder what is this corresponding token value or word value. Let's go tokenizer.decode, pass it to the decode function. Run that. It's performance. Okay, so let's go ahead and see the candidates here. These are the candidates. We have performance. Now, if we change the temperature value a little bit, for example, let's set the temperature to a lower value. For example, let's set it to 0.1. So now remember, lower temperature values leads to more sharper outputs, leads to more deterministic outputs, less creativity. Run that. Intelligence. So you can see now the model chooses the word intelligence as the next token. Why? Let's read the sentence again. I learn machine learning to enhance human intelligence. So it is less creative and it chooses the word intelligence. But if we increase the creativity rate of the model by going ahead and set the temperature value to, for example, 0.5, cognition. So you can see the model now is thinking in complex manifolds. It chooses the word cognition. You can see, go ahead here. This is the word that it chooses, cognition, okay? And if you increase the temperature further and further, 0.9, for example, physical. So the model now is random and choosing creative words, choosing very hot words. You can see here, I learn machine learning to enhance human physical. Let me write physical. For example, abilities or performance, health, functions, capabilities. Let's see what it chooses to enhance human physical function. Okay, and the temperature, I think you can increase further. 1 point, for example, 3. It chooses and. Okay, if you increase further to 1.5, it chooses enjoy. So the model now chooses the word enjoy as the next token that it thinks the most probable word. I learn machine learning to enhance human physical enjoy. Enjoy, okay, like that. Then we have several candidates here. It will choose one of them. Vulnerabilities at the temperature 1.5. So these are the different sampling strategies, okay? And then at the end we have the last sampling strategy, which is called random sampling. So this strategy isn't common. You will see it rare in the world of machine learning. You will not use it as common as the previous ones, but it's called random sampling. Random sampling. And then let's write the function define. Let's call it random. Let's name it random sampling. Then pass into here my logits. Then specify a little documentation here. So your future self or someone else comes here, he doesn't get confused what this function does. He has a little explanation what this function does. So if you come back later after 6 months, for example, or after 1 year, and you come back to these functions, well, I don't remember what this function does. No, you don't get to this situation. You have a explanation that tells you what this function does. This is the benefit of writing a documentation. Sample directly from softmax distribution without filtering. So it samples directly with softmax or from softmax distribution without any filtering strategy. Props equals torch, or f, let's use f dot softmax, and then pass into here logits, comma, dimension equals -1, then simply return torch dot multinomial, and then pass my probabilities, comma, 1. This, and that's it. Now you have a random sampling strategy. Let's run that. Let's call it together and see what happens. Random sampling, and then pass in my outputs here. As you can see, it returns a, you can see when I run that again, it changes its decision. So every time it chooses another token, it's random. So tokenizer dot decode. Let's decode it. Let's see what is the word meant of I meant. Let's change the sentence. I learn machine learning to enhance, so to trigger GPT to complete the sentence in a correct way, to enhance every day, to enhance my doctors, to enhance abilities, so it's a random sampling strategy. It's a random sampler. Sample directly from softmax distribution without filtering. What it does, we pass the logits to softmax function. It normalizes these logits. Then we pass these probabilities to a multinomial function and return that. And that's it. We have now a four methodologies to sample from the token pool. Let's try to create another sentence. For example, sentence equals the sentence, today I decided to go to the, and let's go ahead, inputs equals tokenizer. So let's tokenize this sentence. Remember, you have to pre-process this sentence before passing it to the GPT model by passing this sentence to the tokenizer, comma, return underscore tenses or return tenses equals pt, short for PyTorch. Then we have output equals GPT2, and then pass inputs here. So these are the input IDs. These are IDs. We pass them to the GPT2 model. And remember, you have to put two asterisks here to unpack it. Then logits equals output dot logits, and then pass 0, -1 to index to the last word. So at the end, let's print here, print f string, a little f string, and try to print the first method, the first methodology, which is greedy decode, as, and then inject the function tokenizer dot decode. So we need to decode to the corresponding token by passing the list greedy underscore decode. Call this nice function and pass into here my logits. Then the same idea, print f string. Let's name it here top k sampling. Then print the function or inject the function tokenizer dot decode, tokenizer. Make sure we read that right. Tokenizer dot decode, and then pass here the function top underscore k underscore sampling, and pass my logits into here, comma, specify the k. Feel free to change it to your own k. I will set it by default to 10. Then let's go ahead and print the third method, which is top p sampling. And the top p sampling, remember, it is called also the nucleus sampling. Let's go tokenizer dot decode, and then pass into here the function top underscore p underscore sampling, and then pass to here logits, comma, p. Specify the p as you would like, but in this case I would keep it simple and pass 0.9. The fourth methodology is, remember, the temperature. Then we have to pass into here the function tokenizer dot decode, and then pass into here the temperature temperature underscore sampling, and then pass into here logits, comma, and then specify the temperature with any value between 0 and 1. I will keep it here 0.7. Then at the last, we have the random sampling methodology, which is a simple tokenizer.decode, a simple sampling strategy, random underscore sampling, and then pass in my logits. And with that being said, we can run that again. So let's go ahead and 3, 2, 1, run it. And I'm excited to see that we have no typos, we have no errors. As you can see, greedy decode local. So the greedy decode chooses the word local. Top case sampling chooses doctor. Top piece sampling chooses lesson. Temperature chose nearest. And you can see random chose military. Let's change the sentence here. Today I decided to go to the local doctor lesson. Let's choose, for example, local. Then how this would change the outputs here. Run that. Here we can see the greedy chooses library. So today I decided to go to the local library. Top case chooses library. Top P library. Okay, library. And you can see they are all now unified. They chooses the word and here we have the greedy said read, and it's reasonable because I go to the library, then I would do what I would do there is reading. But the top K here says find. So let me go with find, and find, you can see find out. Yeah, because you find out. In English, we always put the word out after find. So it is reasonable. Then find out what. So the greedy says what. The top case sampling says the. Top P says what. So you can see that the greedy now is equal to the top P sampling strategy. Find out what was, what they, what was, let me say what was going. Okay, so you can see the top P here says in. What was in, for example, in there, or in my, for example, in my wallet. You can see now we have the word wallet as the top case sampling. The temperature says wallet. Also the temperature says wallet. Let me go ahead, and you can see now they are all saying that we need to put a dot here. Then if you run it again, they would say I. Okay, and as another example, quickly, sentence equals I am really happy because, you can see I, it, they. Let me say because I have, for example. Then you can see the temperature. I have gone. It chooses gone back. And if you change the temperature here, you can feel free to play around with that. Make it 0.1. It will say temperature 2. But if you make it here, for example, 1, really creative, it will say temperature in. I have gone back in time. You can see I am really happy because I have gone back in time. Okay, and feel free to change and adjust the sentence, and also change the K, the P, the temperature, and play around with that. And always remember, you have this nice tool to visualize and learn about top P, top K sampling, and also the temperature here. If you want to play around with the temperature, you can see. Let me write here the next sentence. I like machine learning because. Then try to generate. Now it will be fast. You can see the tool is already loaded. Then we have here temperature. Now if we make the temperature 0.1, you can see the distribution here is really sharp. It's really just pointing to one token. The rest are 0. But once you increase the temperature, it distributes that value. So it doesn't make the distribution goes towards one token, but rather it makes the distribution more flatter. So if you increase it, it gives some proportions to the next and it chooses other tokens. So it gives some possibility to choose other tokens. Okay, rather than just centering all the mind towards one token, we give some opportunity to other tokens to show up. As you can see, the sampling here methodology is K. Let me increase the K so you can see the K here is 5. So just you want to keep 5 tokens. The rest are discarded. But let me make it, for example, 17. Now you can see, or for example, 6. You can see 1, 2, 3, 4, 5, 6. If we increase that again, 10. Now we have 10 tokens. The rest are discarded. We just keep 10. And also if we go to the top P, now you don't have here K, but rather you have a P, which is the cumulative sum, the cumulative probability, and it chooses the smallest possible set of tokens whose cumulative probabilities exceeds a threshold P. For example, let me make the threshold 0.2, then these are all makes up to 0.2. And if we go ahead and increase that, you can see it chooses different tokens. Let me decrease the temperature a little bit. 0.5, you can see here, when we make the top P 0.3, it chooses 100% I. The rest are discarded. If we increase that again, it will choose we here, because we, and if you go, for example, like that, increase it, it will redistribute the probability distribution. So these are different sampling strategies that are employed to manipulate the distribution or the probability distribution of the token pools and changes the decision of models like GPT and any other model that is considered a generative model. So keep in mind, you can feel free to play around with these values in our collab. So now we have finished about GPT and generation, and let's dive into another topic within the transformers library. Now I have a little code that visualizes the probability confidence rates associated with the corresponding tokens. So to write this for loop, first we need to construct a sentence, and then set this sentence variable to any sentence you would like. For example, I would say I learn machine learning to enhance. Then I will ask GPT to complete that. Now let's go ahead and pass this sentence to the tokenizer by going token IDs equals tokenizer dot, and then pass into here sentence, comma, return underscore tenses equals pt pytorch dot input underscore IDs. Now if you visualize this token underscore IDs, you will see that we have here IDs, just a normal tensor, a simple tensor with these IDs 40, 2000, and it all. Now let's pass these IDs to the GPT by going outputs equals GPT2, and then pass in my token underscore IDs. The GPT here will return, if we get this output as outputs, you will see this whole output, which consists of logits plus also dynamic layer, and so on. We need just to fetch the logits, just to retrieve the logits. So let's go ahead and tab into dot logits. So we need just to fetch the logits. If you print that, you can see now we just have the logits, the raw unnormalized scores that the model outputs. So these are raw values, raw, okay? We can see here raw unnormalized scores or values. Now let's go ahead and go to outputs, override that again, equals torch.softmax, and then pass the outputs here. But keep in mind, you have to index and get the last item. So if you do that again, like that, outputs, and visualize it, 0, -1, well, 0 will get rid of this outer bracket. So here, if you go at index 0, it gives me here these brackets. Then if you go comma -1, it will fetch the last token, the last word. So as we said, we have 1, 2, 3, 4, 5, 6. We have 6 words. I learn machine learning to enhance. So we have 6 words here. We have 6 vectors. 1, 2, 3, 4, 5, 6. Inside every single vector, how many values do we have? We have 50,257 logits or values. Why? Because when GPT takes this sentence, it rolls out on it and then predicts 50,000 tokens or 50,000 probabilities or logits for every single word. Okay, and then we need to access the last token, the last word, which is, if you go ahead outputs, we have to put S here. You can see we have the last token, the last item. Now we need to call the function, as you can see, torch.softmax on this. Now note with me what would happen to these values. And then we have to pass here dimension equals -1. 3, 2, 1. Note that these are negative values. what would happen to it now? They are converted into what? Into positive values. Some values are really small. You can see they are multiplied by the Euler number raised to the power of -6, and some values are really high. The most high value you can get it by going to argmax.argmax, okay, and then call the argmax function here. You can see the most high value is at the index 674, but I don't want to get this. I need to store all of these values inside the outputs variable and overwrite on it, okay. After that, let's go ahead and get the top 10 equals torch.topk. This function is a really helpful function inside torch. It's a really helpful function. Let's pass into here outputs, comma, specify the k as 10, since I named the variable top 10. If you visualize top 10, we have a nice top 10 values here. So that's really cool. Let's go ahead now and do a for loop for index, comma, value in zip, and then pass into here top 10 dot indices, comma, top 10 dot values. Let's go ahead and print into here tokenizer.decode, and then pass into here the index dash, put a curly brackets here, inject it values, and then get there just one number after the dot, okay, and then put the percent sign. Now let's go ahead and run that. 3, 2, 1. Values isn't defined, so we have to, we need to call this variable value, just one value. So here, note we have values, but here value is referring to this variable. So we unpack this zip object into index. So the indices value gets returned to index, and the values value gets returned to value. Then we loop, and then print those outputs. And then hooray! Now we have the tokens associated with their confidence rates. So GPT thinks that the most probable word is hour. So if we read the sentence again, I learn machine learning to enhance hour. Hour is being inserted 11.5%. If we choose now to enhance, for example, hour, understanding is 4.3%, ability is 3.9%. Let's go to enhance our understanding. Feel free to choose any word from this list. You can actually choose any word. Understanding. Then we have, you can see here, of 91%. So GPT thinks that 91.8% this word of should be the next token. Then if we go the how, you can see how human. We can choose now of them, for example, the world, human, brain. So we can say to enhance our understanding of the brain, for example. Then we can see we have here comma and comma in. Let's choose, for example, in the order, in ways, in general, and so on and so forth. So here we have the tokens associated with their confidence rates. GPT is assigning probabilities or probability distribution to these tokens, okay? And this is how you can visualize and print what is the confidence rate for every single token. So not only choosing the next token using top K and top B, but also visualizing the confidence rates. And this is a really cool feature you can have in the Python library of the zip function, and also how to print the index, passing it to the decode function, and get the value. Let's dive into the second task of NLP, natural language processing, which is the task of sentiment analysis. So let's name this as a title, sentiment analysis. Now we need a dataset. We need a dataset to be able to classify the text as positive or negative or even neutral. Let's go to Hugging Face and then go to their website and search into here, go to datasets, and let's go to the filter by name and search for IMDb by Stanford NLP. Then straight away go to use this dataset, and then you can see we have a library called datasets. Click on it, then let's copy this code. You can see here this code is simple. From datasets import load underscore dataset. Then we use this function and pass into here the name, the username of the account, Stanford NLP/IMDb. Here you can see we have a nice visual of the samples. You can see here we have some text and it's labeled negative, so is short for negative, and then we have positive. You can see we can scroll down and see all the samples. Then we have many pages, page 1, page 2. Feel free to explore this dataset in your own time. Keep in mind, you have to become one with the data in order to be able to model it. Okay, then we have here, if you scroll down, you can see we have, if you go to this IMDb again, we have here also a way how to use this dataset using code. So let's go to our Colab and paste this code, run it away. Now we have here readme.md, which is a file, readme.markdown. You can see plain text. We have this data. The data now is being loaded and downloaded. So all we've done is we've copied it from Hugging Face and straight away paste it into the Google Colab. Now, after this code finishes loading, let's go ahead and get the type of this dataset, which is DS. You can see now it's loading. Now it's loaded successfully. Now let's go ahead and type this dataset. Now, since my variable name here is DS, I'm going to use DS, but you can feel free to name it whatever you want. So here the type of this dataset is datasets.datasetdictionary.datasetdict. So the type of this dataset is what? Is dataset dictionary. Let's go ahead and go here, dataset, and then let's access this dataset as DS. You can see we have training dataset, we have testing, then we have unsupervised. So we have the training dataset, test dataset, and unsupervised. The trained dataset is a dataset object or a dataset class. Then we have features, text. Every single text is associated with a label, positive, negative, neutral, and the number of rows here is 25,000. And for the test dataset, here we have features, we have text column, label column, or text key, and the label key. Then we have num rows as 25,000. Okay. Let's go ahead and now explore this dataset in your own in our own way. The first thing is we need to go DS and then choose the key train. You can see now we are indexing and fetching the key train from this DS variable. You can see we have a dataset class. Inside it we have features and we have num rows. Let's go ahead and try to pass this into our import pandas as PD. And then let's go ahead and pass this DS train into a pandas column. So dataset and then choose train column or train key dot to underscore pandas. So now we are converting the dataset into a pandas data frame. You can see we have a nice little data frame text. I rented I am curious yellow from my video. This is the text. Then label is 0, negative. So the label is 0 or 1. 0 for negative, 1 for positive. Now let's go ahead and try to index on this data frame by going my dataset frame data frame equals ds dot to underscore pandas, and then let's fetch the key train by this way. Then we can go my dataset underscore data frame and then access the column text. You can see we have the column text. Okay, and if you want to know how many samples do we have, we can go ahead and fetch the length of my dataset data frame and then choose the key, the column text. We can get the length as 25,000. Now we need a model to classify the sentiment. So from transformers, import the pipeline function, pipeline. Then let's go ahead and import that. The second step is we need a model. So let's go pipe equals, or you can name it also classifier. Let's use classifier equals pipeline, and then pass into here the task you want to conduct. In this case is sentiment analysis. Also you can write into here text classification like that, text classification. It will be the same, but in this case I want to use the task sentiment-analysis. Then let's go ahead and you can specify the model here. Feel free to choose any model. You can go to models and choose whatever model that is used for sentiment analysis. We can go to tasks, NLB, and then go to text classification. It's the same as sentiment analysis. Then you can choose any model. if you go to sort the models here and choose most downloads, you will see that it will be Stable BERT, which is the default. So let's keep the default here and straight away run this as this, like this. You can see now the model is being downloaded. Model.saveTenses tokenizer._config.json, and we have vocabulary.text device set to CPU. So now the model is loaded. Let's go ahead and use this model on our text. So we can go classifier and then pass into here my text as this day is great. The classifier will work and it will label it as positive. So you can see now we have a positive label for this string. And the score, the confidence rate of the model is 99%. So let's go ahead and also do another example, classifier, and then pass here the string. This day is terrible, and I am so sad. And the model will classify it as negative. Hooray! We have label negative, and the score is 99%. So now you have a ready classifier that is performing really well, pretty well. You can see the performance rate here is really high. The model is really confident. Now let's use it on our text dataset, which is IMDb from Stanford NLB. Let's create a function called def score. This function takes from me a text, a sample text. You can name it review text as review underscore text. Then this function will return the classifier, and this classifier will work on what? On the review text, but we need to specify the limit here as to 500 because this BERT, the maximum length is 512. Then we can go at index 0, then we can fetch the label. We need just the label. So here, the same idea. You have a list. Inside this is we have a dictionary. What if you want to just return the label? Well, that's easy. Index at index 0, it will fetch only the dictionary. Then after that we have a dictionary. Now how to grab the label? We can go label and it will step into that label as negative. Now here we need to pass this function by giving dataset or my dataset underscore data frame, and then choose the column text, or let's name a new column called model underscore prediction. The model prediction equals the dataset or my dataset underscore data frame, and then choose the column text dot apply. We have to apply the function score. So here all we are doing is we are applying this little function score. This is a really helpful function. We are applying it on our text column and assigning the value of this function, the return value, which is the label, whether it was negative or positive. We are assigning it to a new column called model prediction. So let's straight away go ahead and run that. Now keep in mind it might take a little bit of time because we have so many samples. As we saw, we have 25 rows, so it might take a little bit of time. We have to wait until it generates those predictions. Now in the meantime, we can go to Stable BERT, to the paper, Stable BERT paper. We have here Stable BERT. You can see a distilled version of BERT, smaller, faster, cheaper, and lighter. As transfer learning from large-scale pre-trained models becomes more prevalent in NLP, operating these large models on the edge. So keep in mind this Stable BERT is really a small model, but it's faster, smaller, cheaper, and lighter. So it has a state-of-the-art performance, but also it is pretty fast. So it can operate on the edge. Okay. Under constrained computational training or inference budget remains challenging. In this way, we propose a method to pre-train a smaller general-purpose language representation model called Stable BERT, which can then be fine-tuned with good performance on a wide range of tasks, like its larger counterparts. And we saw that it is performing already pretty well. While most prior work investigated the use of distillation for building task-specific models, we leverage knowledge distillation. So distillation is one of the brilliant ideas in the world of deep learning. It was proposed by Jeffrey Hinton. Distillation is you train a student model to behave like a teacher model. So rather than using a large model, a pretty massive model, you train a student model that tries to mimic the output layer of a teacher model during the pre-training phase and showed that it's possible to reduce the size of a BERT model by 40%. So they reduced the size of a BERT model, of the original BERT model, by 40%, while retaining 97% of its language understanding capabilities and being 60% faster. To leverage the inductive biases learned by larger models during pre-training, we introduced a triple loss combining language modeling, distillation, and cosine distance losses. Our smaller, faster, and lighter model is cheaper to pre-train and we demonstrate its capabilities for on-device computations in a proof of concept experiment and a comparative on-device study. So, by the way, feel free to read through this paper. You have this paper here. You can see here this visualization. They are comparing distal BERT of Hugging Face by other models, like we have GPT, we have here BERT Large, Transformer Elmo, GPT-2, we have XLM by Facebook or Meta, and we have here NVIDIA. So you can see distal BERT is a really fast model and really performing well. Okay, and you can see here also they present their work here. In the present work, the student distal BERT has the same general architecture as BERT. The token type embeddings and the pooler are removed while the number of layers is reduced by a factor of 2, and you can read this in your own time. But now let's get back to our collab. You can see it's still running. Now the loading has finished. We have applied the function score on the column text successfully, and as you can see here, we have now a column called model prediction ready to go. Let's now go ahead and my dataset underscore data frame and show this data frame. Now, hooray, we have a column called model prediction that shows negative, 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 positive, shows the labels that the model has made on our text. So let's compare the model predictions to the ground truth labels by going choose the model prediction. We can choose both columns, label, comma, model underscore prediction. Now you can see here we have label and we have model prediction. Now let's show the first 20 rows. As you can see here, we have label 0. The model has got it right as negative. 0, negative, 0, negative. Then we have here 0. The model has made it wrong. The model get it wrong and classified positive. But in fact, the label is 0. But the model prediction here is positive. And here we have 0, negative, 0, negative, negative. And feel free to compare the labels to the ground truth, or compare the model prediction to the ground truth label in your own time. But here, as you can see, we have this data frame, my dataset underscore data frame, and it has 2 columns. It has the label and model prediction. And here we have the text. For example, if you show the first row by going .I lock 0, here we have 0, 1. If you go 0, here we have the text. Let's get the text. This is the text of the first sample. We can print it to see what it looks like. I rented I am curious yellow from my video store because of all the blah 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 blah. Now, what if we pass this text? So this is a review. Let's pass it to my model by going classifier and then pass into here the review. You can see the review. Yeah, we need to get rid of this print function. Now we pass in the review to the classifier, and the classifier now took care of it and predicted the label as positive. The score is 78%. Now to get the label, we can go label, we can go at index 0 to fetch or retrieve this dictionary. Then we can tap into the column or the key label. It is positive. Okay. The ground truth for it, if you go to my dataset underscore data frame, this is the data frame. Then we can choose at index 0. We get the sample 0 .I lock. Here we have the text sample, the first text sample. The label is what? 0. And the model has predicted that it is positive. Okay, so you can see the model is getting some are right and some are wrong. Okay, but here in this data frame, we have made the predictions successfully. Now let's go to the next step where we import another model. So if you go to Hugging Face, here in the tab models, if you search for a model called FinBERT, now I was exploring the models for sentiment analysis, and I found this model which is called FinBERT for financial BERT. You can see FinBERT is a pre-trained NLP model to analyze sentiment of financial text. It's built by further training of the BERT language model in the finance domain. So the author of this model took BERT architecture, the same BERT architecture, but fine-tuned BERT in the finance domain, used some financial documents and fine-tuned it on this financial documents and financial documents using a large financial corpus, and thereby fine-tuning it for financial sentiment classification. You can see now we are in the field or in the task sentiment analysis. Let's go ahead and use this model for the transformers. Here we have the higher level helper, and we have the specified class and functions. Let's use the higher level helper. So to use this, we can go here, then we can say from transformers import pipeline, then we can go FinBERT equals pipeline, and then pass into here the name of the task, as we said, sentiment dash analysis. Then we can specify the model here as the name of the user slash the name of the model. So here we can copy this and paste it over here, and that's it. Now it's loading FinBERT, a BERT model architecture fine-tuned on a very massive corpora in the financial domain, and it's capable of classifying the financial documents. So let's go ahead and try some to predict on some financial sentences. By going here, you can see for we have the sentence equals the company reported a strong increase in quarterly. So you can quarterly revenue, comma, exceeding market expectations. So this is a sentence, and you can see it's clearly, its meaning is indicating that it's a positive financial sentiment analysis. So the company reported a strong increase in quarterly revenue exceeding market expectations. If you pass this sentence to FinBERT, so now use FinBERT model, and then pass my sentence, and then go ahead, FinBERT will classify it, the label as positive. Because why? Because this sentence is referring to a positive indication or positive intent. So the FinBERT is using its fine-tuned parameters to classify this sentence, and it got it right. This is a positive sentence. The score is 95%. And the paper for FinBERT is this paper. You can see FinBERT by Dogo Arashi. Financial sentiment analysis is a challenging task due to the specialized language and lack of available data in that domain. General purpose models are not effective enough because of the specialized language used in the financial context. We hypothesize that pre-trained language models can help with this problem because they require fewer labeled examples, and you can feel free to read that in your own time. But the most important idea, we introduce FinBERT, a language model based on BERT, to tackle NLP tasks in the financial domain, and you can find it here on Hugging Face. Let's try another example with a negative sentence by going sentence equals shares fell after the firm reported lower than expected. So you can see the fine-tuned language here, lower than expected. So we need a fine-tuned model trained on massive corpus of financial documents to be able to work and deal with these kind of very particular terminology, and then earnings. So here, shares fell after the firm reported lower than expected earnings. Let's pass this to my FinBERT, and then pass my sentence. Then go ahead. You can see the label is negative. Because why? Shares fell after the firm reported lower than expected earnings. and the score here is 97%. The model is confident by 97% that this sentence belongs to the negative class or the negative group. And keep in mind, you can also deal with batch, deal with several sentences in one time by going sentences equals a list. Then let's pass here several sentences. The first sentence is strong consumer demand drove record sales across all regions, comma. The next sentence is supply chain disruptions severely affected production output. And let's pass this list into our BERT classifier, financial BERT. Pass my sentences, and 3, 2, 1. You can see now we have two different predictions. Because why? Because we have provided the model with two different sentences. Hence, the model took those sentences and made the prediction for every single sentence on its own. The first is positive and the second is negative. With that being said, let's move on to a third task, which is in this case named entity recognition. So this task is one of the most common tasks in the world of NLP, natural language processing, which is the field of detecting and identifying the named entity recognition. For example, locations, countries, organizations, and the names of persons. Let's go ahead and create our sentence. So sentence equals Apple. So Apple is a company announced. Then let's go ahead and record earnings in the United States. Here we have a name for a location on Monday. So here we have a sentence that says Apple announced record earnings in the United States on Monday. Let's pass this to a named entity recognition model by going NER. So NER, named entity recognition, equals pipeline. So we can use the same function and then pass into here NER. Now, of course, you can pass here a model. So feel free to go into Hugging Face, go to models, and then scroll down to tasks, and you can choose from NLP the class of or the field of named entity recognition. But here we can see, we can explore what is the default model is. So let's just explore, go ahead and run this straight away and see and detect what is the default model. So the default model here is what is called DBMDZ/BERT large case fine-tuned. So if you take this model and search on it on Hugging Face, you can definitely find it by going scroll up, filter by name, and there we have it, DBMDZ. And you can see this is the model, DBMDZ/BERT large, and it's used for token classification. It's built upon the library transformers, PyTorch, TensorFlow, JAX, Rust, and so on. And you can see downloads last month is 1,700,000 and about it. And you can see you can go ahead and use this model using transformers, and feel free to pass that model alongside with the task specified as token classification. But now let's go ahead and use this model straight away by passing my sentence to the NER tag pipe by going named entity recognition and then just pass in my sentence. And let's the magic trigger. Here you have a list of dictionaries. You can see the first dictionary. Let me just show up the sentence here to compare and see. We have Apple. So the first thing is we have org. Org is short for organization, company. So here we have Apple. Apple has been detected as an organization. That's perfect. Then we have location, which is United. Then we have another location, which is states. So you can see United States is a location, is a country. Then if you go ahead and try another sentence, here you can see location is states. We can go and try another sentence together. So sentence equals, for example, I worked at Facebook after graduating from Harvard. Then we can pass this sentence to my NER sentence. You can see here we have organization, Facebook, and I have another organization as Harvard. And you can see if we pass here, for example, I, for example, live in, for example, UK. Here we have also a location, I think, called UK. So UK, yeah, UK, United Kingdom is a location. Okay, I live in UK, worked at Facebook after graduating from Harvard, and it detected that so beautifully and in pretty well performance. Now let's move on to another task. It's called question answering. Question answering. And this field is also one of the most important fields in the world of NLP, where you provide the model with some context, some text, and the model tries to find some answers in that text. And when you ask it a question, it will answer that question from the text. So let's go ahead and Q&A bot. Let's call it question answering bot equals pipeline, and then pass into here the task. So remember, you can pass here sentiment dash analysis. You can pass into here text dash classification. You can pass here named entity recognition, NER. And also you can pass into here the task as question answering. So question dash answering. Let's write a answering and see what is the default model that it will provide us with. Let's write here R and then Ctrl Enter. You can see the default model here is also distilled BERT / distilled BERT base case distilled dash squad. And now it downloaded the model successfully. Let's go ahead and use this model. So we need the text context equals some context, then it can find some answers. So let's copy this context, for example, and pass it into here. Context. Let's make that pretty well visualized by going ahead and when the word is reaching this line, it should cut off and go down. The line should cut off and go down. Like that. So now we have context, okay? Let's go ahead and run that. Then let's provide this model, which is QA-bot, underscore bot. Let's provide context equals context. And also we have to provide into here some question by going question equals question. And we have also to provide, we have to create a question variable equals, for example, here we have financial sentiment analysis is a challenging task. Let's ask it, what is financial sentiment analysis? Like that. This is my question. Let me pass my question, the question and the context as this. 3, 2, 1. Let's ask it. Now it worked, and you can see the score is 30%. Answer is a challenging task. So here, if you go up, you can remember that financial sentiment analysis is a challenging task, and it responded with that, and it told us that it is a challenging task. So this idea is mimicking the idea of RAG, retrieval augmented generation. Okay. Also, we can ask another question. We can ask question as, for example, let's read here. We can see general purpose models are not effective enough because of the specialized. Let's ask why generative models are not effective, and then pass this question to my model by going Q question answering underscore bot question equals question, comma context equals context. Then let's go ahead and here we have question. Yeah. Let's run that. You can see we have score 41% answer, specialized language used in a financial \n context. And you can see we have here \n. If you want to show it in a pretty formatted way, we can sort this output into a variable called result, for example. then we can show this result. Then we can index on this dictionary and access the answer key, answer. Then we can print it. You can see print. So specialized language model or specialized language used in financial \n, then we have context. For example, let's go ahead and here find some. We introduced BERT. Let's ask it, what is BERT? What is BERT? BERT. A language model based on BERT. You can see I asked it, what is BERT? It said a language model based on BERT, and that's it. Feel free to grab or fetch another kind of context or text and ask this model whatever you want. But keep in mind, this model is the default model, which is this still BERT. And remember, there are some beta models, some very powerful models out there in the Hugging Face platform. You can feel free and go ahead and explore them. Maybe they are better than this BERT. You can go ahead and specify the model name as you would like and use it, okay? But now let's go ahead and move on to the last task, which is machine translation. So the task of translating from one language into another, converting from one language into another language. So the first thing is we need to define a variable called translate. I will name it translator equals pipeline, and then pass into here translation underscore en underscore to underscore French. So we have the task of translating from English to French. Let's go ahead and run that. Here you can see we are downloading now the translator. Here we have Google T5. So the default model is Google-T5, which is also, if you search here, T5 paper. This is the paper behind the T5 model, which is the default model at Hugging Face for translating, exploring the limits of transfer learning with a unified text-to-text transformer by Colin Raphael and et al. So here you can see they leverage the whole transformer architecture. Unlike BERT, which is encoder only, and unlike GPT, which is decoder only, T5 is using both parts, encoder and decoder, okay? And they performed very well on the translation task. Okay, so feel free to read that in your own time. Let's go ahead now and use this model by going code and then creating a text or sentence. So translate. So all you need to do is just call your translator, your variable translator, and then pass in some word. For example, hello. You know hello in French is bonjour. So let's go ahead and translator hello, it's bonjour. And if we also translate translator and then pass into here thanks, it will say merci. You can see merci. And feel free to pass in whatever text you want and it will translate. So you can see how easy it is to translate, how easy it is to find named entity recognition in text, how easy it is to grab some context and ask some questions about it without even training these models, without caring about how to build these models, what are these architectures. So Hugging Face is an open source platform that hosts millions of models and you can access them freely. So last thing, let's try some sentence here. For example, sentence, what is your name? What is your name? And try to translate it to French. Translator, pass here my sentence. Go ahead. Qual est vector or veteran nom? Okay, so this is how you can translate, and feel free to access the dictionary. You can go at index 0, gives you a dictionary, then we can access the key translation underscore text, and then we have it. Okay, so the last thing, we can go to Hugging Face like that, go to models. Here we have tasks, go to tasks, go to NLB, scroll down, NLB. Here we have the task of machine translation. Here we have a plethora of models that are all about you can see the first model is T5, Google T5, which we used before. We have Facebook NLLB, so no language left behind. Okay, 200 languages distilled. Then we have Google MAD LAD, and feel free to use whatever you want. If you choose this model, use this model, transformers. Then we can copy this model. So this is how easy it is to grab a model from Hugging Face. Then we can just run it. So this is Facebook NLLB model, 200 distilled 600M. So I think 600M is referring to 600 million parameters. And here we have the model card. You can also read here. This is the model card of NLLB. Here are the metrics. You can read the metrics. There are some intended use. So how we want to use the model. We have some training data, ethical considerations, and this is the model card. And also you can see here we have it's built upon PyTorch, transformers, and here the number of downloads. Okay, let's go here. You can see the model has been downloaded successfully. Welcome to this section where we will discuss audio processing using Python and how to use models from the Hugging Face platform to process and model audio. So the first thing here, let's name this as audio processing using Python. So how to import an audio in Python? First, we need to import some libraries like NumPy, Matplotlib, and librosa. So let's go import NumPy as np, import matplotlib.pyplot as plt, and then import librosa. So why do we need these libraries? First, NumPy, because we want to convert the audio into an array of numbers. Secondly, Matplotlib, because we need to plot some plots and visualizations of the audio amplitude, of the audio waves, sound waves. Then we have librosa for processing and reading in the audio file. Librosa is the standard library in Python for dealing with and controlling audio files. Secondly, let's go ahead and create a variable called audio path equals, and then I already have here a audio file. You can see it's called audio.mp3. The extension is mp3. Let's pass it here, audio.mp3. Then run it away, straight away. The third step is here. We have to unpack. We have to call librosa.load, call the function load, and then pass in here my audio underscore path, comma. Then we have here the parameter that is called SR, short for sampling rate. The sampling rate is an important concept when dealing with audio. Every single digital audio is associated with a sampling rate. In this case, let's set it to none. This function would return two values. I would unpack them and store them in two different variables. The first variable is y, so my audio, and the second is SR, so sampling rate. So I will store the audio file inside y, and I will store the sampling rate inside this variable SR. Let's go ahead and run that. Now it's trying to load it, and it is already loaded. If we print here y, you can see it's an array. It's a massive array with a lot of numbers, a lot of digital numerical values. Why? Because we have converted and read in the audio into an array. So now we have successfully converted our audio file, our audio path, into an array of numbers. And feel free to visualize it like that. For example, the first 100 samples, these are all the numerical numbers, the numerical digits, when we converted our audio into an array of numbers. Second, we have here y.shape. So let's see what is the shape of my y. The shape will be as this. You can see we have one dimension. The audio lives in one dimension, and it contains 293,280 values. Then let's go ahead and let's explore what is SR. SR is the sampling rate, and it is currently 16,000. Then if you wanted to visualize the audio waves, the sound waves, let's go ahead and create a nice figure by going pld.figure and then pass in here fig size equals. Then let's go ahead and set it as 14,6 or 5, DPI, let's set it to, for example, 150. Then let's go ahead and go plt.plot. Let's plot the audio stored in the variable y. Then let's go ahead and put a beautiful x table as time dash samples. So the x-axis represents the time, the samples would go on the x-axis. Then we have plt.y label, the label of the y-axis as amplitude of the audio or of the sound. Okay, then let's go ahead and run that, and then cool, we have here the sound waves. You can see These are the sound waves. The sound goes like that. Okay, you can see here we have sharp sounds, and we have then soft sounds. Then it goes up, goes down, up, down, like the sinusoidal waves. You can see this is the audio waves. Okay, then let's go ahead and do the next step. Then we need to divide the number of data points in the sound by the sampling rate yields to yield the total time of the audio. So if you wanted to know, or if you wanted to discover what is the total length of the audio, all you have to do is to grab here the y, the array, then get the length of it by passing the y to the length function. Here we have this number, this huge number. Let's divide it by the sampling rate. So the total time of the audio is 18.3. You can see here it's 18.33. Okay, let's go ahead and so it's 18 seconds. Okay, this is in seconds, not minutes, not hours. 18 seconds, 0.33. Then let's go ahead and divide here. You can see from IPython dot display import audio. So in order to listen to this audio, if you wanted to know what this audio actually represents, you can import the audio class from within the display module from within the IPython library. So from IPython, note the I is capital here, .display import audio class. Then run it. Now all you have to do is just call audio and then pass data equals y, comma, the rate equals SR, the sampling rate. Then run that again. You can see here we have this audio. Maybe you won't be able to listen it, but I will run it now.
It seems to me more and more as I live longer that most poetry and most literature, and particularly the literature of the past, is discordant with the vastness and variety.
Let's move on to the next step, because I'm recording my audio now. Then let's go ahead and we have an important concept, which is DFT. And if you don't know this concept is important in the world of audio. It's short for discrete Fourier transform. And if you wanted to visualize this discrete Fourier transform function or integral, you can go ahead and go window equals numpy.Hanning. So numpy is a pretty powerful library. It contains so many functions. One of these functions is Hanning function. The Hanning function computes the Hanning window. You can see here, return the Hanning window. The Hanning window is a tapper formed by using a weighted cosine. Let's just pass my audio here. So you have to pass in the length of the y. Then we have to go and windowed underscore input equals y times window. So all you have to do is just multiply the y by this window that numpy has created or has calculated for us by using the Hanning function. And then DFT, so discrete Fourier transform, equals numpy.FFT. So FFT is short for fast Fourier transform .RFFT, and RFT, I believe it's short for real valued it's a real valued transform Fourier transform, and then pass into here windowed underscore input. Okay, then let's run that. You can see here an numpy.FFT. So it's called FFT.RFFT. RFFT is short for real valued fast Fourier transform. Okay, I missed a typo there. You can run that again. You can see here we have DFT. DFT now is what? Is an array of values. Okay, so again, numpy.FFT. FFT is short for fast Fourier transform dot real valued fast Fourier transform. And if you search here numpy.FFT.RFFT, you can see we have here the function showing up. You can see compute the one-dimensional discrete Fourier transform for real input. Real, you can see real, R is short for real. This function computes the one-dimensional endpoint discrete Fourier transform DFT of a real valued array by means of an efficient algorithm called the fast Fourier transform FFT. So F is fast, this F short for Fourier T transform. And you pass it, you provide it with an array, input array, then you specify the n. Here we kept the n as optional value. You can see here we have a lot of expressions. Feel free to read it in your own time. But now let's go ahead and do the exciting thing of plt.plot, and then we have to pass in here the DFT, so the discrete Fourier transform. Then let's go ahead and plt.title, set a nice little title here as discrete Fourier transform. Then let's go ahead, 3, 2, 1, hope it works, and now it worked. You can see you have the discrete Fourier transform here showing up in a nice visualization, and you can see we have sound waves in a discrete Fourier transform function. Then let's go ahead and do the amplitude. Amplitude equals numpy.absolute. So if you wanted, for whatever reason, to get the amplitude of this discrete Fourier transform sound waves, you can pass it to the absolute function to get the absolute value by passing in a DFT, discrete Fourier transform, and easily go ahead and just plt.plot, then pass in here the amplitude. You can see here we have the amplitude. You can see the difference between this waves and this wave. Here we have the absolute version of those waves. Then let's go ahead and continue our process by going amplitude underscore dB. So dB is short for decibel. Decibel is the unit of measuring audio in the universe. So we have librosa dot amplitude underscore 2 underscore dB, which is a nice helpful function to convert amplitude to decibel, and then pass into here amplitude, comma, the reference equals numpy dot max. And then all I have to do is just go frequency equals librosa dot fft underscore frequencies. So we have here a function called FFT, fast Fourier transform underscore frequencies, and then pass into here SR, the sampling rate, equals SR sampling rate, comma, NFFT underscore FFT equals length of Y. And then we can go easily plt.figure, create a figure, and then set the fig size to make it look pretty as 515,4, and then the DPI as our faithful value 150. Then let's go ahead and plt.plot, and then pass in my frequency, comma, amplitude underscore dB. So remember, we have converted our amplitude unit to decibel and stored it in the variable amplitude underscore dB. plt.xlabel, and then set it as frequency in hertz, in the unit of hertz. Let's go plt.ylabel, and then pass in here amplitude in decibel. You can see decibel is written as D small, B capital. Then we have here plt.xscale. So you have to, if we go ahead and just run that as that, you can see it's now the x scale isn't measured in a logarithmic measure. It's measured in linearly. But once we set the .x scale and then pass in log, short for logarithm function, you can see now the measure changes. It's now showed in a logarithmic fashion. So you have to set the x scale as log to show the x scale as in a logarithmic fashion. And keep in mind, you can see here the scale 10 raised to the power -1, 10 raised to the power 0, 10 raised to the power 1. If we now get rid of this log, it will be measured in linear units, 0, 1000, 2000, 3000, 4000, and so on. But once we open this comment or uncomment this and measure the x scale logarithmically, these numbers will be in logarithmic world. You can see. Okay. Now let's go ahead and continue our process. Here we have a code for converting the audio into STFT by going d.librosa.stft and then pass in my Y. Now you can see this D, what it looks like. This is the STFT version. Then we have to go ahead and just go D underscore dB. So convert it to decibel by going librosa.amplitude underscore 2 underscore decibel, and then pass in numpy.absolute, and then pass in my D. Just we have to pass in my D inside of wrapped within the function absolute, and then wrap this function within the amplitude dot underscore 2 underscore dB to convert from amplitude to decibel, and then set reference equals numpy.max. Now all I have to do is just create a figure, plt.figure, and then pass into my figure here the fixed size, to set the fixed size as 15 or 14,5, dpi equals 150. Then we have plt dot, or librosa, let's go librosa now, librosa dot display, so please display dot spec show. So if you know a spectrogram, spectrogram is the standard way to plot audio, spec show, and then just pass d underscore db, comma, sampling rate equals sampling rate, comma, x-axis equals, set it as the value time, so name it as time, and the y-axis represents the logarithmic. Then we have here plt.color bar. So if you want to make it pretty and visualize the color bar, you can set it as format equals %sign plus 2, then you can dot 0f db. So this is the format of the numbers. We want just to show just 2 decimal points after the 0. You can see here, this is the visualization. It's a spectrogram for visualizing the audio. The x-axis represents the time, the y-axis represents the hertz, you can see in the unit of hertz, and here we have the color bar showing from 80 decibel to 0 decibel. So the closer the color to this color, lighter, it's close to 0 decibel. And then the closer the color here, so these regions here represents the 0th decibels. When we reach this color, this darker, the darker the color, the more the value of this sound wave or this sound point, the closer it is to 80 decibel. You can see here we have very 80 decibel, okay? Then let's move on to the next visualization. Let's go S equals librosa dot feature dot mel spectrogram. Also we have another type of spectrogram. It's called mel spectrogram. So we can go to librosa. This is the library of librosa, you can see here. This is the homepage of librosa, audio and music processing in Python. And here we have the documentation. You can see this is the logo of librosa. It's the standard library in Python for dealing with audio files. You can easily pip install it if you don't have it. For example, if you are on a local Jupyter and you don't have this library already installed, you can go pip install librosa. Then we have librosa is also available on conda package. You can install it by saying conda install c conda fork librosa. And don't forget here, the second website here is the documentation. You can feel free to read about the functions, troubleshooting. We have display. You can see display here. I think they will display the function as we did now, the spectrogram, and also they will teach you a lot about hertz formatter, chroma formatter, and a bunch of other functions that if you want to dive deeper into the browser. But here, let's keep the thing simple and just pass into here y equals y, comma, sampling rate equals sampling rate, comma, n mels. So what is the number of mels? Let's set it as 125, 125, and then, or 128, for example. Then, comma, f max equals 8000. Then let's go ahead and convert it to decibel by going dB. So remember, the B is capital, equals librosa dot power underscore 2 decibel. So convert the power to decibel, and then we have to pass an s, comma, reference equals numpy dot max. Then plt dot figure to create a figure, a nice pretty figure, and then set the fixed size as 14,5, and then dpi equals 150. And remember, we have to make our code pretty and aesthetically appealing. Then librosa dot display dot spec show spectrogram, so spec show, and then pass into here s underscore dB, s in the unit of decibel. Then we have sampling rate equals sampling rate, comma, x-axis equals, let's make it as time, comma, y underscore axis, let's set it as log, short for logarithm. Then we have f max equals 8000. Then on the last here, you have to show a color bar by giving plt.color bar, and then pass into here format equals %sign plus 2 dot 0f, then db. 3, 2, 1, go ahead, run. You can see now the code works fine, and it shows us this another spectrogram, which is by converting the array or the sound wave to STFT or mel spectrogram function. So it's kind of look the same. This is a normal spectrogram, and this is called mel spectrogram. If you wanted to know the difference, you can feel free search that on Google. But now let's go ahead and just do the other part, which is now get a model from Hugging Face and try to classify it, to classify this audio based on a model from Hugging Face. So we have to import required libraries. And remember, this task is called audio classification. So the first thing is we have to go ahead and just import those libraries by going import torch, transforms, transformers. You need transformers, because remember, the default library in Hugging Face for dealing with audio is the same as the text. It's called transformers. So the same library, transformers, works for text and works for audio. Then we have to import here torch audio. Okay, then let's print the versions of them. Torch dot, just for fun, version. Then we have here print torch or transformers dot underscore version underscore. Then we have to print here print torch audio dot underscore version underscore. Run it away. You can see here torch dot version, transformers dot version, torch audio dot version. It will show us these versions. So my torch version at the time of recording this video, 2.9.0 plus CUDA 12.6. Remember, in the future, you might have a slightly bigger number. Then we have here transformers.version. Currently, it's 4.57.3. And here we have torch audio.version. It's 2.9.0 plus CUDA 12.6. So let's go ahead now and do the audio classification process. The first thing is we need to import from transformers. So from the library transformers inside Hugging Face, import auto feature extraction or extractor, AST for audio classification. You can see the naming are here long, so you have to keep in mind the first letter of every word is capital. So AST is all capitals for audio classification, and you have the class auto feature extractor. Run it straight away. Then you can see now it's trying to import and fetch those classes from the transformers library. The second step is that we have to import Librosa again. You don't have to, because you have it, you already have it, but we can import it again. Then we have audio underscore path. So maybe you need to keep this section separate from this section by importing all the necessary libraries again. So sometimes you don't want to run the whole collab. So you might in some point just run from the cell, but have all the codes below the cell working. So you have to sometimes re-import the libraries as we saw here. Then the audio path equals audio.mp3, the name of my audio. Remember, I already have an audio here file called audio.mp3. Let's pass it to my variable here, audio underscore path. Then let's go ahead and we have y,sr equals librosa.load. Just have some practice. Then we have here, we have to pass the audio path, the sr equals none. So here, all we are doing is just, we are passing the audio path to the load function. The load function will take care of this audio path and read the audio path in. It will read this audio file in and convert it from audio waves, from audio file into an array stored in this variable y. You can see this array. It's a huge array, and every single audio is connected with a sampling rate. We store it in this variable called SR, short for sampling rate, and it's currently 16,000. But now let's dive into the most important idea, which is, and also you can visualize it using from IPython, of course, from IPython.display, import audio class. Now let's call this class audio, and then pass in my audio path by going data parameter equals audio underscore path, then run it. You can see now this is my audio. I will play it and you can listen it now.
It seems to me more and more as I live longer that most poetry and most literature, and particularly the literature of the past, is discordant with the vastness and variety, the reserves and resources and recuperations of life as we live it today.
Now the audio has finished. You can see it's finished. We can continue our processing and coding. So the first thing is we have to go feature extractor, feature underscore extractor. This is a variable, well, where I will call the class auto feature extractor dot from underscore pretrained. So here we are calling the method from underscore pretrained and then pass into here the name of the model. So you can see it's from the MIT University /AST dash fine-tuned dash audio set dash 10 dash 0, the version .4598. So 4593. Okay, this is the name of the model. Okay, we are passing this string to the method from underscore pretrained coming from this class auto feature extractor, and then we are instantiating a new object and convert and storing it inside this variable feature extractor. Let's run that. You can see now it's trying to instantiate. Then the preprocessor underscore config.json has been loaded 100%. Okay, now let's go ahead and see here. You can see we have a result. Let's create the result variable equals feature extractor. Now let's now leverage the benefit of using this object feature extractor and just pass into here my y, the array of the audio, comma, return underscore tenses. So return tenses, set it as pt, short for PyTorch. So please return the tenses in the form of PyTorch tenses. And then let's run that. You can see here, this is the running of this cell. Let's go ahead and visualize my result. You can see, and hooray, here we have my result. We have a dictionary, we have a key called input values, and the value as a tensor. Here, this class has worked on my array of values, the array of the audio, and produced this tensor that contains these numbers. You can see we can access this dictionary by going result in the key input underscore values. Then we have this tensor. Then you can also visualize the shape, what it looks like. We have 1, so we have a batch of 1. Then we have 1024. Then we have 128. Okay. Then let's go ahead and dive into calling in the model, loading in the model by going AST for audio classification. So we have imported this class earlier. It's called AST for audio classification. Remember, my task here is to classify audio. We will not going to produce audio. Here, in this specific task, we are going to classify audio by dot from underscore pretrained and then pass in here MIT/AST dash fine-tuned dash audio set dash 10 0 .4593. Then we can also keep in mind, you can copy this name, go to Hugging Face and search for it by going to Models tab, then paste the name into here. You can see we have this model MIT, and the task here is audio classification. And here we have 86.6 million updated September 6, 2023. We can go into it. You can see this is the name. You can copy it. If you don't want to write these numbers, you can copy from here and just paste it over here. Here you can see here we have how to use this model. Use this model and go to transformers. Here we have from transformers import pipeline. You can use the high level helper, and also you can use load model directory as we did together. Auto feature extractor, we have imported it from transformers, and also we have here auto model for audio classification. If you don't like to type code, you can copy that and just paste over there, and you will have the extractor, and also you will have then the model, which is auto model for audio classification dot from pretrained, and then pass in the username of the account / the name of the model. And keep in mind, you might need to read here on how to use this model, okay, later. So the model description, the audio spectrogram transformer is equivalent to VIT, but applied to audio and blah, blah, blah. Let's go ahead and just run this cell. You can see here you have some typo, AST for audio classification. Let's just choose it. You can see the model is running with any single error. You can see we have here model.save tensors. It's loaded successfully. And then all we have to do Now we have a model. Now actually you can visualize the model, beginning model. This is the model architecture. Feel free to look at this model architecture to learn from it. We have AST embeddings, AST patch embeddings. So you can see we have patches here. So this paper, I think here, they will direct us to the paper. You can see in this repository. Actually, we can search for this and write a paper. So yeah, this is that's it. It's called AST, Audio Spectrogram Transformer, by Yuan Gong and et al. In the past decade, convolutional neural networks, CNNs, have been widely adopted as the main building block for end-to-end audio classification models, which aim to learn a direct mapping from audio spectrograms to corresponding labels to better capture long-range global context. A recent trend is to add a self-attention mechanism on top of the CNN, forming a CNN attention hybrid model. So in the past, they used to use a self-attention mechanism on top of the CNN, forming a CNN attention hybrid model. However, it's unclear whether the reliance on a CNN is necessary, and if neural nets purely based on attention are sufficient to obtain good performance on audio classification. In this paper, we answer the question by introducing the audio spectrogram transformer, AST, the first convolution-free, purely attention-based model for audio classification. We evaluate AST on various audio classification benchmarks where it achieves new state-of-the-art results on of 0.485 AMAP on audio set, 95.6% accuracy on SC50, and 98.1% accuracy on speech commands V2. And here, if you visualize it, you can see the architecture is very simple. They have here some input spectrogram, then they patchify it, patch, split with overlap, 1, 2, 3, 4, 5, 6, 7. Then they flattened it using a linear projection layer. Then they embed it. So we have E. This E is short for embedding. So embedding 1, embedding 2, embedding 3, and the rest. Then we have positional encoding, P0, P1, P3. So here they have pre-processed the audio to add, to map embeddings, to map these patches into embeddings, and then insert or inject some positional encodings to preserve the positional of the audio. Then they straight away pass it into a transformer encoder block. Then they have a linear layer to classify and then produce some logits to classify. Now let's go ahead and use this giant architecture, this pretty powerful architecture, AST, which is uploaded on Hugging Face. You can see here we have AST. Then let's use it. So this is the architecture. We have already skimmed through it. Now let's go ahead and go to the next step where we will see here result and then choose the key input underscore values. So now remember, I had an audio and I passed it to my auto feature extractor here, feature extractor. So I instantiated a new object of feature extractor. Then I used that feature extractor object to pass my audio. Then it produced a really, really powerful tensor. This tensor is ready to be passed in this architecture and to be processed further until the model decides what is the actual class of this audio. Then let's go ahead and just use this tensor, this magical tensor, and pass it to here. So prediction logits, I really love the logits, equals model, and then pass into here result, and then also step into input underscore values dot logits. So here, all we are doing is we are fetching, retrieving that input values tensor, passing it to our model, this model, AST. Then this model will go through several steps, thanks to these authors. These are really kind authors. They have created a really powerful model here. Then we can just go ahead and get or grab the logits. Then we can go ahead and get the logits. Now you have logits, prediction underscore logits. And these are the logits. You can see these are unnormalized scores the model has produced, and they represent how much the model believes that this audio belongs to every single class. So this number represents how much of beliefness the model thinks this audio should belong to this class, and so on for every single class. Now let's go ahead and create a variable called predicted underscore class underscore IDs, and then go ahead and torch.argmax and then pass in prediction underscore logits, comma dimension equals 1. So all we're doing here is we are dimension equals -1. You have to grab or fetch the last dimension. Here we are passing my logits to the argmax function. The argmax function will return the index at which the highest value would be, the highest probability value is, and then just give me that item. And that's simple. Then we have this predicted underscore class underscore IDs. Let me just write IDs. Then you can see here we have IDs. It's now 0. But I wonder, what is this class? What does 0 represents? What is the corresponding human readable class name that corresponds to 0? Well, you can get it by going model.config, so short for configuration.id to label. And then all you have to do is just pass. You can see here, these are all the classes, the available classes within this model. So here you can see 0 is speech. Currently, this audio is speech. 1, male speech. 2nd, female speech, woman speaking. 3, child speech, conversation. Then have here babbling, speech, synthesizer, shout, bellow, whoop, yell, children shouting, screaming. These are all the different classes and different categories that exist in this model. You can see here also we have here goose, honk, wild animals, bird. You can fetch some bird sound from the internet and classify it, and it will classify it. Here, the most important idea is that our model predicted that the most believable logit should be at this position here, at position 0. Okay, so the predicted class ID is 0, and we know that 0 is speech. So let's just go ahead and index on this by going model.config.id to label, and then just pass in here predicted class IDs. Then run that, and the model successfully told us that this audio belongs to the speech class. So what a surprise. Okay, so the model is successfully, so look at how much easy it is to use a model from Hugging Face to classify audios. Feel free to retrieve or grab your own audio from the internet or your favorite music or whatever you want, and try to run this model on it, and this model will classify it and return you a class name for what this audio belongs to. So you can see Hugging Face is now a truth treasure. Hugging Face contains 2 million models, and they are all open source to us. They are all available to us. You can easily, within 5 lines of code, I think here, if you compress them, there are actually 2 lines of code to have a model to classify for you, to classify audio without worrying about, you don't have to worry about how to train it. You don't have to worry about the hyperparameters. You don't have to worry about what the architecture, how to combine this architecture, what are the embeddings, what are the position coding, how to construct a transformer. They have done all the work for you. They have uploaded this architecture onto Hugging Face, trained on a massive dataset. The model has really powerful parameters, then you can easily leverage them for free. Okay, so this is how to classify audio, and let's dive into another task in the audio world. And also keep in mind, you can go to Hugging Face, you can go to tasks, models, tasks, then go to audio. Here we have audio. Under the NLP, we have audio. We have text to speech, text to audio. We will do this. We will do text to speech, and also we will do text to audio. And we already have done audio classification. So feel free to play around this. And also we have automatic speech recognition. Now let's dive into another task of the world of audio in machine learning, which is converting audio to text. So this is the modality, converting the modal audio into the modal text. The first thing is we have to, from transformers, import pipeline. So we have to import the pipeline function from the transformers library inside Hugging Face. Then let's go ahead and create a pipe equals pipeline, and then pass into here automatic dash speech dash recognition. So this is the task of converting audio to text. It's called automatic speech recognition, ASR. Here you can see we have a typo, a classic error. Now the model is running successfully. You can see here it's downloading model sentences, same weights, some weights, we have vocabulary, special tokens. They are all loaded and downloaded successfully. The next step is, let's use this model pipe and try to convert the audio into text. So the first thing is, let's go pipe. You can see here the pipe. This is my current pipe, transformers.pipelines.automatic speech recognition.automatic speech recognition pipeline at this stored at this location in the memory. Then let's go ahead and dive into pass in here my audio.mp3. So currently I have an audio file here stored here. It's called audio.mp3. Let's pass this file path into my pipe, which is this model that I have loaded previously, automatic speech recognition, and then we loaded a pipeline and stored it in the variable pipe. Now let's run this command, pipe, and then pass in my audio. Now you can see this is my audio, and it converted that audio into text. You can see here we have a dictionary text. It seems to me more and more as I live longer that most poetry and most literature, and particularly the literature of the past, is discordant with a vastness and variety that the reverses and resources and recorruptions of life, or recuperations of life as we live today. So this is the text. We have converted the modal audio into the modal text successfully. You can see. Feel free to change this audio into whatever audio file you have. For example, you can record your own voice and pass it to here. You can download or load the file here. Then you can pass it to the model, and the model will transcribe that audio into this text. Now let's dive into another task, which is converting text to audio. So now let's do the reverse. Let's do the reverse option, which is converting text to audio. What if you have some text and you want to convert it into some audio file? Well, you can do that easily using Hugging Face platform. The first thing is, let's go from transformers. So remember, when you deal with audio, you have to deal with transformers, not diffusers. From transformers, import pipeline. This is a function, a high-level helper that you want to use, or that you will use to load in models from the platform Hugging Face. Then let's go pipe equals pipeline. Then let's pass into here text to dash speech. So convert text to speech. The reverse process. You can see the model here is loading. It's trying to fetch that model from the pipeline of Hugging Face using the library transformers. Now let it download on its own, and then once it's finished, we can go and write some text. For example, I like coding in Python. For example, this is my text. Then we can go ahead and show it. You can see this is my text. I like coding in Python. Let's pass it to my pipeline. Pipe. Here you can go. You can see output. Let's create a variable called output equals pipe, and then pass in here text. So all you have to do is just create some text. You don't have to store it in a variable. I stored it in a variable to make my code neat. Then we pass that variable text into the pipe function. Then it will produce an audio out of this text. Let's go ahead and run that. You can see now it's trying to create and produce an audio file, audio waves from this text. And it's finished. Now we have output. This is my output. You can see it outputted a dictionary of audio and sampling rate. As I told you, every single digital audio in the computer is connected to a sampling rate. And the sampling rate here is 24,000. The audio here is in the form of array. So this model, as we know, machine learning is the art of converting data into numbers and then passing these numbers into models. Then the model will produce also numbers. So the model will not produce here straight away a audio file path or audio file, but rather it will produce an array of numbers. Let's go ahead now and index to it and have this output. You can see here output, and then get the key audio. This is my array. Then also we can get the shape of it. We can go here at the new cell, output, and then audio. Then let's go and print the shape out of it. The shape is 1,59,840. So it contains 59,840 values. If you go ahead now and do like that, output, and then index on the audio, dot squeeze, if you squeeze it, we will get rid of this one. You can see output here is written output audio and then dot squeeze. Now we have this shape without the one here. You can see just we have this value. We can pass this, so here we can get this and pass this array to plt.plot. So plot it using matplotlib. Okay, then we can go ahead and run that. You can see these are the audio waves, the sound waves that the model has produced. So this audio didn't exist. The model, we provided the model with this text, I like coding in Python. Then the model has produced these waves and stored it in an array that is like that, a massive array that contains 59,000 and it's about values. Now let's go ahead and from IPython. So if you wanted to listen to this audio, you can do that easily by going from IPython .display import audio. So you have to import the class audio, and all you have to provide to this class is the audio. Then go ahead and you can see data, pass in data equals output, and then index on the audio key, comma, rate equals output, and then pass in here sampling underscore rate. Because remember, the output of the model is a dictionary, as you saw here, that contains two different keys, two distinct keys, audio and sampling rate. To access sampling rate, you have to go output, this is the name of the dictionary, and then access the sampling underscore rate, and it will provide you with the sampling rate. And the same with the audio, it will provide you with the array with these values. And if you show output, it will be a whole dictionary. Now let's go ahead and run this as it is. You can see now this is my audio. Let's play it.
I like coding in Python.
And keep in mind, these models are open source on Hugging Face. They are not the most perfect models out there in the world. So maybe the sound will be noisy a little bit. Maybe it contains some noises in the background, but that's fine. All you have to do is go to Hugging Face, go to tasks here, then scroll down until you go to audio, then choose text to speech, this task, converting text to speech. Then you can choose the best models from here. So maybe try to use Microsoft Vibe Voice. Maybe you want to use Aractoco T5 Gamma, and so on. So feel free to choose whatever model you would like to use, you prefer to use from here. Here we have, you can see 3,000 models dedicated to this task, which is text to speech. And also we have text to audio, which is the task of converting text to audio. Here you have models, 2,623 models. You can see Stability AI also has a model called Stable Audio Open. Also have Facebook Music Gen Large. We have also Marvis AI / Marvis. And you can see we have tons and tons of models. Then also we can go to here, ASR, Automatic Speech Recognition. Then you can find heaps of models. How to use it? You can go to here, for example, OpenAI Whisper. Then all you have to do is just go to Transformers, then copy this code or this code into the environment Colab, and it will work for you. Just as easy as that. Here we can go ahead and so with that being said, we've finished the modal audio. We have finished this section of audio. You can see we have done 3 different tasks. The task of audio classification, where we classified some audio into speech here. It told us that it's speech. You can see here, these are the logits that the model has produced. And then we have provided with some speech, and it says that it is 0, which means it's speech. Here you can see speech. And then we have another task, which is converting audio to text. The process of converting audio into text. And we have provided it with some audio file. You can see here, we have loaded a model called Automatic Speech Recognition. And be careful about the typos. Previously, I written here auto in a reverse way, and it didn't load. You have to be careful when you write these words. Then, here we have converted the audio into text. You can see it seems to me more and more as I live longer. So we have provided an audio and it converted it into some text. At the last, we have the last task, which is converting text to audio. the reverse. You provide the model with some text, and the model tries its best to convert this text into audio using some deep learning mechanism. And you can see these are the sound waves. And then if you want to save this audio file path, you can go with that. You can go with that easily by going. You can see here we have a from IPython. So let's go from PyDub, from Python dub import audio segment. This is a class. Then we have to go ahead and create an instance called audio underscore seg equals audio segment. The class audio segment, you can see segment, and then provide here the output, and then index on what? On the audio to get the array with these values. Dot 2 bytes. Then let's go ahead and comma, provide the frame underscore rate equals, so the frame rate is the same as the sampling rate, but another name. So output and then index on the sampling underscore rate. And then you have to provide or supply this function with the sample underscore width equals output and then index on audio dot dtype dot item size, comma. So here you can see we have here dtype, so the data type, okay? Then at the last, we have to provide the parameter channels. So how many channels are there? We have one channel, 3, 2, 1, run that. And now we have successfully saved our model. Let's go ahead and audio underscore seg. Let's use that object or that instance dot export. So we have a function called export that will export my audio and then pass in the name of the audio. For example, my underscore audio saved dot, and you have to provide the extension as MP3, comma, the format of the audio should be in this format, MP3. Now let's run that, and you can see it saved the model with this name, my audio saved.mp3, using this name. If you open this file section in Colab, you will see that I have now a new file, my audio saved.mp3, and to download it, just double click on it and it will download straight away. In this section, let's dive into Diffusers models for images and generating images using Hugging Face platform. The first thing, let's name this cell by going image processing. So let's take the first, some techniques to process images in the Python language using Python programming language, and then let's convert it into Markdown. You can see image processing using Python. So the first thing, we need an image. You can see here I already have an image and it's called whiteflower.jpg. You can see it here. Now let's process this image using Python. The first thing is, let's go from pill import Python import image by going from pill import image. So from Python image library, import the class image, and the class image will read in our image file and then convert it into an array full of numbers by going pick equals image dot open. Then let's pass into here my image path by going flower dot, you can see here my extension is JPG. So let's write white dash flower dot JPG. And now it's read successfully. If you go ahead and show this PIC, short for picture, here we have this picture. Then let's go ahead to the next step. So now we have done the reading of the image. The next step is, what if you want to check the type of the picture? What is the type of the picture? The type is JPEG image file. And keep in mind, if you read in a PNG image, the type of it will be PNG image file. And if you read a GIF image, it will be GIF image, and so on. So whatever the extension you have, this ending part will change depending on the extension of the image. Let's go ahead. Then we need to import numpy as np to convert our image into an array, into an numpy array. And remember, numpy is the fundamental computing library inside the Python ecosystem for data science. Let's go ahead and do picture underscore array equals numpy.asArray. So we have a helpful function inside numpy. So within numpy, we have a function called, you can see numpy numerical Python, we have a function called asArray. This function is responsible for converting the image into an array in NumPy by passing in my picture. Then let's go ahead and show my picture array. You can see we have this. We can show data and then convert this image or this picture or this image into an array full of numbers. You can see these are 255, 255, 255. It's a white pixel corresponding to this region where you can see I have here so many white pixels. And these are all white pixels, okay? Then we have here some yellow pixels and so on. Now let's go ahead and retrieve the shape of this array by going pick underscore array dot shape. And the shape of it is, as you can see, we have 360, 360, 3. So here we have the height, the width, and the color channels. So every single image is containing a height dimension, a width dimension, and a color channels dimension. The number of color channels, if the image is colored, so if it's a colorful image, then the number of channels would be 3. And if the image is a grayscale image, so it's a silver image or a gray image, then you have just 1 channel. In this case, it's a colored image. So here we have 3 different color channels, and these are red, green, blue. Now, if you take a closer look at my picture array, it contains integer values. These numbers are integer. These are whole numbers. If you want to normalize the image, we have to divide it by 255, so 255. Then it will be normalized, as you can see, where the most white color would correspond to 1, and the most dark color, so the most black color, would correspond to 0, and every other color between 0 and 1. So you can see here, once we go ahead and import matplotlib, import matplotlib.pyplot as plt. So matplotlib is the default library in Python, or the standard library in Python for visualizing and plotting some visualizations. Let's go ahead and plt.imshow and then pass in my picture underscore array. So you can see here, by passing my picture array to the imshow function, imshow is short for image show. It shows our image, the flower image, you can see. And here we have some axes. If you want to get rid of these axes, you can do that easily by going plt.axis and then pass here false. You can see here, it will turn off the axes, the x-axis and the y-axis. Now let's go straight away and picture red. So what if you want just to view or to display just the red channel? You can do that easily by going picture red equals picture underscore array dot copy. So first, I advise you to copy the picture array into a new variable. So rather than manipulating and damaging the actual array here, where you could do that, but I advise you, I highly recommend that you copy this array and store it into a variable called picture underscore red. Then you can see here we have the same exact copy. So here pick red currently is the same exact copy because we have done nothing but copied the array into a new variable called pick underscore red, short for picture red. Now let's do the manipulation part, where you will go ahead and you can remember we have RGB. Now we want to 0 the green channel, 0 the blue channel, and just keep the red channel. And look what happens. Here we can see pick underscore red, and then give me all the height dimension, no problem, comma. Also give me all the width dimension. I don't want to get rid of the width or height. I don't want to cut anything of the image, but just set the one channel, which is G. So remember, R0, G is 1, B is 2. Please set the one channel, this green channel, set it to 0. So here you can see green channel set to 0. So 0 it. Then the same with the blue channel. Give me all the height, all the width, and then the second channel, which is B. Remember, in programming, we start counting from 0, set it to 0. So 0 out the blue channel. Then here we have blue channel set as 0. You can see here, my picture red now is a red image. So you can see now, we have removed the blue channel, the green channel, and only kept the red channel. You can see here we have this array. It just contains, you can see here, every single blue value and every single green value is now zeroed out. The green channel is 0. The blue channel is 0 for all pixels, for all values. Just the red channel is kept. And you can see now we have a very reddish picture. Now let's go ahead and do the same with the rest and the remaining of the channels by going RGB. Remember, here we have to go ahead and copy the array by going pick underscore green equals pick underscore array. So give me the picture array, the original array, but copy it, dot copy. So make a copy of it. Then let's go ahead and say pick underscore green, and then give me all the height, all the width, but please go ahead and for the red channel, zero it out. And the same here, pick underscore green, give me all the height, all the width, but please for the blue channel, zero it out. Here we have, remember, 0 corresponds to what? The red channel. So red channel is zeroed out, and here the blue channel is zeroed, set to 0, and here also set to 0. And now let's see what would happen here by printing out my picture underscore green. 3, 2, 1, run that, and here you have a green like image. So you can see the red channel is zeroed out, the blue channel is zeroed, while we have kept all the green channels. And you can see now we have a green image. Let's do the same with the last channel by going ahead and copying out the picture underscore blue equals pick underscore array dot copy. Let's go picture underscore blue, and then just set the 0 channel to 0, which is red, and then do the same with the 1 channel, which is green, set to 0. Then let's visualize my picture underscore blue, where you have a blue image. Okay, so we have red, green, blue. We have 3 color channels, red, green, blue. Now you can see that these are the manipulation of images. We can go ahead and also do some further processing using now CV2, import CV2. So CV2 is a library inside Python, and it's short for Computer Vision 2. So CV has also pretty much functionalities to manipulate and to process images in Python. So let's go ahead, image equals cv2.imread. So please image read the image by passing here the path of the image. So let's copy here the path of the image. You can go ahead and just copy the path and pass it to this function, imread. Here we have image. You can see it read the image here. But you can see there's a difference. Why when we read the image using the normal PIL library in Python image library, it read that image and it displayed that image as this. You can see here, these colors are yellow. But here, when we read the image using this library, CV2, you can see here we have different color. We have different color hues. Why? Because if you notice, the real image or the actual image actually is the same as the way that the PIL image has read it in. So CV2, keep in mind that CV2 library here, it changes the order of the channels. So rather than red, green, blue, it's blue, green, red. So let's go ahead and change that. Here you can see image underscore RGB equals CV2. If you want to get it in the original format, if you want to get back to the original format and the original form, you can do that easily by going CV2 dot CVT color. So you have a nice function here. It's an amazing function. It's called CVT color, and then pass into here image comma CV2 dot. You can see here color. Write it all in caps, so all in capitals. Color underscore BGR. So blue, green, blue, blue, green, red. 2 red, green, blue. So this is the name that you want to write. Color underscore blue, green, red. 2 red, green, blue. As I told you, this library or this package, which is called CV2, when you read an image using it, it reads that image and it manipulates and damages the color schemes. How to solve it? Well, there's a helpful function, a very amazing function. You can use it. Just pass in the image and then write this flag, cv2.color_bgr2rgb. Then let's go ahead and run that. You have image_rgb. So you can see we are now having the same image. You can see we have returned that image to its original format, to its original form. You can see now this region is now not anymore blue, but now is the original form, which is yellow. Okay, so this is how you can get back to the original format. If you read an image using cv2, please keep in mind you have to call the function cvt color, pass in the image. You want to apply the manipulation on it, then write this flag, cv2.color_blue green red to RGB, red green blue, to the normal and regular format. So now let's convert this image into a grayscale image by going image_gray and then equals cv2.mread. So we have to read in the image. So remember, mread short for image read. So please read in the image, and we have to pass into here my image file path by copying the path and then pass into the my function here. Then let's go ahead and also provide this parameter cv2.imread_, so image read underscore grayscale. So if you want to convert this image into a grayscale, you have to provide this flag cv2.imread_grayscale. Let's go ahead and run that, and now we can easily go ahead plt.imshow and then just pass in my image_gray, cmap, set the color map equals to gray. So you have to set the color map as gray in order to display the image in a gray format or a gray mode. You can see now we have a grayscale image. So an image in the fashion of grayscale. It has gray colors. Okay. Now let's go ahead and do the next step, which is image_resize. So it's an important skill of how to resize images. You will see it a lot, especially in Hugging Face models. There are some cases where you need to resize some image in order to meet the predefined criteria or the assumptions of the model. So it's a really important skill to have. Image_resize, cv2.resize. So just use the function resize, then pass in my image. Then you have to define the size, 200, 400. For example, set it as 200, 400. These are the dimensions and the dimensions of the image. So let's go ahead and just go plt.imshow and then pass into here image resize. You can see it will resize my image using this function resize. Go ahead and run that, and now we have a resized image. You can see here the x-axis, so the width here spans until it reaches 200. So you can see here 200. This corresponds to the x-axis. Here we have from 0 to 200. So here we have 200, and the y-axis spans from 0 until it reaches 400. So you can see here 350, it reaches 400. So these are the dimensions. If you change it, for example, 150 by 150, then it will change into 150 by 150. You can see we have a squared image, 150, and here we have 150. Okay, feel free to play around and have fun with that, with those values. Now let's go ahead. W_ratio equals 0.5. Then we have height underscore ratio equals 0.5. Here, remember, when we resize the image into 200, 400, the image scaling wasn't equal. You can see the image here is squeezed, is squashed. It's not in equal dimensions. It does look like a real image. So in order to have in order to resize the image without damaging its scaling, without damaging its dimensionality, keeping the image to be in equal dimensions, you have to specify W ratio as 0.5, height ratio 0.5, so the half. Let's go ahead, new image equals cv2.resize, and then pass into here my image, and then pass here 0, 0. So for the D size, then f(x) equals W_ratio. So W ratio stands for width ratio, fy, so the y-axis corresponds to the height ratio. H ratio. Then now let's go ahead and just display my image using the new image. You can see here we have resized our image successfully, but keeping the dimensions equal, keeping the dimensions to be in a not damaged way. You can see here we can set a W ratio, height ratio, pass these variables to the parameters fx, fy to the resize function. Rather than specifying these dimensions here, we passed here 0, 0, and then determine fx as W ratio, fy as the height ratio. Then we have this image with a neat scaling. You can see it's now 180 by 180. So it halves the image width and height. Then let's go ahead and generate. Now let's dive into the actual generation. So that's enough with how to pre-process images, how to deal with images. You can see here we have done plenty of skills of reading the image, converting it into array, then how to get the red channel, green channel, blue channel. And you can see here we have used the library CV2 as an alternative. Then we have convert the format from blue, green, red into red, green, blue. You can see here from blue, green, red to red, green, blue. And then you have here, you can see the way to convert it into grayscale. And the last thing here, how to resize it with unequal dimensions and with equal dimensions. That's enough with the skills and on how to pre-process images. Let's dive into how to use image models, diffused models from Hugging Face to actually generate images by going, let's name this, generating faces using diffusion models or diffusers, diffusion model. So here you can see this task is one of the most early tasks in the world of generating images, and it's pretty well served. You can see here from diffusers, import the DPM pipeline. So DDPM pipeline. So from diffusers, import DDPM pipeline. If you wonder what is DDPM, DDPM is a diffusion model, and it stands for denoising diffusion probabilistic model. And if you look at here, denoising diffusion probabilistic model. Okay, this is a DDPM pipeline. We want to import that pipeline from the diffusers library. Go ahead and import. You can see now it's importing. This model has a paper. If you search here, DDPM model paper. This is the model, denoising diffusion probabilistic models. And you can go here, you can see it's by Jonathan Ho and et al. So here you can see we present high quality image synthesis. So image synthesis is a fancy word for image generation. Results using diffusion probabilistic models, a class of latent variable models inspired by considerations from non-equilibrium thermodynamics. So remember, the diffusion model is inspired by the physics science, specifically non-equilibrium thermodynamics. So particularly this field has inspired this deep learning model diffusion. Our best results are obtained by training on a weighted variational bound designed according to a novel connection between diffusion probabilistic models and denoising score matching with Langevin dynamics. And our models naturally admit a progressive lossy decompression scheme that can be interpreted as a generalization of autoregressive decoding. On the unconditional Cypher 10 dataset, we obtain an inception score of 9.46 and a state-of-the-art FID score of 3.17. And you can read that in your own time. So this is the paper behind this class. Feel free to read it in your own time, but now let's go ahead and use this class. It's called DDPM pipeline from Diffusers library. And you can see here the paper is loading, where they generated faces. So the actual interest of this paper is to generate faces, and we will do the same as they did. We're going to generate faces. And you can see here they have so many equations in the paper. You can see also not faces but also images. So you can see from here, these are this is the forward process, where they start with non-noisy image, then they slowly add noisy, or they start from random noise, then the model slowly but gradually denoises that noise until it reaches a point where we have a coherent logical object. We have a forward process and we have also a reverse process. Okay. So now let's go ahead and use that model. You can see here DDPM equals DDPM pipeline, then dot from underscore pre-trained, and then pass in Google / DDPM dash celeb AHQ dash 256, then we have .2 CUDA. So here we have from pre-trained method and then pass in Google. So the provider of this model on Hugging Face is Google / denoising diffusion probabilistic model dash celeb. Celeb is a dataset of faces. Celeb AHQ 256. If you search here and say here dataset, it's a huge dataset. It's also provided on TensorFlow. You can see TensorFlow library is providing this dataset. Celeb underscore A underscore HQ. So in case you don't know what this is a dataset for faces. You can see here high quality version of the Celeb A dataset consisting of 30,000 images in 1024 by 1024 resolution. And you can see here you can download the image. You can download it from this GitHub repository, and you can go down. There's some code to download and get the dataset. You can see these are faces for people. So Celeb is a dataset of faces containing tons and tons of human faces. You can see DDPM dash Celeb AHQ dash 256. You can see now it's downloading. So it's trying to load in this model from the Hugging Face platform. Now let's go ahead and just use this model by going. So you can see here we have this model DDPM. This is the model DDPM pipeline. It's a pipeline. Let's go ahead and just generate an image equals DDPM and then pass in num underscore inference underscore steps equals 30 dot images at index 0. So all we're doing here is just we are calling the DDPM denoising diffusion probabilistic model, passing in num inference steps equals 30. Then we are stepping into the images property and then getting or retrieving at index 0. Let's run that. You can see it's now trying to generate that image. And you can see, wow, you are going very fast. Why? Because I have here a GPU. Go to runtime, change runtime type. You can see here I'm using currently L for GPU. So don't be surprised if you are using CPU and you are slow or your model is going slow. Currently, I am using GPU. Okay, that's why my model has done that quickly. Now let's go ahead and just show this image. You can see this is a face for a human. Okay, so this is the diffusion model, the same as they did in the paper. So remember in the paper here they have generated faces. Okay, here you can go down or up. Yeah, here you can see they have a lot of faces. They generated a lot of faces, and one of these faces now is showing up in our collab environment. Because why? Because we used the model DDPM dash celeb AHQ dash 256. Now let's go to the next step and go from diffusers, import DDPM scheduler. Now you can see we have here DDPM scheduler, comma, UNet to the model. And also we need to import the UNet to the model. Run that. Now let's go scheduler equals DDPM scheduler. Then let's go dot from underscore pre-trained, and then pass into this from pre-trained the name of the model. By going here, you can see passing Google / DDPM. So remember, denoising diffusion probabilistic model dash celeb dash or AHQ dash 256. Just like that. We are passing here the name of the model to the method from underscore pre-trained coming from the DDPM scheduler. Let's run that. Now we have a scheduler. We can check it out. Scheduler. Okay. This is my scheduler. You can see it has a bunch of info. Class name, DDPM scheduler, diffusers version 0.36.0, beta end, beta scheduler, beta start, clip sample range, and a lot of other properties and attributes. But now let's go ahead and focus on how to use the model unet by going model equals unet 2D model. So the unet 2D model, two-dimensional model, dot from underscore pretrained. So use from pretrained and then pass in Google /ddpm -celib ahq-256.2 CUDA. Keep in mind you have to move this model to CUDA environment or to CUDA device, because otherwise this model will live on the CPU and it will take forever generating one simple image. Okay, run that. Now it's getting my model. We can check out my model, and this is my model. These are all the layers. You can see this is the deep learning. You go deep. You stack deep layers on top of each other. You can see we have here CellU, activation function, we have convolution, dropout. This is the unet model, okay? Module list, we have ResNet, block 2D, group normalization, convolution 2D, linear, group norm, dropout, convolution, and they replicated these blocks many times. Okay, you can see here the scroll goes forever. We have so many layers. Okay, feel free to explore this architecture in your own time, but now let's go ahead and use the scheduler, then dot set underscore time steps, and then pass 50. So I want to set the time steps as 50. Run that. Now if you check out the scheduler dot time steps, so how many time steps do I have? Here you can see we have 50 time steps, and these are as 980, 960, 940, 920, 980, 880, 860, 840, 820, and so on and so forth. Now let's go ahead and import torch. Then let's go sample size, set the sample size variable equals to model.configuration.sample underscore size, and then show the sample size. So here we have tapped into the configuration of the model.sample size. Then we have here the variable sample underscore size. You can see we have here 256. Okay, this is the sample size. So all we have done is model.configuration.model.sample underscore size. Then all of a sudden the sample size is 256. Now let's go ahead and noise equals torch.randn, and then we have here 1,3, sample underscore size. So we are passing the sample size inside the tuple. Here we have a tuple. The 1 represents the batch size. So how many image? Here inside this batch only we have one image. We have just one image, comma. Then we have here 3 color channels, red, green, blue, comma. We are passing the sample size here as a value. Then let's go ahead, comma, device equals CUDA. So now we have a variable called noise, and it stores a random torch, random tensor. We can show it here. You can go noise. This is my noise. So just noisy numbers, noisy values, okay? Rand_n, pass here 1,3, sample size, then device as CUDA. Now let's go ahead and create a variable. You can see here we need to duplicate the sample size, sample underscore size 2 times, okay? We have to pass them twice, like that, okay? Because here we have color channels, height, width, okay? Now let's go to the next step where input equals noise. Then let's go a for loop for t. So for every single t, so time step, for every single time step in scheduler dot time steps, so loop through the time steps, then do the following with torch dot inference mode. So we need to enable the inference mode. We have to enable and turn on inference mode. And when you enable and turn on the inference mode using PyTorch, then you are basically turning off the back propagation algorithm. You are turning off the gradient tracking in PyTorch, and you are in the inference mode. Okay, let's go noisy underscore residual equals model, and then pass input comma t dot sample, and here let's call it noisy residual equals model and then pass input, comma t, so the time step that we are looping through in scheduled time steps. And remember, this time steps is just a tensor with these values. It contains here 50 values. Okay, we have here 50 different values. They are representing the time steps. We are passing every single time step alongside with the input to the model. And the input is what? Is random noise. So we are taking the random noise, passing it to my model, the unit model, and providing also the time step here, and then taking the sample. Then we have here previous underscore noisy underscore sample equals scheduler dot step, and then pass into here noisy underscore residual, comma t, comma input, and then dot previous underscore sample. So here we are getting the previous sample, the previous step. Then at the last, you can see we need to set the input variable. Input equals previous underscore noisy underscore sample, and run that. Now it's running. So now it's looping through the time steps, and now it's finished. It's done this kind of steps with torch inference mode. Please enable the inference mode. Then call the model, pass in my input. So input is what? Here my input is just random tensor. If you want to show it here, you can go dot shape. You can see here, this is my shape. Let's squeeze it by going squeeze here, squeeze function. So now we don't have anymore that one dimension. Now let's permute it to be compatible with matplotlib. Dot permute pass 1 2 0. Why? We need to pass here the height here. So height has 1, put it at the first. The width, put it here. Then the color channels, move it to the last dimension. Now we have a compatible tensor. Let's go dot numpy. Now dot detach first. Here we have dot detach, then dot numpy, because we need to detach it, and then numpy. You can see dot, and then convert it numpy version device. Yeah, we need to dot to CPU, then numpy. Okay, then we need to pass this to plt dot im show. You can see here we have random noisy image. So we are starting from this noisy image. Okay, so the error here was we were converting this tensor, which is living on the CUDA device. We were converting it to numpy. If you see here, this is a PyTorch tensor, and then once you turn it into numpy, okay, by going .numpy, it gives you a huge error saying that, hey, you are storing that tensor on CUDA, can't convert CUDA device to numpy, because numpy lives on the CPU. Numpy always works and deals with arrays stored in the CPU. So use here, they give you a hint. Please use tensor.cpu or .to CPU. You can see now you can go ahead and .cpu. Okay, you can see now we are moving our tensor.cpu. Then we can go .cpu. Okay, it turns it into CPU. Then we can go .numpy, and it returns a numpy version of it. Then we can pass that to our plt.imshow function, and it will show random noise image. So you can see here we have random noisy pixels. So nothing to infer from this image, just random pixels. And every time you run that, you get random shuffle of the pixels. Okay, we are starting from this noise and then passing the t, which is the time step alongside with this input, noise input, and then getting the previous sample. Then we are taking this previous noisy sample and assigning it to the input variable. Okay, let's go now from PIL. So let's go ahead, and we have another idea of showing a distribution, or another concept of showing the distribution of this array. So all you need to do is go ahead and copy this array, then just show its distribution by going here. You can see we have this numpy array. It contains all these dimensions. We can go flatten it. You can see we have now one dimension because the histogram just deals with one dimension. Then we can go and plt.hist to show a histogram. Here, if we put semicolon, you can see we have a nice little amazing histogram, and it's showing this histogram. You can see it's like Gaussian distribution, okay? It's like the normal distribution. So this is noisy image, and it is representing Gaussian distribution, okay? So random Gaussian distribution. If you search here, Gaussian distribution images, it's like that. You can see we have this like of shape, the same as here, okay? So let's go ahead and input, or from PIL import image, the image class. Then let's go import numpy as np. You don't have to, but let's recreate it. Then we can go image equals input divided by 2 plus 0.5. So we are dividing our image by 2, then we are adding 0.5 dot clamp, and then also need to call the clamp function, pass in 0,1, then dot squeeze. So you can see here we are again squeezing our image. Why? To get rid of that batch dimension. Then we have here image equals image dot permute. So you can see permute, we are again permuting and reordering the order of the height, width, color channels dimensions by going 1, 2, 0 times 255 dot round. Then we are rounding here dot 2. Then we are moving to the torch dot u integer 8 dot cpu, you can see, and then dot numpy. Then we can go image equals image dot from array, and then pass in my image, and here we have my image. So this is the image of the face. You can see we need to run this again. You can see here, let's write another face, image, then another face. Then we can go down and use this code again. You can see this for loop, and then from PL import image, then divide the image, okay? You can see this face, okay? So because we have overwritten over the variable image using this, you can see using this code, okay? So in order to get this image, you have to rerun the codes above, okay? So you can see here image is showing this image, and if you run again, we have the same image, but here we have done it using a scheduler from the library diffusers. So you can see here from diffusers we have imported the scheduler function, ddpm scheduler, and unit2d model. Unit2d model. So we've done it here manually. Instead of this doing it automatically, here we have done it manually using a for loop. We started from this random noise, used a for loop as a loop across the time steps here. So we are looping here through these time steps, and then slowly but gradually denoising that noise and recrafting this image. You can see we have crafted this image from scratch, from pure noise. So we had pure noise, then we turned it into this face, human-like face. By doing this code, we use the unit2d model. You can see here, this model is representing the unit2d model. Then we pass the input comma t, okay? Now let's go to the last task, which is generating images using a prompt with diffusion. So this task is one of my favorite tasks because we're going to generate images using a prompt with diffusion models, or using diffusion models. So here, remember, we need to import torch. Then we have to go to from diffusers, import diffusion pipeline. So we need to import diffusion pipeline from within the diffusers library. Then let's go ahead and set a pipe here. So pipe equals, you can name it whatever you want. I will name it as image underscore generator equals diffusion pipeline, and then dot from underscore pre-trained. Then we have to pass in here the model of the stability I. So if you go to Hugging Face here, Hugging Face, we can go to Models tab, then go to Tasks, then choose the task which is converting text to image. You can see we have it here. computer vision. It's under computer vision, which is text to image. Choose that. Here you can see the first, if you choose or if you sort the models based on most downloads, here we have the Stability AI / Stable Diffusion -XL -base -1.0, the same model that we want to use. If you go to use this model and then diffuse this, you can see you have a plethora of images here. Let's copy this code. You can see the same code, import torch from diffusers, import diffusion pipeline. Then we have here some diffusion pipeline dot from pretrained, and then pass in Stability AI / Stable Diffusion -XL, so xlarge -base -1. Then the d type here is torch dot b float 16, device map equals CUDA. Then here we have some prompt, astronaut in a jungle, cold color palette, muted colors, detailed 8K. Let's copy that code and then go here. So rather than writing this code, you can easily paste that code here. So feel free to paste it here and then run that again. You can see now it's trying to download that image, that model, and it's now generating the image, which is astronaut in a jungle. You can see here we have astronaut in a jungle, cold color palette, muted colors, detailed 8K. So here in this model card, you can see they have SDXL based model card. You can scroll down. Here we have the model architecture. We provide a prompt, so as the prompt here. Then we have some base architecture. Then we have some latent space. Then we have a refiner. So there's an internal refiner that refines your prompt. So your prompt doesn't get inputted the same as your prompt. There is some refiner, text refiner, that refines your prompt or your instructions. Then we have some image of the size 124 by 124. So here you can see model description developed by Stability AI, model type diffusion based text to image generative model, license, this is license, model description, this is a model that can be used to generate and modify images based on text prompts. So based on a text prompt, you can generate a model. It's a latent diffusion model that uses two fixed pre-trained text encoders. And here, if you go to Polo Club diffusion model, it's an explanation for Stable Diffusion. So you can see here diffusion. If you go to outside here, you can see it's called Stable Diffusion explained with visualization. If you go here, you can see first we have some prompt, a cute and adorable bunny with huge clear eyes holding a bunch of flowers in the style of cute Pixar character. So then we have some text representation generator. If you open this, here we have a tokenizer. So first your text gets tokenized, and as you know, tokenization is the process of segmenting, breaking down your text into several tokens, and every single token represents a single chunk. So it's the process of chunkifying your text. Then we have here 77 tokens. Start token that triggers and motivates the model. Then we have a cute is a single token, and is a token. You can see adorable is a single token, bunny is a token with huge clear. Then we have some text encoder. The text encoder here, as you can see, we have image encoder and a text encoder. So you can see photo of white dog. You have image encoder, text encoder. It tries to understand the text and then tries to generate an image. Okay, so you can see Stable Diffusion uses a special text encoder that connects text with image. For an image caption pair, the text encoder converts the caption's tokens into a vector that is close to the image's vector, produced by a paired image encoder not used in Stable Diffusion in hybrid text image space. Then after that, these tokens gets mapped into a vector for each token. So these tokens are mapped to IDs. Then for every single ID, we map it into a vector. So you can see vector for each token. Start has its own vector, A has its own vector, and every single vector has some numerical values. 0.03, minus 1.33, 0.33, 0.31, and so on. So for every single token, we have a single vector, and these vectors contains numerical values. After that, after the text representation generator has finished, here we can see we have the image representation refiner. So we have the unit. So we have the same architecture that we used earlier, which is the unit model. The unit is a convolution network. You can see predicts noise. You can see here. This is the unit. Here, image representation. It starts with random noise, then it does several steps many steps. You can see 8, 9, 20, 27, 20, 30, 30, until it gets to the coherent last image, okay, until the clear image. And here, after this image refiner, we have the upscale. You can see here we have this time step. We can go to 1. You can see here we start with random noise, we start with pure noise, and then slowly but gradually the diffusion model denoises it and gets rid of the noise until it creates this really clear image. It's a very clear image, okay? So this is the process of diffusion. Diffusion is one of the greatest ideas in the world of deep learning. It starts with random noise, and then slowly it tries to remove that noise. It tries to delete that noise to get rid of it, and then slowly build coherent objects like eyes, like hair, like ears, and then it shows us this nice, really appealing image, which is an adorable bunny, okay? So now the model has finished. We can visualize the image by going image. You can see here it's an astronaut in a jungle with cold colors, muted, 8K, and detailed. You can see we have this astronaut in a jungle, okay? This is the image from the Stability AI Stable Diffusion, and that is how to generate images using Stability AI diffusion model. So that is how easy. You can see it's really easy how to use a model from Hugging Face. All we've done actually is just we've gone to from diffusers import diffusion pipeline class dot from underscore pretrained method, and then pass in Stability AI / Stable Diffusion XL base, then just created and crafted some prompt, and then pass that prompt into a pipe dot images at index 0. So let's go to Stability AI, or to the expression here. We can see selecting the prompt. We can actually copy this prompt and then go to here. So all we've done is prompt equals this prompt, a cute and adorable bunny with huge clear eyes holding a bunch of flowers in the style of cute Pixar character. Then we have here image equals pipe, and then pass my prompt into here inside the pipe dot images at index 0. Then we have here image. So all we are doing here is just crafting some prompt, passing it to my pipe, and then dot images. Then we are here, you can see we are generating the image, okay? Now behind the scenes it's starting with random noise, then slowly it's trying to remove that noise and trying to draw that image, trying to paint that image for us, which is a cute and adorable bunny. So if you go to here, you can see this is the resulted image in the Polo Club tool. Let's compare it to what will be outputted in our Colab environment using this model, Stability AI. And if you choose another prompt here, for example, a very beautiful cityscape, you can see, run that again. It starts here from random noise. Then slowly it's trying to remove that noise and shows a really clear cityscape. You can see here we have the cityscape, okay? And if you select another prompt, for example, for example here you can go to a cute and lovely 4-year-old baby. You can see this is the clear image. Then if we play the time steps, you can see now it's trying to add some noise. You can see starting with noise, then slowly denoising it until it creates that logically coherent and logically and appealing image. Now if you go to here, you can see here we have an adorable bunny image. You can see we have this rabbit, okay, using that prompt, a cute and adorable bunny with huge clear eyes. So you can see it has huge clear eyes holding a bunch of flowers. So it's holding here, you can see a bunch of flowers, orange flowers. Then we have here in the style of cute Pixar character, and it's in the format of Pixar character. If you know Pixar character, this is one of the Pixar characters. Then let's go and copy that prompt here, which is a cute and lovely 4-year-old baby, and paste it over here. We have here prompt, paste it over here. Then just all we have to do is go ahead and image equals pipe. So call the pipe, and then pass into here images or prompt, pass the prompt, dot images, then access index 0, then actually show the image. So if you know the TV static images, it's the same as the random noise. It's starting from random noise and then slowly getting rid of that noise and painting or drawing the image that you ask here. And this model is considered a conditioned latent diffusion model. Because why? Because it's conditioned upon our text prompt. You instruct it and it's conditioned based on the prompt. So if you go to here to the Polo Club tool, and you can see here what is a Stable Diffusion model. Stable Diffusion is a text to image. So it's a model that converts text to image model that transforms a text prompt into a high resolution image. For example, if you type a cute and adorable bunny, Stable Diffusion generates high resolution images depicting that a cute and adorable bunny in a few seconds. Click select on the prompt here to change it. And there they have discussed how it works. Stable Diffusion first changes the text prompt into a text representation. As we said, it first tokenizes our prompt. So here, this prompt is first gets tokenized, then every single word gets mapped into a vector. Then it tries to understand that vector semantically and contextually. Then it tries to generate an image. You can see here, image. This is an image of a cute girl, 4-year and cute girl. Okay, as we asked in the prompt. And at the last here, we have a prompt. Let's try a prompt that we write here, which is a giraffe with top hat, and then pass this prompt into my pipe, the model, by going model, and then pass in my prompt, then dot images, add index 0, then let's show that image, and here we have called it pipe. Okay, so image equals pipe, pass in my prompt, dot images at index 0, then show that image. We can go ahead and run that. Now it's trying to generate or trying to produce a giraffe with top hat. So as we said here, you can see in the Polo Club tool, they have said that they have a tokenizer. So first, this prompt gets tokenized. So for example, like that, a giraffe is a single token with is the token, and then every single token gets mapped into a vector like this, 0.5, 0.3, 0.2, and then this vector represents the contextual meaning, the semantic meaning, the spelling, and so many different perspectives about this word. Then we pass it into a text encoder, then it understands the meaning of this text and pass this rich representation vectors with its understanding to an image encoder. Then the image encoder will take this and understand it and tries to generate the image using a diffusion model. So the main idea here, you can see we have text representation. Stable Diffusion converts a text prompt into a text vector representation, then image representation. Starting with random noise, Stable Diffusion refines the image representation little by little with the guidance of the text representation. Stable Diffusion repeats the refining over multiple time steps, for example 50 in our diffusion explainer. Then we have image upscaling. Stable Diffusion upscales the image representation into a high resolution image. And feel free to read through that in your own time, but this is the main idea of the diffusion. And you can see here we have this image of a giraffe, you can see, with top hat, okay, and it has here a tie. Okay, so that's it. That's how to use diffusion models in Hugging Face, Diffusers models, and how to generate images with a prompt using a text prompt, and also how to generate faces without any prompt using a denoising diffusion probabilistic models. And we have taught some skills on how to process images using the Python programming language ecosystem. Let's dive into another modality and section of this course, which is video models and how to use video models from Hugging Face platform. The first thing is, let's go and name this as video models. Let's import the required libraries that, for example, Torch, import Diffusers. The Diffusers library is a really important library in the world of video and images. Whenever you want to deal with video modality or video files or to generate videos using deep learning, you have to import the Diffusers library from Hugging Face. Then let's go import transformers, and then at the last import CV2. Now let's run that. You can see now it's importing those libraries, including Torch, Diffusers, Transformers, and CV2. The next step is that let's go ahead and name this as generating, start a new section as generating video with diffusion. So now let's take how would you generate a video using a diffusion model from Hugging Face. The first thing, let's go from Diffusers, import stable video diffusion pipeline. So here we have this class. You can see it's called Stable Video Diffusion Pipeline. Let's import this class from the Diffusers library. You can see now it's importing this class. And let's wait until the class is imported. You can see now the class is imported. The third step, let's go ahead and dive into it. Let's construct a new instance from this class by going pipe equals, and then let's call that class, which is called Stable Diffusion or Stable Video Diffusion Pipeline. Let's use that class and then pass into here. You can see dot from underscore pretrained. Let's call the method from pretrained and then pass stability AI slash stable dash video dash diffusion dash image to vid. So vid is short for video dash xt. So you can see here, this is the name of the model. Then let's set the torch underscore d type. So the data type of the torch should be as torch dot float 16. So why you have to set this parameter? If you don't set this parameter, you will get the error out of memory, because remember or keep in mind, videos are really large files and generating them isn't easy. So you have to change the precision of the numbers to be float 16. Okay, this is a really important setting you have to care about and you have to provide it. Otherwise, you will get out of memory error. Variant equals FP16. So short for floating point 16. And here, keep in mind, you have to write stability AI slash stable video diffusion, stable dash video dash diffusion dash image to video dash xt. Then let's go ahead and load this pipe. Let's run that. You can see now it's trying to load in our model. You can see the model is now loading. Model and index of JSON. It's now trying to download that model. So all we did is just call this class stable video diffusion and pipeline dot from pretrained and then pass in the name of the model, comma, torch d type as float 16, and then set the variant setting as FP16. Okay, like that. And then we have the model here, or the pipe. Let's now call the pipe to see it. Now this is the pipe. You can see here we have this stable video diffusion pipeline. We have class name stable video diffusion pipeline, diffusers version 0.36.0, name or path stability AI slash stable video diffusion dash image to video dash xt, feature extractor, transformers, clip image processor, and so on. Now let's go ahead and you can see here I have an image. I already have an image here called elmo.jpg. If you open it, you can see this is an image of Elmo. Let's take the copy of this image and paste it inside the variable called my image, or for example path equals elmo.jpg. So this is the path. This is the path of elmo.jpg image stored inside the variable called path. Run that. You can see a path is a string, a normal string, a regular string containing the word elmo.jpg. Now to show this image, let's go ahead and from diffusers dot utils. So inside the utils library or utils package, which is short for utilities, import the following. The first is load underscore image. So this function is really helpful. It's from the utilities library from within Diffusers. It helps you to load the image and show it. Then comma, we have this also function, export to video, to later export our video frames into a video. Okay, so let's from diffusers.utils import load image, comma, export to video, and let's go ahead and image equals. So here we have a path. Remember, we stored the path of the image inside a variable called path. Let's use this function, load image, and pass into here the path of the Elmo image. Now, once you write here the name of the variable image, we have a surprise. The Elmo image is loaded into the environment of Google Colab. You can see we have Elmo image loaded inside the Colab environment successfully without any problems. So the idea here, all we have done is from diffusers.utils import load image, comma, export to video. Then we pass the path to load image and we showed that image successfully. Here you can see we have an important setting that we have to do, which is pipe dot enable underscore model underscore CPU underscore offload. This is a really important setting that you have to use. This function, enable model CPU offload. You have to call this function on top of pipe. Why? Because to not get the error of out of memory, as you can see. So keep in mind, you have to run this code. This code is necessary. Then let's go ahead and dive straight away into how to use this model. First, let's set a generator equals torch.manual seed to set a manual seed to get reproducible results. So in order to get reproducible results, the same results, you and I have the same results, the same video frames, you should have to set manual seed as 42. So now we have a generator. You can see it's a normal torch.manual seed function set as 42. So feel free to play around with this value. You can set it whatever you want, but in this case, I will keep it as the regular normal seed 42. Now let's dive into the step of creating the actual frames by going frames equals pipe. So remember, we have created this pipe earlier. You can see here, pipe at the top here. We have here pipe equals the class that we have imported earlier. Stable video diffusion pipeline dot the method from underscore pretrained, and then pass here the information about the model. Now let's use this pipe and pass in my image, and then the model will work and produce a video and generate a video out of this image by going image. So pass my Elmo image. Here we have image. You can see it's an Elmo image. Let's pass it to our pipe, then comma, decode underscore chunk underscore size equals 8. So set the decode chunk size as 8. This is a really important parameter. You have to set it as 8, comma, generator, and then pass in my generator, which is, if you remember, our seed. Okay, dot frames at index 0. Why? Because this class will return a kind of object. We have to access the attribute frames and get the frames at the index 0. So this is a really important chunk or really important piece that you have to provide in order to get the frames straight away. Let's go ahead and run that. You can see now it's trying to generate an actual video out of this image, which is Elmo image. Now the model is working. You have to keep in mind, I went to runtime, changed runtime type, and then chose L for GPU. Otherwise, if you are working on CPU, it will take at least 40 minutes to generate a video. So keep in mind, you have to rent GPUs. You have to buy GPUs from Google Colab and then use L for GPU or A100 GPU or whatever GPU you have available. The more powerful GPU, for example, L4, A100, will take less than 1 minute to generate a video. But otherwise, if you are using CPU, keep in mind it might take at least 40 minutes. You can see here we have little nice progress bar showing us the progress of this model. Now this pipe is running behind the scenes a diffusion model. The diffusion model is the model that is responsible for generating pixels and generating the video frames from this image. So here only we are providing the image. We are not providing a prompt. Later in this lecture, we will see that we will use another model from Hugging Face. Then we will provide an image alongside with a prompt. Then the model will be able to generate a video. But here, this model, which is the default model here that we have used, which is called Stable Video Diffusion Pipeline, we have imported it from this library, from Diffusers import Stable Video Diffusion Pipeline. This model is generating a video out of a single image. We are not providing any prompt. And if you go to here and search Stable Video Diffusion paper, this is the real paper or the actual paper that introduced and proposed this model from Stability AI. You can see Stable Video Diffusion, scaling latent video diffusion models to large datasets on 25 November 2023. And if you go to view PDF, it will show us that here we have Stability AI. This is the paper that they proposed this model, Stable Video Diffusion. And feel free in your own time to read this paper at your own pace. But here in the abstract, they said, we present Stable Video Diffusion, a latent video diffusion model for high resolution, state-of-the-art text to video and image to video. Here we are using this modality, image to video. We are using this paradigm, converting an image into a video. But also you can use text to video. So you provide the text prompt, then it converted into a video. Recently, latent diffusion models trained for 2D images synthesis have been turned into generative video models by inserting temporal layers and fine-tuning them on small, high-quality video datasets. However, training methods in the literature vary widely, and the field has yet to agree on a unified strategy for curating video data. And if you go down, you can see they generated so many images and so many, you can see here, we have so many images and so many videos. These are video frames. So one frame, second frame, third frame, fourth frame. So this is a video, okay? You can see they provide one image, and then the model tries to manipulate that image and create many frames. Here the model has finished. You can go and show the frames. You can see here we have a nice list, whoa, containing so many images. And every single image is in the form of PIL. And if you don't know PIL, PIL is short for Python Image Library or Python Imaging Library. So if you wanted to access one of these images, you can go at index 0, then it shows us that image. You can see this is the first image of Elmo. This is the second image of Elmo. This is the third at index 2. The fourth image. You can see Elmo is going down. Every time Elmo is going down. Okay? And these are the frames. So feel free to play around with these images. Here you have a nice list containing of, if you take the length of it, here we have, how many frames do we have? We have 25 frames. We have 25 images, different images inside this list, and every single image represents a single scene, represents a single frame. Now let's go ahead and export it by going export underscore to video. Remember, from the utilities library or from the utilities package, we imported here a function called export to video. That will help us to export these frames into a combined video. It will combine these images into one video file and store it in your Colab environment. Then you will be able to download it and visualize it. So let's use that function, export to video. Then just pass in the frames, pass in the list, this great list of frames, pass it into this function, frames. Then we will, you have to name this video. I will name it as elmo.mp4. Then all we have to do is just set the FPS equals 7. So here, frames per second. This parameter is short for frames per second. So how many frames do you want to show per second? I want to show 7 frames per second. Okay? Now, let's open this section and 3, 2, 1, run the cell. And you can see here, when we refresh, we will get a video. You can see it's called elmo.mp4. Now let's click that video, double click, it will download that video automatically. You can see it takes a little bit of time, but no worries, it will download that in any time. Now let's click on that video. You can see this is a video of Elmo jumping up and down. You can see Elmo now is a video. Elmo isn't anymore one single image. It's now a moving video jumping up and down. Okay, so feel free to grab any image, to fetch any image of yours and try to pass it to this model. It's called Stable Video Diffusion, and you can see how easy it is to use it. Just in 4 lines of code or 5 lines of code, you have the ability to use a deep learning model to convert one image into a video. As they mentioned here, it's easy to convert one image to a video, or the second modality, text to a video. So you can see here, we have here 2 options: text to video or image to video. Now we have used this paradigm, image to video. We provide it with one single image, which is this Elmo image, a static Elmo. Then we convert it into a video using this pipe, our model, pass in the image, decode chunk size as 8, and then set generator as generator to get reproducible results, then get the frames at index 0. Then all of a sudden, all the surprise, you have a massive list of all those images. Then we tried to export it to a video, and it did that, and then we have a video here called elmo.mp4. Now let's go to Hugging Face. Here you can go to tasks or models, tasks. Then we have here multimodal, we have here computer vision, we have NLP, and we have audio. Let's go to here to multimodal. You have the option to convert image to a text. So image text to, it's called image text to video, or let's call it image to video. Yeah, yes, this is the option that I want to point out. Image to video, like we did. Here we have a plethora of models. You can see we have so many models. We have mountains of models. You can see 484 models, a big number. The first model is by Quark Vision, live avatar, updated 7 days ago. You can see it has 151 likes. Here we have also Stability AI, Stable Video Diffusion Model, image to video. And I believe if you go to sort and then choose most downloads, here the most likes, here Stability AI, Stable Video Diffusion, is the most model that has the most amount of likes. So if you sort by most likes, here the first model is the model that we have used previously, Stability AI / Stable Video Diffusion, image to video. And if you click on it, these are the images that they have made. You can see these are some videos. If you grab some earth image and pass it to the model, it will round that earth, make it moving. The same with the clouds and the sea. You can see we will try with the sea. We will try to pass an image of sea, and it will animate the sea and make the waves animating. And there we have these buildings. So feel free to play around with these models, to explore, experiment. Here we have use this model, Diffusers. So you can remember that previously when we clicked on use this model, it was here transformers. It was pointing out to transformers. But now, once we got into the models of video, Hugging Face automatically changes this option to diffusers. And you can see here we have diffusers library. If you click on it, it will show us a model. Then here is the guide on how to use this model. First, from diffusers, import diffusion pipeline. Then diffusion pipeline.from pretrained, pass in here Stability AI / Stable Video Diffusion. Then we have here a prompt, a man with short gray hair plays a red electric guitar. Then we have this image. So they provided here with prompt and image. Then the pipeline will work and produce output a MP4 video. Now let's get back to our notebook and complete our lesson. Let's jump into another topic here, which is generating video using another diffusion model, this time using image and prompt. So not only an image but also a prompt. Provide the model with the image and prompt by going import torch. Then let's go torch.cuda dot empty cache. Then let's call that function. You can see here we have empty the cache. So you have to empty the cache or empty the cache before you move on to the next step. Why? Because torch.cuda.empty cache makes sure that our CUDA isn't busy with any other task. Let's go from diffusers. From diffusers, import a function or a class called i2v gen xl pipeline. So what basically this class is short for? I image to video. So converting image to video generator or generation X large model pipeline. We need to import this class from the diffusers library. So from diffusers, import i2v gen xl pipeline. Then let's go ahead and here you can see from diffusers import .utils. So from the utility functions or from the utility library, please go ahead and import the following: load image, export video. And here you can see, oh, we used this function before. Load image is used to load an image. Export to video is used to let us export a video. So we've seen that before. Then we have to create a pipeline. Pipeline equals diff I, so image to video generator XL pipeline. So I to V generator XL pipeline. Then let's go ahead and pass into here dot from pretrained. We have to provide into here the repo ID. So this time let's store it in a variable called repo underscore ID equals ali dash vlab slash i2v. Its meaning is image to video generation or generator dash xl x large. This is my repo ID. So ali dash vil lab slash i2 video generator dash xl. Then let's pass here the repo ID. So instead of manually writing the repo ID here, what if we store it in a variable and use that variable? It will make your code a lot neater. Then you have here torch underscore dtype equals torch.float16. Please keep in mind you have to set it like that. Otherwise, you will get a out of memory error because, as we told you, we are dealing with video data, video modality, which is a really massive or intensive computing modality. When you compute on images, on videos, on audio, the model will be heavy in computing, will be in computationally intensive. So you have to lower down the precision to be float 16. If you use float 32, you will be out of memory. So we have keep in mind, make sure you are using float 16. Then let's go ahead and set the variant equals to fp16, floating point 16. Now let's run that. You can see now it's trying to download in the model, to load the model in, which is this model i2v generator xl pipeline.from pretrained. So as you can see, the progress bars are moving forwardly. Then let's go ahead and set the pipeline. So by going pipeline dot enable underscore model underscore CPU underscore offload. This function is really important because it will make sure that we are not getting the out of memory error. You have to enable model CPU offload. Then let's go ahead and here I have, you can see an image of C. If you open it, you can see we have now another image, which is a view of a C or an image or a picture of C. Let's now use this picture to generate a video using another model, which is this model from the repo ID. It's called i2v gen xl pipeline. By going ahead and loading the model as we did before, here we can go C equals load underscore image and then pass in my c.jpg. So all I have to do is just grab an image, store it over here, call the path of this image, pass it to this function, load underscore image, then you have to store it inside some variable. I called it C. If you now visualize or print out the C variable, it will show us that we have now a picture or a view or a scene of a C. You can see we have this image of a C. Normal image. It's a static image. Note that when we pass it to a model, it will animate that C. It will make this C be animated, moving. It's not static anymore. So by going prompt equals the C, for example, and you can be as creative as you want. So the C waves heavily. I will keep it simple here. You can feel free to prompt and to ask or to instruct the model as you would like. Here, I just told the model, hey, take this image and try to make the C waves heavily. You can get as creative as you would like here. But now let's go ahead and just set the generator equals torch.manual_seed as 42, then frames. So get back the frames. This pipe will return back a set of frames stored inside the form of a list by going pipeline and then pass in prompt equals the prompt equals prompt, comma, image equals C, comma, num frames. So how many frames do you want to generate? In this case, I want to generate 16 frames. Keep in mind, the higher the number, the more time it will take to produce that video. And the lower the number of frames, the faster the model will run to generate your video. So you have to keep it balanced. But if you have infinite amount of resource, and if you have infinite amount of computing, feel free to set it as to, for example, 164. But let's keep it simple and quick by setting this to 16. Then we have here generator equals generator dot frames, and then get or fetch the frames at index 0. So you don't have then to access it later. Here we are accessing straight away. Dot frames fetch at index 0. Now let the model run. So by the way, this model, which is called I2VGen XL pipeline, if you copy this name, go to Hugging Face. This is the Stability AI model. Don't forget, go to models and then filter by name. You can see we have this model I2V image to video. It's called this repo. You can copy the name of the repo from here. You can see this is the model, okay? So this is the model VGen. It's from Alibaba company -VI lab /I2 image to video generator -XL. You can copy the name from here. If you don't want to type it later, you can give it a like if you want. You can follow this account. Here you can see downloads last month. They have 2,729 downloads in the last month. Here you can see VGen is an open source video synthesis code base developed by Tongyi Lab of Alibaba Group, featuring the state-of-the-art video generative models. This repository includes implementations of the following methods, and you can read through that in your own time. But here the most important idea is, if you go down, they have here some guides on how to use this model. You can see from Diffusers, import I2VGen XL pipeline. So that's what we did before. And then you can provide it with image URL. You can provide this model with a, you can see image, then prompt. Papers were floating in the air on a table in the library. Then they provide the image. They supply the model with image and prompt. Then they pass it as we did. You can see frames. So this pipeline returns frames. They pass here prompt equals prompt. So as we did here, you can see if you go down, scroll down, here we have prompt equals prompt, image equals C, and they passed it like that. Image equals image, generator equals generator, then dot frames at index 0. You can see here, they did what we did exactly. We have here dot frames, and then they accessed at index 0. Then at the last, they export this frames into a GIF. In this case, we will export it into a video, and then they passed straight away the frames. Okay, so you have here plenty of explanations on how to use this model, how to use it. Okay, and this is the result. You can see papers. They ask the model to generate papers were floating in the air. So here you can see the papers are floating in the air, and also this prompt is really important on a table. You can see here on a table. So they have a table. So you can see how great this model is at capturing the meaning and the contextual meaning of the prompt, understanding the latent of the text, and then combining that understanding with a visual understanding of the image, and then using a diffusion model, they generated this great masterpiece of art. Okay, so feel free to go as creative as you would like. Now, the diffusion model, the first paper that introduced it was by Joshua Soldixon, which is titled Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. This is the original paper that introduced the model diffusion by Joshua Soldixon. You can see a central problem in machine learning involves modeling complex datasets using highly flexible families of probability distributions in which learning, sampling is another word or is a fancy word for generating, inference, and evaluation are still analytically or computationally tractable. Here we develop an approach that simultaneously achieves both flexibility and tractability. So all the models like VAE, GANs, and Boltzmann machines, they're all generative models, but they are intractable. But diffusion is a model that is both tractable and flexible, capable of modeling complex probability distributions, and at the same time, it's yet tractable. The essential data inspired by non-equilibrium statistical physics is to systematically and slowly destroy structure in a data distribution. So the way the diffusion model operates is it starts with a random noise. It starts with an initial random noise. Then it slowly during the training phase, it starts with the original image. Then it tries to destroy that structure in the image. Then at the inference time, it starts from random noise. Then it tries to generate this image, for example, a coherent and logically inspiring and logically appealing image. So it starts with random structure. It destroys structure in a data distribution through an iterative forward diffusion process. We then learn a reverse diffusion process that restores structure in data. So as I told you, during the training phase, the diffusion model starts with a logically coherent image. Then it slowly adds noise until it destroys structure in the image. Once the image is destroyed, there's no any meaningful logical coherence or there's nothing to infer from it. The diffusion model starts to redraw that image or to get how to do a reverse diffusion process to get to the original image. Then during the inference mode, the model is asked with a prompt to generate a new image or generate a specified image, and it starts from random noise. Then it tries to generate that image. And as we saw here with the Elmo video, we give it an image, then it tried to move and animate Elmo image. So these are all diffusion models and evaluate probabilities in deep generative models with thousands of layers or time steps, as well as to compute conditional and posterior probabilities under the learned model. We additionally released an open source reference implementation of the algorithm. And later, there's a paper by Yang Song, diffusion paper. Here you can see by Yang Song, the principles of diffusion model. So if we go to, this is Yang Song. Here we have score based. So Yang Song here, what he did in this paper with his friends, they avoided modeling the probability distribution by computing a score-based generative modeling through stochastic differential equations. So in this paper, which was in 2021, they avoided modeling the complex probability distribution. So it was submitted on 26 November 2020 and last revised 10 February 2021. Here in this paper, they proposed a way to avoid modeling complex and in high dimensional probability distributions via using a score-based generative modeling through stochastic differential equations. So you can see they have this. We present a stochastic differential equation, SDE, that smoothly transforms a complex data distribution to a known prior distribution by slowly injecting noise. So you can see here, by slowly injecting noise. The diffusion model operates by injecting noise and destroying that image structure, then slowly getting back and returning back, learning how to return back to the original image. And a corresponding reverse time SDE that transforms the prior distribution back into the data distribution by slowly removing the noise. Crucially, the reverse time SDE depends only on the time-dependent gradient field, aka score. So they named it as score of the of the perturbed data distribution. By leveraging advances in score-based generative modeling, we can accurately estimate these scores with neural networks and use numerical SDE solvers to generate samples. We showed that this network or this framework encapsulates previous approaches in score-based generative modeling and diffusion probabilistic modeling, allowing for new sampling procedures and new modeling capabilities. So feel free to read that in your own time. Here just we are giving an introduction to diffusion model and what is the core behind diffusion. So the core idea is that diffusion model is a generative model mostly used to generate videos and images. It starts with random noise and slowly building structure and coherent meaning in the image or in the pixels by reordering the pixels, by shuffling the pixels around. Okay, you can see it has heavy math. Then you can go down. You can see the fields. These are the gradient fields that the score. You can see an overview of score-based generative modeling through SDEs. And if you scroll down, you can see here they generated some faces using a diffusion model. Now let's get back to our collab. You can see now the model has finished generating. Now we have here frames. These are the frames stored inside the list. And if you wonder what is the length of the frames, we have 16 frames, 16 scenes, 16 images, as we have specified over here. So feel free to play around. And it's fun to play around with these values, to play around with the number of frames. Here the number is 16, the same as we did here. Now let's go ahead and export it by going export to video and then pass in my frames, comma, C underscore, name it whatever you would like. I will name it as C waves underscore dot mp4. Then let's go frames per second equals 4. So I want to show 4 frames per second. Here you can see cwaves.mp4. Let's go ahead and download that video. You can see it's a video .mp4. And these are the frames. You can see now the C is moving. It's now animating that image. It's no longer a single image. It's now an animating video animation. And you can play around this value, FPS, make it as 8. You can see now we will visualize 8 frames per second. And then download that video again. You can see it will show us 8 frames per second. Okay, now it's showing us 8 frames per second. So here we have reached the end of the video models. You can see we have used both modalities, using an image or a single image to generate a video, and also how to instruct a model via a prompt plus an image to generate a video. Keep in mind, Hugging Face has a plethora of models. You can go to models, then tasks, then choose here the task image to, you can see here we have image to video, and also we have here text to video, as we did. Here we have 863 models dedicated to the field of text to video. For example, Tencent Yuan Video. It has here a way on how to use this model, and here we have they have the model card. Okay, so feel free to play around with any of these models in your own time. But now we have taught you the way on how to use video models from Hugging Face. See you in the next section. Now in this section, let's dive into Gradio. Gradio library allows you to create graphical user interfaces for your machine learning models. So it enables you to create GUIs for your models. You don't have to worry how to create the front-end web development. Only you need to just to create a model, wrap it inside a function, then pass that function into Gradio library, and it will do all the job for you and create a nice front-end interface for you. The first thing is, let's name this as Gradio or Gradio, and then import it. Import Gradio as GR, then import torch, import numpy as np, and then from pil, from Python image library, import image. Then if you need to check the Gradio version, you can go with that, import Gradio, and then tab into Gradio dot underscore underscore version underscore underscore. So you can go Gradio dot underscore underscore version underscore underscore, and it will retrieve the version of Gradio. And currently, at the time of recording this video, it's 5.50.0. Maybe in the future you will see a higher number here, but it will work for you as we do here. So the first thing, let's go and deal with Gradio numbers. So how to deal with Gradio numbers? How do you create a number field or a number input in Gradio? We have to create a function, define, called add underscore numbers, and then pass in x comma y. Then all this function does is just return x plus y. So this function is a really simple function. It takes here x comma y, it takes two parameters, then it adds these parameters and returns them. So return x plus y. And if you call this function add underscore numbers and then pass 10 comma 20, it will add these two numbers and return 30. And if you pass here 50 comma 20, it will add them. So 50 plus 20, we will have 70. Okay, so it's a really simple function. Now let's create a Gradio interface by wrapping this function inside the interface class. So all you have to do is just define a variable iFace or interface, let's call it interface, equals Gradio.interface. Then we call the class interface. So you can see here we have the class interface. This is the most common class that you will use inside the Gradio library. It's the main class, the major class, interface. It takes from you three parameters. Fn, short for function, and as you can see, the function is add numbers, add underscore numbers, comma, let's pass in some inputs, equals a list. Here you can see we have two inputs. So if you have multiple inputs, you have to pass them inside a list. And then inside this list, let's define Gradio.number, comma, Gradio.number. So this function takes from me two inputs, x and y. And we have to provide two input fields. This is x and this is y. Then, comma, let's pass in our outputs equals Gradio.number. And this function also returns a number. So the addition of x plus y will be also here a number. So we have to return that as in the form of a number using the class number. You can see here n is capital number from the Gradio library. Now the last step is interface.launch. We have to launch it. So call the method launch to launch this interface and to have it ready. Now let's run that. You can see now it's preparing a Gradio interface and it will show us these inputs. You can see we have now x. We can type here whatever number you want. For example, 5 plus 10, submit. It will return here 15. And if you type here, for example, x as 10, y as 30, 10 plus 30, it will be 40. Okay? Feel free to try whatever numbers you would like. Here we have, it looks like you are running Gradio on a hosted Jupyter notebook, which requires share equals true. If you are running this code on a local Jupyter notebook, it will not give you this warning or this kind of information. But if you are running it on Colab, then you have to provide here the parameter share equals true. Then it will disappear. This info will disappear. Okay, so you can see 3, 2, 1, run that. This notification will disappear. You can see now it disappeared. Here we have another kind of info, Colab notebook detected. So now it detects that we are using Colab to show errors. If you want to show errors, if you have some errors here and you want to debug those errors, set debug equals true. But in this case, we don't have any errors. So this is a little notification. Okay. If you want to debug, just set debug equals true. In this case, we don't. Then here we have some kind of important information. This share link expires in 1 week. So we have here a live link. If you open it in a new tab, it will show the Gradio app. You can see here we have another interface, GUI, graphical user interface, using Gradio library or Gradio package. If you pass here 100 plus 200, it will be 300. Submit, you can see it works. Okay, so this link here expires in 1 week. For free permanent hosting, if you want to have a permanent hosting forever and GPU upgrades, run Gradio deploy, then you can deploy it on Hugging Face to Hugging Face spaces, and we'll see that later. So now let's go ahead and continue learning about what are the different capabilities and features offered by Gradio. Also, we can do the same thing by the function subNumbers, which subtracts numbers x comma y. Now we can go faster than earlier. Return x minus y. Here, this is a function called subNumbers. So subtract numbers. It takes from me two different numbers, x and y. Then it returns x minus y. Now let's go ahead and create an interface by going interface equals gr. So Gradio.interface. And as I told you, this is the main class, the most important class inside Gradio. It creates an interface, a graphical user interface for you, a user-friendly interface. Function equals sub underscore numbers, so the name of the function, comma, inputs equals x list, and then pass Gradio.number, and then Gradio.number. And we have also outputs equals Gradio.number. So it takes from me, it receives two different numbers, and it returns the subtraction of those two numbers in the form of a number. Now let's launch it, interface.launch. And then all you have to do is just run the cell. You can see now it's showing the interface. Here we have x. If you provide 8 and then y 4, 8 minus 4 we have here 4. If you provide 12, 12 minus 10 is 2, and so on. You can see how easy it is to create a really pretty web interface or front-end interface using Gradio. Now let's go ahead and do another task of dividing numbers. So div underscore numbers, and then it takes from me x comma y, then it return x divided by y. Then let's create an interface equals Gradio, so gr.interface, pass in fn function equals this function, div underscore numbers or div number, we can call it div numbers, then we can pass in here div numbers, comma, inputs equals a list, so it takes from me multiple inputs, x and y, equals Gradio.number. And then we have to put here parentheses or open and close parentheses. And also we have here Gradio.number. Then we can get some outputs by going Gradio.number. And then at the last, don't forget to launch it. .launch, start. Then run that again. You can see we will have another Gradio interface. And it allows us to divide different numbers. For example, if you have here x as 15, divide by 5, 15 divided by 5 will be 3. 3 multiplied by 5, it's 15, okay? So this is how to calculate or create a mini calculator using Gradio. Now let's go to the text. So what if you want to manipulate text or to deal with text? How Gradio offers us the text capabilities and how can we make the most out of it? We can go div and then name this function. I will name it as reverse text. So I will provide the Gradio interface with some text, and I need this interface to reverse my text. So provide here text, then it returns input text. We can call it input text, input underscore text. Then we can reverse it as colon, -1. So the most simple way or the simplest way to reverse any text in Python is just passing here square brackets, then colon, so start from the start and end at the end, but just pass here -1 to reverse the order. So if you have here some text, for example, Python, this is a normal text in Python, we can pass into here or index on it and then pass give me all Python. You can see here we have all Python. It's the same. Start from the start until the end, and then provide here another colon, then pass into here -1. So start from the start, and you can stop at the end, but start from the end. Okay, you have -1. You can see Python in reverse order. You can see Python, okay, in a reverse order. You can also pass here language. You can see language in a reverse order. Okay, so this function just receives some text and returns the reversed version of it. So returns the reversed version of my text. It's a really simple function. Now we can go reverse underscore function or reverse text, and then pass in some text. For example, I like Python, then it returns I like Python in a reverse version. Now to create a Gradio interface, we can do that easily by going interface equals Gradio.interface. So create an interface, then pass in here a function. So you need to provide the interface with a function to perform it. So you have some inputs and you need to create some outputs. Then what is the link? What is the linking process between my inputs and outputs? This function represents the linking and the connection between my x and y. Equals reverse equals text, comma, inputs equals a list of, so here we can pass here Gradio.text. So this time we don't need to pass multiple inputs, but rather just pass one text, okay? So Gradio.text. And you can see we can pass in some text later and it will be reversed. Comma, outputs equals Gradio.text. So we are setting the inputs as a text and setting the outputs as a text. Then we can go interface.launch. We can launch this app. And remember, we have a public URL here that will be expired after 1 week. Here you have some input text. You can see now we have input text. We can write, I really love the programming language Python. Then we can submit it and it will be here reversed. I really love the programming language Python. Okay, if you provide there some word, for example, the word machine, it will be reversed. You can see machine. Okay, so this is how you can create a Gradio interface to deal with text inputs. Now let's dive into Gradio sliders. How do you deal with sliders and the slider input or component? First, we have to go def and then define a function called slider underscore example and then pass in a value. Then return f. So let's return some string, formatted string as slider current value is. So let's just keep it simple and just return a string that is saying slider current value is as this value. So this function will be passed to interface, and then here we have some value. We inject this value inside this string, and then we are printing slider current value is value. Now let's go ahead and use that function. We can go slider underscore example and then pass in, for example, 20. Now it will return the text slider current value is 20. But if we want to pass it to interface Gradio, we can go Gradio or interface equals Gradio.interface and then pass here fn. So fn is short for function. Provide this interface with a function as slider underscore example. And note in here, you don't need to pass here two parentheses. Okay? Because why? You only need to execute this function when the Gradio interface is being displayed. So you don't need or you don't want to execute it when the interpreter reads that function. Then we have your inputs equals Gradio.slider, then pass minimum equals 0. So what is the minimum value you want to set as? Maximum equals 100. So that's up to you, whatever the minimum value you want to set, and the maximum, whatever maximum value you want to set. Then we have here step equals, for example, 1. Let's set it to 1. Then we have here outputs equals Gradio.text. Let's go ahead, interface.launch, so launch the app, and we can run that. Feel free to pass here share equals true to not display that notification anymore. So you can see we don't have that notification, and here we have a small info to show errors, set debug to true. But now we don't have errors. You can see we have now a slider. You can choose whatever value you want. Then, for example, 46. If you submit, it will return this text. Slider current value is 46. If you set it to 100, it will be slider current value is 100. And you can see now the step size is 1. So when you decrease, it will be decreased by 1, 99, 98, 94. You can see 93. But if you want to change the slider step, you can do that by resetting the step parameter, for example, into 2. Now you set it to 2, it will jump by 2 steps. It will increase or decrease by 2 steps. So you can see here, increasing by 2 steps. You can see 2, 4, 6, 8. Now the scale is increasing by 2. And also when you decrease, it will be decreased by 2. Okay? So now the range here is by 2s. Okay? So that's how to deal with sliders. Now let's move on to Gradio drop down menu. So how to create a drop down menu in Gradio. First, we need to define a function, as always, def drop down underscore example, and then pass in some value, then return f string current value, or current value is as value. And then let's go ahead and call it drop down underscore example, pass in some value, for example, the value Python. So I choose Python language. You can see current value is Python. Now let's wrap it inside interface Gradio, the Gradio interface, by going iFace equals, for example, Gradio.interface, so creating an interface, a GUI, then pass in a function equals drop down underscore example, comma, inputs. What are the inputs you want to input? For example, here, Gradio.dropdown. So the class here, you can see it's called dropdown. These are different components, are all available for us in the Gradio library. So the Gradio library has so many components. It has buttons, dropdowns, sliders, text boxes, number inputs, and so many components. Here we can pass choices equals a list called options. So this options list we have to create by going options equals a list. Then we can list here A, B, C. So here we have some options. For example, A, the option A, option B, option C. So for example, if you want to customize a hyperparameter, if you are hosting some machine learning model, then you have some different values for some hyperparameter. For example, learning rate. You set some different values, then you let the user choose whatever learning rate they want to use. This is one idea on how to use and leverage dropdowns in Gradio. Then we can go comma outputs equals Gradio.text. So it returns the text. Why? Remember, in this function we are returning what? Text. So you have to keep in mind what are my input shape and what are my output shape, and also how do you present your output and how do you present your input. And let's go ahead and then call iFace equals launch. So you can see this time I called it iFace. Here, because since we have just one input, we don't need to pass it into a list, although it doesn't produce any error. So let's run that. You can see options. Yeah, here I called it options and I didn't run that. You have to run this list, then run this list. So you can see this is my Gradio interface is being loaded. Here we have some drop down menu. You have A, B, you can switch to C, and then for example choose B, submit it. You can see current value is B. So you can see how easy it is to create drop down menu. You don't have to worry about the HTML, the CSS, the JavaScript to create these front-end web development. As they say in the tool Gradio here, and then go to the website, build machine learning apps in Python, create web interfaces. Web, you can see web is using HTML. So behind the scenes, there are some HTML files, CSS files, JS files are being run and loaded behind the scenes, and you don't know what's happening behind the scenes. So create web interfaces. for your ML models in minutes. Deploy anywhere, share with anyone. And you can see here down, they have everything you need to build. So they have so many components. You can see here, import Gradio as GR. Then we have greet, to greet someone, name, hello, plus name. Then you pass the function as we did, fn equals greet. This is a simple function like us. Then inputs equals text. We have a text input. You can write here, my name is Muhammad. Then submit. You can see the output here, hello Muhammad. And then the outputs here as text. So feel free to read here in your own time. You can see so many documentations as they have here, API. But let's now go to our notebook and complete the codes. Now, if you wanted to change, for example, here the options, you can do that easily by going A, change for example into Python, B, change it into PHP, and for example C, change into SQL. And you can run that again. You can see now our Gradio interface is being loaded, and it will show us the names of the Python or PHP. If you submit, you can see current value is PHP. SQL, you can see here current value is SQL, structured query language. Now the next step is, if you want to create Gradio image, how do you deal with images? Well, you can do that in easy steps. First, from pill import image, we have to import the image class, then def convert, and then pass in image underscore path. So this function will convert my image from a normal image, from a regular image, into a grayscale image, which is amazing. You can see load the image, and then we have image equals the image class dot open, and then pass in this function image underscore path. So we are receiving, this function receives image path, the path to an image. Then we are passing that image path into the open function. It will open that image and return a pill image instance into this variable. Then all we need to do is just go ahead and convert the image into a grayscale format by going return image.convert, the function convert, and then pass in L, capital L, to convert any image you would like into a grayscale image. Now, if you have here some images, I already have some images here. You can see I have this image of C, a picture of a C. We can pass this image, copy this path. We can pass the path of this image into this function. As you can see here, it's called convert. So we can say convert and then pass in my image path here. They ask for image path. We can run that. It returns an image converted into a grayscale image. You can see now the image is a grayscale. So to incorporate this into a Gradio interface, that's easy. We can go iFace equals Gradio.interface, then pass in the function that you want to execute, the function that you want to run behind the scenes. Here we have convert, comma, then we have inputs equals Gradio.image. So we have the image component, then pass type as a file path. So the type of this image will be a file path, a path to the image file. They have outputs equals Gradio.image. It receives an image and it returns an image, but in a grayscale format. Sometimes you will receive an image and return a label to classify the image. But here we are inputting an image and also outputting another image. Here you can see iFace.launch, then pass here share equals true to not to get that not to get that error or notification. Share equals true. You can see now it's loading a Gradio interface. Here we have drop image here. We can, for example, take this image and drop it here. Or we can go to Google, search for C images. Here you have a plethora of C images. We can, for example, take this image, go to Gradio there. You can see to the collab, drop it here. Now it's dropped, submit. Now we have a grayscale version of the image. So you can see here we are inputting a colored image. We have colors, submit it. Then we have a grayscale image converted successfully. So now you have a nice app, and you can also present it using this public URL. So running now, this app is being running on a public URL for a duration of 1 week. After 1 week, this link will be expired. So you can see here you have this app. You can drag any image. For example, if you search for flower images, this image, for example. If you go to here, drop image here. Now this is the image of a flower. Submit it. You can see now we have a grayscale image converted. Let's dive into Gradio JSON. So let's put a title here, Gradio JSON, and then let's define a function called number underscore details. So number underscore details to retain some details about a number. It takes from me, or it receives a number, and then you can see it creates a details dictionary. This dictionary contains several information and details about this number. The first information is original, and it contains the original form of the number, the same number. So the number that we pass in will be stored inside the key original, comma, we have the squared version of the number, which is number, then double asterisk 2. So we raise this number to the power 2. Then we have square root, where we take the square root of the number by raising this number to the 0.5 half. So if you raise any number to the power 0.5, then you are basically getting the square root of that number. And also at the finally, is underscore even, is the number even or is the number odd? In this case, you can discover that by going number modulus 2 and then equals 0. So you can see now we have a dictionary that contains several information and details about this number. For example, here, if you have the number 10, and if you put double asterisk sign, then 2, then basically you are raising 10 to the power 2. And then you have here 100. So you have 10 times 10, then we have 100, okay? 10 times 10. The same number, double, twice. And here we have square root, where you raise 10 to the power 0.5, then we have 3.16, and if you raise here 100 to the power 0.5, it will be 10. You are taking the square root. And also at the end, you have 100 modulus 2, then you have here 0. Does this equal 0? In that case, will be true. So this modulus sign, in addition to double equal sign 0, will return true or false whether this number is an even number or odd number. For example, 50 is considered an even number, it will be true. Whereas 51 is an odd number. So you can see here we have false, okay? It's a clever trick to return and discover whether this number is even or not. Then at the end, return details. As you can see now, we have a nice function, an amazing function that returns some information and details about whatever number. So you can call that number underscore details and then pass in, for example, the number 400. Then you can see it returns here some information. Original 400, squared 16,000, square root 20 is even true. If you raise here, for example, 20, you can see it changes dynamically based on what the number you provide to the function. Now let's go ahead and wrap this function inside a Gradio interface by going interface equals Gradio.interface and then pass in here fn equals number underscore details. This is this function, and then comma inputs equals Gradio.number. So remember, this function receives from me a number, a single number, then it outputs, so the outputs equals Gradio.json. Then at the end, let's go interface.launch. Let's launch this interface. Now we have this fascinating Gradio layout. You can see it's loading. Here we have number. If you, for example, input the number 70, submit, then it will return a JSON format data. You can see original is 70, squared 4900, square root 8.3 is even true. So you are returning some information, some really helpful and rich information about the number you are providing in. If you change it, for example, to 99, you can see submit. It changes based on the number that you are providing. If you input here 100 to see whole numbers, you can see here squared is 10,000, square root is 10, is even true, and original is 100. Okay, So that's it, dealing with Gradio JSON. Now let's go to the next step, where we will deal with another label. So the Gradio label. Labels in Gradio. So the label is the name of the class. So imagine you are creating a classification model and you want to classify into different categories. You will return then a label that labels whether this data point belongs to one class or another class. For example, you are classifying several different types of flowers, whether this flower is a red flower or a yellow flower. So let's define a function called classify underscore number. It receives from me a number, then it checks if condition. If number is larger than 0, then return positive. So that's it. If this number is larger than 0, if this number greater than 0, then return positive. Else if this number is less than 0, so this number is smaller than 0, then return negative. Else this condition is false, this condition is false, then basically return 0. So if none of these conditions are met, then at the end we do an else statement and then return 0. But if this condition has been met, so if number is greater than 0, return positive. If number less than 0, then return negative. So here we are basically classifying numbers into positive, negative, 0. Now let's go ahead and use this function. You can see here we have indentation error. So expected colon. So you can see here we have, here we need to put semicolon. Okay, you can see now we have a classify function ready to go. Let's go classify underscore number and then pass into here, for example, 50. 50 is positive, then it classifies it as positive. If we pass here -1, then it classifies it as negative. If you pass here -50, it will be as negative. But if you pass here 0, it will be classified as 0, and so on. So here we have a nice function that classifies into positive, negative, 0. It classifies and categorizes different numbers into these different categories. Let's wrap it inside the Gradio interface by going interface equals gradio.interface and then pass in the function fn equals classify underscore number. So we pass in the name of the function. We are taking the name of the function and passing it to the fn parameter. Let's insert an inputs here. Inputs equals a list or a gradio.number. Let's pass in just one number, a Gradio number component, comma, outputs equals Gradio.label. So the output here is a label. You can see now we are using the component label to label the class. Then let's go ahead and go interface.launch to launch our app. Run that, and you can see now we have this interesting layout is being loaded. You can see loading. Now we have a number. If you insert 80, it's a positive number and it will be classified as positive. You can see now we have a label. This is the label component. It's different from the text component. You can see here we have the text component at the top where you type something and it produces, you can see here, you insert some text, Python, then it produces some text. Okay, it's still within the text input. Here we have a label. A label is different. Here you don't have an input but a label, but rather a label. So you can put here whatever number, for example -5, then submit it. Then you have here negative, and if you pass here 0, it will be classified as 0, and feel free to try whatever number you would like. Now let's go ahead and dive into another component of Gradio, which is Gradio layout. So Gradio layout. So now basically we have finished, so congratulations, we have finished all the components, the most important and common components that you will use inside Gradio. If you go ahead and search here Gradio or Gradio components, documentation, then here you can see components. Here we have a great list, a massive list of all the components that you can use. So it's a huge list. You can see we have here introduction, audio, you can set some audio, bar plot, button, chatbot, checkbox. You can see you have clear button. We have here the dataset, datetime, and also you can see image that we have used earlier. So remember image, Gradio.image, where you pass in an image and then it opens that image. And remember we have specified the value here as, or the type here as file path, okay? Then you can also search here for whatever component you would like to use. Also here we have JSON that we used earlier. You can see JSON. Also here we have the markdown drop down menu, and feel free to explore that in your own time. But now let's go ahead and dive into the Gradio layout code. So now basically what we are doing is just creating components and throwing them straight away into this interface. But how do you lay out, how do you organize these items? How do you organize them and control the layout and the way of displaying these items? So rather than just displaying them in random order, why don't we just organize the way of displaying them, making them organized, neat, and a lot more beautiful way? So render it in a beautiful way by going with Gradio.blocks. So now you can see this class interface controls the rendering process. So interface is an automatic class that automatically sets the organization way of the items. So the interface is an automatic way. But if you want to use a manually created layout way, if you want to create layouts manually, you are the person who defines how to display things, then you would need to go ahead and use a with context in Python, Gradio.blocks, then open and close two parentheses as demo. Then we have here with Gradio.row. So create a row in this layout. So you can see here we have a class row. So now we are manually defining the layout. How do you want to display these items? Inside this row here goes whatever you want to put inside the first row. For example, the first thing is text1 equals Gradio.text, and then pass into here the value equals output1 or output1, okay? Then we have text2. We need to insert another text item equals Gradio.text, another text component, and pass value equals output2 with Gradio.row. So please insert another row. Please add another row here, a second row, and inside that row, go ahead and insert whatever item you would like. For example, text3 equals Gradio.text, and then pass in value equals our bottom row. So if you have bottom row, and then let's go ahead and do demo launch. So demo.launch. So here, these values are just really strings. You can define whatever string you would need to add. Now let's launch our app. Make sure you pass in share equals true if you don't want to get that notification anymore. You can see here we have this Gradio layout. And beautiful. Now we have two rows, you can see. Now you are controlling the way of displaying the items. See, we have two rows. The first row contains two text boxes. You can see here we have output1, output2. Then the second row contains a text box with bottom row. So here again we are instantiating a new instance of blocks by going with Gradio.blocks as demo. Then inside this blocks define two rows, row and row. Inside this row insert or inject two text boxes, and you can see them here we have two text boxes. They are siblings. Inside this first row we have injected two input boxes. Then we have inside the next row we have one text element that says bottom row. As you can see, now we have this beautiful layout being rendered in our customized way. Now let's go and move on to the next step. Import Gradio as GR with Gradio.blocks as demo. So you don't need to import Gradio again, but if you want to run this cell as the starting cell again, you need to import it again. So if you don't want to run all the cells later when you come back later. For example, after 1 hour and the runtime has disconnected, when you import from here, you don't need to run all the cells from above. You just start from here, okay? With gr.blocks as demo, let's go ahead with gradio.row. So insert a new row. Then inside this row, insert text1 equals gradio.text, and then pass in value equals output 1. And then we have here text2 equals gradio.text. So insert a text component and then pass here a value equals output 2. Then we have here with Gradio. So with Gradio, so with is a context manager in Python. With Gradio.row, it manages the context. Then text3 equals Gradio.text, and then pass in the value as bottom row. Let's go ahead and demo.launch to launch that app. And here you can pass share equals true or without it. You can see now we have this Gradio layout is being displayed and rendered for us. You can see we have 2 rows. The first row contains 2 text boxes. The second row contains 1 text box. And you can see this because the first row contains 2 distinct text boxes. It shares the spacing between them. So you can see these are equally spaced. Whereas the second row here contains 1 text box and it spans across the full width. It reaches the full width of this row, okay? It takes up to the full width. It fills the full row. Now let's go ahead and add another code cell and also explore some more different options with Gradio.blocks to customize our layout. So here we have to go with gr.blocks as demo. Let's go ahead and add with Gradio.row. So add a new row. Then inside this row, note here we have a new column with Gradio.column. So here we are adding a column now. Sometimes you don't need it doesn't necessitate. So in some cases it doesn't necessitate to add a new column. But in this case, you will need to add a column. Then inside this column, text1 equals gr.text, and then pass into here value equals row 0 column 0. So this is the row 0 col 0 dash component 1. And as I told you, in some cases it doesn't necessitate to add columns. In some cases it will be necessary. In case you need to add columns, note we are adding the columns inside the rows. So first you start by adding a row. Inside the row you add columns, and you cannot swap that order, okay? Then we have here text2 equals gradio.text, and then insert some value here as row 0 column 0 dash component 1 or component 2 here, okay? So here we have component 1, the row number 0, the column number 0, but component 1 and then component 2. After this column, let's add another column with gradio.column. So note the C here is capital. It's a class. It's called column. Inside this column, go ahead and insert a text3 component equals gr.text, and then pass in a value parameter, and then specify row 0 column 1. Then after that, let's add, so you have to de-indent here 2 times to get rid of this row context manager, and then add another row. So with Gradio.row outside the scope of this row. So here we have this row scope. Inside this scope we have 2 columns. Inside the first column scope we have 2 text components. So you have to be careful when you space into the columns, the rows. Inside this column scope we have 2 text components. Inside the second column scope we have 1 text component. Then let's create another row and insert here text4. So without inserting any column, gr.text, and then pass here value equals bottom row. And you can see here the flexibility here. Not when you add 1 column inside 1 row, you don't need to add columns inside the next row. So it's really flexible here. The way you organize it is up to you. You are the person who is responsible for displaying how is your Gradio layout is being rendered and displayed to others. You define the columns. Inside these columns we put components. These columns are inserted inside rows, and not every single row needs to contain columns. Maybe there are some rows that doesn't contain any column. Now let's go ahead so you can see the flexibility and how easy it is to construct layouts. So you can see now that we have a layout, and note now we have columns. So now we have one row. Inside this row we have one column. This column contains two components, so component 1 and the component 2. Here we have another row. You can see bottom row. So you can see here we have one row, inside it two columns, column. The first column contains two different text boxes. The first column contains two different text boxes. The second column inside the first row contains one text component. And then the second row contains one text component, and it takes up until it fills the full width. Until it fulfills the full width. Okay. Now let's move on to the next step with Gradio.blocks as demo. Let's go ahead and insert here a row. So with gr.row, insert a row here, and then we have with Gradio.column. And note here the two columns, you can notice that the two columns here are taking the same amount of spacing. They are taking the same amount of width. You can see they are equally spaced. Whereas if you want to differentiate or to assign different width scales, you can do that easily by passing here a scale parameter. So you can go scale equals 2. So here we are scaling this column to take up 2/3 of the width. And then text 1 equals Gradio.text, then pass in value equals row 0, column 0, dash component 1. Then we need to insert another text component by going gr.text pass value equals row 0, column 0, dash component 2. And this column is taking scale parameter equals 2. Let's now insert and add another column by going with Gradio.column. Let's go ahead and insert the scale parameter equals to 1. So this column will take just 1/3. You can note here 1/3. This column will take here 2/3 of the total width. Okay. Then inside this column context manager, let's insert text 3 equals gr.text and pass in value equals row 0, column 1. Then outside of this row scope, let's add another row by going with gr.row and then pass in here text 4, or add text 4 equals Gradio.text value equals bottom row. And then let's launch this app and see how this differs from the previous app. And remember to pass share equals true. So you need to make sure that you pass in share equals true. You can see here. Now this column takes up to 2/3 of the total spacing. If you go up, scroll up here, you can see here the difference between that layout and this layout. This layout, the spacing is shared. The spacing is distributed equally between these two columns. The spacing is distributed equally between them. But here, the spacing is 2/3 of the space is inserted to the first column. 1/3 of the space or of the width is inserted to the next column. And you can see how the difference between that. All that just with one parameter. Scale equals 2, scale equals 1. You can see how easy it is to manipulate and to play around with the layouts. It's actually quite fun to play around with layouts in Gradio. Now let's go ahead and do some more complex layouts by going with gr.blocks as demo. Inside this blocks, you can see first we instantiate a blocks object and insert an alias name via as demo. So adding an alias name, then with gr.row or .tab. Now let's add a tab. So here we have the tabs, tab, and then we have tab 1. So this is the first tab. Actually, you can insert tabs in Gradio. Then we have here with Gradio dot row with Gradio dot column. So inside this row, let's add a column. Inside this column, let's insert text 1 equals Gradio text, and then pass in some value equals row 0, column 0, dash component 1. Then we have text 2 equals Gradio dot text, pass in value equals row 0, column 0, dash component 2. Let's go ahead and insert another column with gr dot column, and then add another column. Inside this column, let's insert text 3 equals Gradio dot text, and then insert a value of row 0, column 1. And after this column, let's add, so outside the scope of this row context manager, let's add another row, you can see. And then inside this row, insert text 4 equals Gradio dot text, and then pass in value equals bottom row. At the last, let's add another tab. So you can see here, outside the scope of the tab class here, the tab class of the tab object, let's add another with context manager with Gradio.tab, and then pass in here tab 2. So you'll see how nice it is, these tabs. These tabs are really nice. They organize the display of the items. Text, but then with Gradio.row, let's add a row inside this tab, Gradio.text, and actually you can add here columns, but let's keep it simple. Text, and then pass here welcome to the new tab. Let's go ahead and run that demo by getting demo.launch. Every single Gradio run, you have to launch the demo. Okay, and then pass here share equals true. Let's run that. You can see now it's running. Now it will show us the layout. You can see the layout has shown up. Here we have tab 1. You can see we have one row. Inside this row, it contains two columns. The first column, the second column. The first column contains two text components, and you can see that the spacing is distributed equally between these two columns. Then you have the second row. In the tab 2 here, we have just one row that contains this text box, welcome to the new tab. So these tabs are really nice to organize and to make the display neat. Here we can also insert column equals scale equals 2, and here we can insert a parameter scale equals 1. Okay, now if you go to tab 1, you can see here the spacing is distributed equally. When you run that again, you can see this column will take 2/3 of the space. 2/3. And if you swap the order, you can do that easily by going 2 and here 1. So feel free to customize your layouts whichever way you want. Okay, you can see this column takes 2/3 and this column takes just 1/3, even though it contains two components. So we can also use so here the name of this is called as, let's name it as Gradio demo tabs. Okay, these are the tabs that we add to a Gradio. Okay, now let's move on to the next step, which is the idea of using a Gradio blocks and then adding an accordion. So how do you add an accordion? Yeah, Gradio accordion. How do you add an accordion into a Gradio and insert a new component inside an accordion? So let's go with Gradio.blocks as demo. Let's go ahead and Gradio.label and then insert here label here. So you can add a label here. After this label, let's go with Gradio.accordion. So you can see the accordion object or the accordion component uses this with keyword. So you have to add with keyword in Python, Gradio.accordion, and then pass into here accordion here, comma, open equals false. So if you want this accordion to be opened by default, you have to pass in here true. And if you want this accordion to be closed by default, pass in here false. And that's up to you. And then we have here gr.image. So inside this accordion, we want to open an image object or image component. Let's go demo.launch. You can see here it's trying to load in the layout, and it will have an accordion object. You can see accordion here. You can open it, close it, and if you open this accordion, we have this drop image here. You can open our images, choose Elmo. You can see here we have Elmo image. Okay, it's trying to load that. So inside this accordion, if you close it, it will be closed. Open it, it will be opened. And remember, we have a nice little parameter called open. If you pass here true, it will be open by default. So this accordion item is one of my favorite items in Gradio library. You can see now it will be opened by default. Okay, choose image, flower. It's loaded successfully, and you can close it if you want. Okay, and that is accordion. Accordion is one of the most important items inside Gradio, and feel free to go to documentation to refer back and reference some more opportunities and some more option ways to use that. So you can see here methods. They have expand if you want to expand it. Description. This listener is triggered when the accordion is expanded. So you have also a listener that could execute some code when the accordion item is triggered. When it is motivated and opened, you can trigger some code to be happened and to be executed. We have collapse, so the collapse event. We have description. This listener is triggered when the accordion is collapsed, and feel free to play around with that in your own time. It's actually quite fun to play around with Gradio. So you can see how easy the syntax is of Gradio. Let's go to Gradio buttons. So how do you add buttons using Gradio? The first thing, let's go with Gradio.blocks as demo. Let's go ahead and insert here some buttons by going gr.button and then pass here button component 1. Then we have here gr.button and then pass here button component 2. And also we have here Gradio.image. Then after that we have Gradio demo.launch. Okay, so we can launch our app now. Pass in here share equals true to be able to share it on a public URL. Then you can see now it's loading our layout, and now it contains some buttons. So you have button component 1, button component 2, drop image here or click to upload. You can click here and upload whatever image you would like. You can see now we have an image. Currently, these buttons, when you click on them, they will not do anything. In later section, we will learn how to make these buttons work. Okay. Now let's move on to next step. Next, how to insert some CSS into Gradio. That's easy. We can go ahead and Gradio CSS, put a nice little name here. Then let's go ahead and create some CSS. We can go CSS variable equals, and then insert 3 double quotation marks. So we need to add 1, 2, 3. Then also close by 3 double quotation marks. 1, 2, 3. Inside these double quotation marks, let's add dot your class, for example. Here you can name your class whatever name you want. Then let's go ahead and open and close parentheses. Inside these parentheses, add whatever custom CSS you would like. CSS is short for cascading style sheets. Let's go ahead and insert some height property. So the height attribute as 1000 pixels, comma, background, dash color, and then set it as, for example, red. You can customize whatever codes you would like. Then let's go with Gradio.blocks and then add here CSS equals CSS. So insert the CSS variable inside the parameter or as a value to the parameter CSS as demo, and feel free to name this variable whatever you want. I will name it, in this case, for example, my own demo. Then let's go ahead and with Gradio.row and then element underscore classes. So this is a parameter called element underscore classes, and then pass in square brackets, pass in the name of the class, in this case your class, and then let's go ahead and add Gradio.image as a component inside this row by going ahead and setting the height as 900, width equals 20. Now let's go and demo, or my own demo in this case, my own demo dot launch, and then pass here share equals true. Now 3, 2, 1, run that. You can see now we have a custom CSS code that will run. Now this is the layout, it's being loaded. You can see now the height is longer. So you might not notice that, but you can see the height here. Before, it wasn't that height. But here now we have a much longer height. You can see the scroll now. You can go down further. And then we have a background as red. You can customize whatever CSS you would like. For example, changing the background red as yellow. It will change it to yellow. It's all up to you. The custom settings, the custom modifications that you want to apply to your custom layouts. Here we have def multiply. Now, what if you want to actually make these buttons work? How do you trigger some code when you click on a button? How do you execute some code when you click on a button? That's really simple by going ahead and defining a function. For example, multiply. So def is short for define a function called multiply, pass in x, y, then just returns x times y. This is one of the most simplest functions that we have created. If you write multiply and then pass in 5, 5, it will just multiply 5 by 5, 25. If you pass here, for example, 10, it will be here 50. Let's wrap it inside Gradio interface by going with gr.blocks as demo. So instantiate a new instance of the blocks class as, and store it inside the alias name demo. Go ahead and create a row to organize our display, and then create two sliders. Now we have two events. The first event is called here change event. So you want to trigger some code in a change event or during a change event. So basically we have two different types of events. If you go here and right here, there are two different types of events. We have one click events, and we have two change events. Let's start with change events. So the first thing is change event. How do you trigger code when you, for example, change a slider value? X slider equals gr.slider and then pass nothing. Then you have here y underscore slider equals gradio.slider. So here we have two different sliders. How do you trigger some code whenever you change change event, whenever you change the value of the slider? And then we have here with gradio.row, add another row, and the result, this row will contain the result equals gradio.text. Then let's go ahead and here add y underscore slider dot change. So let's trigger some code when we change the value of the slider. Here we are applying this event upon the y slider, okay, not upon the x slider. You will see later, I will tell you that x slider will not, when we change it, it will not trigger any code. Whereas y slider, when you change it, when you play around with this value, it will trigger this code that I'm about to write into here. Fn function equals multiply. So here we are saying, hey, please, y slider, when I change your value, execute the code, multiply, and then take the inputs as the following. You can see here inputs equals a list of two numbers, x slider, y slider. So multiply the x slider value by the y slider value, then go ahead and just display the outputs as the following: Gradio or result. So we have to pass in result. This result variable contains gradio.text. Okay, the output will be in a text form. Now if we go ahead and just app or demo dot launch. So as I told you, you can feel free to play around with this name. It's called now demo. I can change it to app and it will work successfully. you can set share equals true. Now we will have a really exciting app where you can see here, when we change the X slider, okay, the code doesn't get triggered. So feel free to change that, nothing happens. But when you change the Y slider, Gradio will work and it will execute. So there's a hidden listener that listens for this event, the change event, and whenever you change the value of this, so it multiplies 15 by 42, you can see here we have 630. If you reduce this value by 10, now 15 times 10, if you change this, 15 times 10, here we have 150. Okay, so whenever you change the value of the Y slider, there is a hidden listener, there is a latent listener that listens for this event and tries to execute this code, multiply, so this function, this nice function, it will be executed whenever you change the value of the Y slider here, Y slider to change, pass in the function multiply, pass in the inputs X slider, Y slider, multiply the Y slider value by the X slider value, and then return the output in the form of a result, which is a Gradio text, a normal, regular Gradio.text, okay? And you can see here, this app is fully working. It's a multiplication app that multiplies the Y value by the X value. Now let's go ahead and apply some more examples to practice more. Here we have with Gradio.blocks as demo. Then let's go ahead with Gradio.row, add a new row or insert a new row. Then we can go X slider equals Gradio.slider, and then pass in label equals X, and then also we have here Y slider equals Gradio.slider. So a slider is a component inside Gradio, which is a normal slider that you can slide and change the values. Then we have label equals Y. Then we have another row that displays the value, displays the result by going result equals Gradio.text, a normal text input. Then here we have X slider. So now let's step things up and apply the listener not only to the Y but also to the X by going X slider dot change. So execute a change event listener, pass in the function as multiply, comma inputs equals a list of two inputs. So here we have X slider, comma Y slider, and then at the last finally we have outputs equals result. And here we have to insert equal sign. And also here the change event will work on the X slider. Let's do the same on the Y slider by going Y underscore slider dot change, pass in function as multiply. You can see how fast we can go here. Inputs equals X slider, comma Y slider, and then we have at the last here outputs equals result, that we have the same component for the row, the second row. Here you can see multiply, okay, X slider is called X underscore slider, okay. Now let's run that after we launch this demo by going demo.launch, launch our app, and then pass share equals true. Run that. Now when we change the value of X slider, it will multiply its value by the Y value. So we have here, if you multiply, you can see now whenever we change the value, it will execute, and it's multiplying 13 by 0, it's 0. So here the Y is always 0, so the result is always 0. Remember, when you multiply anything by 0, the result is 0. Now let's change the value here, make it for example 3. 3 times 13 is 39. And when we change the value here, for example here, 2 times 2 is 4. If you increase that, 2 times 3 is 6. Okay, and whenever you change the value of Y, it will display a different result. Let's go ahead and dive into another example where we have the button and click. So now we have click event, button, click, triggers code. So when you click on a button, it triggers some code. With Gradio.blocks, so let's create another blocks as demo or as app. Let's go ahead and insert a row. Inside this row, let's add a text x slider equals gradio.slider, and then pass in the label as x. Then let's also create another slider by going y_slider equals gradio.slider, and then insert the label as y. Then we need another row that shows us the output by going result equals gradio.text, that shows us the result of our multiplication process. Then we have here with gradio.row, insert a button. So you can see now we need the button element by going button equals gradio.button, and then insert here multiply. So put a catchy and also motivating text here to let the user, or to motivate the user to click on the button. Okay, then we have button here dot click. Now you can see we are using the click function to execute some code that will be triggered once you click on the button. This code or this function will be executed. Pass into here multiply, comma, inputs equals a list of x slider, comma, y slider. Then we have here outputs equals, so the outputs equals here one value, which is the result. Okay, now let's go ahead and just launch our app by going demo.launch, and then pass into here share equals true. So all we're doing here is just we are creating some rows. The first row contains two sliders. The second row contains one text component. The third row contains a button that contains this text multiply. It motivates the user to click on this button because it labels multiply. Then we have a click function that will execute this function multiply upon the clicking event. So when you click upon this button, it will run this function multiply with inputs x slider, y slider. It will take these values and multiply them with each other. Then it will render the output at the result component, which is the normal text. You can see here we have x slider. We can see when we play around with these values, it doesn't run anything. And the y also, when you run here we have some values. Now let's go ahead and multiply. It will multiply these values and give you the result. So when you specify, for example, here 4, here for example 6 times 4 is 24, and also change here for example 3 times 4 is 12. Okay, so this is how to execute some code upon the clicking event. Now let's create an app that takes one input and returns multiple different outputs. So let's write returning different outputs. Here the first thing that we need to add, or we need to create, is the idea that creating a function called make_grayscale. This function takes from me image_path, and then let's open the image. So open the image. Let's go image equals image class dot open, and then pass into here image_path. Then let's go ahead and convert the image to grayscale format, and let's go image_grayscale equals image.convert, pass in L. Then let's return image_grayscale, comma, a text output called image converted. Let's run that. You can see now this image, when you pass in some image, for example make_grayscale, this function, it takes from me an image path, then it returns image converted into grayscale, comma, string. So let's go ahead and pass here some image, for example the C image, copy path, pass it to our function make grayscale. It will return back a tuple containing a pill image and the text image converted. Let's unpack that into two variables. We have the gray image, comma, log, the log. Okay, here we have two variables. The first variable is image gray image. You can see gray underscore image. It's now a gray image. You can see a gray image, the same variable here. And we have the log variable that contains the text image converted. Okay, so here we are dealing with multi-modalities. Let's now wrap that into a Gradio interface by going with gr.blocks as demo. Let's go ahead and create a new row with gr.row, and then inside this row let's insert input image. So we need to add an input image equals gr.image component then pass into here type equals file path, and then we have also output underscore image equals gradio.image, insert an image component and let these parentheses empty. Let's go ahead with gr.row, pass inside this row log equals gradio.text, then inside this text leave it as it is empty. Then let's create a submit button equals gradio.button, and then we have here value equals convert to grayscale. So this is the call to action of the button that you need to make it motivating and catchy in order for the user to click it. Then we have here submit dot click. Then we have here fn equals make underscore grayscale. This function, remember, takes from me one input and returns two outputs. Then we have here inputs equals input image, input underscore image. Then we have here outputs equals a list of output underscore image, also comma log. So the log. Okay. Then we have here demo underscore launch, and then pass here share equals true. So the log is the status, and it's simply this text, which is image converted. Let's launch my app. You can see here we have a Gradio app now running. We have a drop image here. Let's choose the image of Elmo. Let's choose it. You can see now it's loading. Here we have Elmo. Let's click on convert to grayscale. It will return here this text image converted, and in addition to with this image of Elmo converted into a grayscale image. So here we have multiple outputs being returned, and this is the idea of returning different outputs, taking in one input and returning different outputs. Let's dive into Gradio themes to change the theme of a Gradio layout using some of the available themes on the Gradio list. We can go help and then pass in gradio.themes to check what are the different themes that we have. You can see now we have a massive output. If you scroll up here, you can see all the available themes, the names of the themes that are available for you to check out. You can see here, these are the themes. We have the glass theme, monochrome theme, ocean theme, origin theme, soft theme, and the color. Now let's go ahead and try some of these themes. We can go def echo. So this function will just echo what we pass into here, text or num. Then it returns. Let's make it num, better than text. Then let's return num. So we pass in 5, it returns 5. If you echo 6, it returns here the number 6. Then let's go ahead and then iFace, create an interface that will be gradio.interface to instantiate an interface object. It takes from me fn equals echo, the function echo, inputs equals gradio.number. It takes from me a number and it returns to me a number. It does nothing but returns the exact same input that we have passed in earlier. The theme, now we can see we have a new parameter here, theme equals gradio.themes.glass. So we have a glass theme. Let's try it. We can go ahead and run that. After we launch this interface, we can go interface.launch. Then set share equals true. Now the layout is being loaded. You can see now we will have a brand new layout. You can see the glass theme. Here we have number 5. Then submit. It will submit the same number, but with a nice, beautiful, pretty theme. Okay, the glass theme. We have also different options. If you want to try them, we can go ahead and copy this code, the same exact code, so we don't rewrite the code, duplicate it, and then change the theme to soft. Okay, so all you need to do is just change the theme from glass to soft, and then see the magic happens. You can see now we have a soft theme. different than what we have earlier. You can see here the theme, this theme. Okay, we can pass in 10, then it will submit and return just 10. Echo it. Then let's try the last theme here, which is called also monochrome. Monochrome. Also, it's a nice theme. You can see it's an exciting theme. We can pass in here 40, submit. It submits and returns 40. Okay, and feel free to play around with different themes. Also, you can use the different method, which is gradio.blocks, setting a blocks as demo. Then we can go and create a new row by going with gradio.row and then append into here gradio.number. Here we can pass inside the blocks theme equals gradio.themes.monochrome. So we have two different methods, remember, to create a layout. We have the interface class, the automatic interface class, and also we have this manual way of constructing the layout. Here, in this way, also you can play around with themes by passing the theme parameter to the blocks class. So rather than passing theme parameter to the interface class, we can pass this theme parameter to the blocks class. You can see here, like that. Then we can call this demo and then launch the app. You can see now we have a monochrome theme, okay? Just with one input. Let's dive into another topic, which is Gradio integration with machine learning. Integration with machine learning. So far we have building layouts, but without incorporating any machine learning into the pipeline, into the process. Now let's have machine learning. From transformers, import auto image processor. So we have this class, which is called auto image processor, and this class is used to process an image to be able to pass it into the ResNet model. We'll use ResNet model. Then we have here comma auto model for image classification, to classify different images, for image classification. Let's go ahead and use that. First we have the processor equals here our instance from the class auto image processor. Then we can dot from underscore pretrained. So from the pre-trained model, which is Microsoft / ResNet - 18, so 18 layers. Here we can load the model into the processor instance. Then we have here model equals auto model for image classification dot underscore from underscore pre-trained, and then pass into here Microsoft / ResNet - 18. So this model you can search on Hugging Face, and you can find it on Hugging Face under the name Microsoft. Go to models, then search, filter by name. You can see here we have Microsoft ResNet 50 and also ResNet 18. You can see here the model card on how to use this model. Transformers, you can see from transformers import pipeline, or from transformers the way that we used from transformers import auto image processor, comma auto model for image classification, and then from pre-trained pass in Microsoft / ResNet 50 or 18, and we have from pre-trained pass in Microsoft / ResNet 50. And you can see here we have the ResNet architecture. You have residual connections. This is the residual architecture. This is the plain architecture, and this is the VG19. They compared it to the VG19. And keep in mind, this architecture is used to classify images. So let's go ahead and load that model in. Now the next step is to visualize the model architecture by printing the model, and you can see the architecture of the model. Here, if you search for ResNet model architecture, you can see a plethora of images on what is the residual net. You can see here the residual neural network. This is the main idea behind ResNet. The main novel idea that they have proposed in this architecture is the residual connection. The residual connection makes the neural network training more stable, and also it eases the flow of the residual. So it eases the flow of the data It makes the flow of data more stable and easy without any degradation in the performance. And you can see the idea here is incorporating the input to the layer into the output. And if you search here, ResNet paper, you can see deep residual learning for image recognition by Kamiki et al. This is the most cited paper in the world by 300 above 1,000 citations. You can see here, view PDF, and scroll down. Here we have the image, the same image, basically in the Hugging Face platform, the residual connections. Now I think our model is loaded. We can show its architecture, and this is our architecture. You can see we have now ResNet stage, sequential, ResNet basic layer, identity. So they are preserving the identity of the layers. ResNet convolution layer, convolution 2D, batch, normalization layer, ReLU. You can see they have so many layers. It's going deep. You can see they have deep layers. And the main idea is that they are using here ResNet shortcut. Now let's move on and use this model into our Gradio interface. The first thing is create a function called classify_image. This function takes from me an image. It receives an image. Then we need to process that image. So in order to use this model, we need to process our image and make it compatible with our model by going ahead and image equals processor that we have created earlier. By going processor, then pass in our image, comma, return underscore tensors equals to PyTorch to set the form of the return tensor should be in the form of PyTorch. Let's go ahead and access the key pixel underscore values. Then let's go ahead and do the next step, which is passing our image to the model, and then it returns logits. Keep in mind, any classifier in the world would return logits, and you have to select or choose the most highest value of these logits, and this is the predicted class. Here we have 0 to 1000 because they are trained on, this model is trained on ImageNet, consisting of 1000 different classes. Here we have logits equals model. So let's use our magical model and then pass in our image dot logits. So get in the logits. Then we have here grab the index of the largest value or of the highest value between these logits. Probability. So here we have so many probabilities. We need to select the highest probability value by going ahead and predicted underscore label equals logits.argmax, and then pass in here -1 dimension -1 dot item to select that singular item, then return model.configuration dot id to label. So just index and on this list id to label. Basically, if you go ahead here and then tap into model.configuration dot id to label, so map the id into a label, it's a huge dictionary or a huge list. You can see here all the different classes and categories and groups that are existing inside ImageNet. We have tench, we have goldfish, great white shark, tiger shark, and so on. There are 1000 different classes here inside the ImageNet dataset. Let's go ahead and pass in our predicted underscore label to get the predicted label. Then let's go ahead and just run this function. This function will help us to use our model and go ahead like that. Now let's interface equals gradio.interface. Let's create and construct a new interface. Let's pass in function equals classify underscore image. Feel free to name it whatever you want. Then we have the inputs equals gradio.image. This is the image component, comma, outputs equals gradio.label. So keep in mind, this is a classification model. It receives an image object and it produces a label for which class this image belongs to. Then we have here the description, nice little description that describes what this model does by going description, upload an image. Then let's go ahead and launch that straight away. You can see now we will have a Gradio demo app that is capable of predicting or classifying the image by just passing here an image. So here we have an image, an area to pass an image, then we can submit and then classify it. And keep in mind, there is a public URL that will expire after 1 week, but now we have 1 week available to use this URL link. Let's go ahead and search for BERT, for example, images. bad images. Here we have plenty of birds. Let's select one of them. Let's copy that image or grab that image. Go to Gradio, drop it there. Then let's submit. It will classify here as BERT. BERT. Okay. Let's go ahead and, for example, grab another image of shark image. This is a shark image. Let's go here. Gradio, submit. You can see here, great white shark. Nice. And the last, let's search here, volcano image. You can see here we have volcano image. Let's get rid of this image. Pass in the volcano image. It will classify it as a volcano. And hooray, here we have volcano. So you can see Resident now classifies that image as a volcano image. Now let's move on to the next step. Now you can see how easy it is to build Gradio layouts or to build Gradio apps incorporating some state-of-the-art machine learning models. Easy, how easy it is. Now let's go to Gradio sentiment analysis to incorporate another model, which is the sentiment analysis model. Let's go from transformers, import pipeline. So we need a pipeline here. Remember, this is a high-level pipeline that allows us to load in a model. So let's go ahead and sentiment underscore analysis equals pipeline, and then pass in sentiment underscore dash analysis. You can see here analysis. Okay. Run that. Here we have the pipeline and then passed into here sentiment analysis. And remember, this is defaulted to distill BERT, the default model to classify the sentiment or to classify text. Now our model here is loading. No model is supplied because we want to use the default model distill BERT. And you can see here it's called also a distill BERT base on case fine-tuned SST to English. Now my model is loaded. Let's go ahead and see here model, or it's called a pipe. Here you have sentiment analysis, sentiment underscore analysis, and this is my model. You can see the architecture of the model or the pipeline. Okay, text classification pipeline. Now let's move on to the next step, which is using this model to classify the sentiment by going sentiment underscore analysis, then pass in I am sad. Run that. Sentiment underscore analysis. Run that. I am sad. It says negative. If you choose here I am happy, it says positive. My day was great. You can see my day was great. Positive. Now let's move on to the next thing, which is incorporating this sentiment analysis model into the Gradio layout by going def and then name my function predict underscore sentiment. So you have to predict the sentiment and then pass into here a text. Then it returns a result. So result equals sentiment underscore analysis, and then pass into here text, some nice text, then return result at index 0, then grab the label and then return also the result at index 0 and then score. So here we are returning both things, the label, negative, positive, or whatever it was, then returning the score, the confidence rate of the model, that the model, how much the model thinks that this or believes that this text belongs to one class. Let's go predict underscore sentiment. So this function predict underscore sentiment, and then pass in hello, I am happy, this course is great. Run that. Here we have a typo, so it's called predict underscore sentiment. No worries. Sentiment. Copy this name, paste it over here. You can see, yeah, I have a typo here. Sentiment. You can see here, we have forgot an N. Now this function returns positive, comma 0.999. So the model is confident that 99% this sentence, hello, I am happy, this course is great, belongs to the positive class. Let's move on to the Gradio interface. and see how easy it is to incorporate it into Gradio by going gradio.interface and then pass in here fn equals predict. So the function called predict underscore sentiment, and then pass into here comma inputs equals Gradio dot text box, and then pass into this function lines equals 2 comma placeholder. You can put the placeholder as type your text here. Type your text here. Then we have outputs equals a list of Gradio.text, and then pass in the label equals sentiment. Then we have here comma Gradio.text, and then pass into here label equals score. So one text for the sentiment and one text box for the score. Let's go iFace.launch and start my app by passing share equals true. And you can see now we have a cool layout or a cool Gradio app that you can type here, hello, I am terrible, and then submit. You can see it will say here negative by 93%. And we can pass in hello, I am amazing. It will say that it is positive. Because sentiment is positive, score 99%. And that's it. That's how to incorporate machine learning models from Hugging Face into the Gradio layout interface, GUI, graphical user interface. Now let's go ahead and then dive into Gradio errors. So this is the last topic I want to discuss, Gradio errors, how to show some errors in Gradio by going def underscore, so define underscore, add underscore even. So imagine a function that you want to add or sum even numbers. So let's pass in a comma b. So for whatever reason, you just want to add even numbers. Otherwise, you want to raise an error. You want to tell the user that I don't want to sum odd numbers. So here, if not validate even. So let's create a function called validate even first. Validate underscore even. This function will check whether my number is even or odd. And based on that information, I want to incorporate it and check. It takes from me num. It receives from me a num. Then it returns return num, then modulus 2 equals 0. Then let's go ahead and call that function validate underscore even. So here, if you want to check that, we can call this function validate underscore even and then pass here, for example, 10. It will say that true. Yes, my number here is even. If you pass here 11, which is odd, it will say false, not even. 12, it will be true. So if not validate even, then pass into this function the a parameter, then raise a Gradio error. And you'll see that this error will be displayed in a nice format. Pass into here first, value is not even. I am angry at you. Then we have here, if not validate underscore even. So if the b value is not even, then please raise an error. So raise a Gradio error also, telling the user that first or second value isn't even. Please update it to be able to sum those numbers. Then we can go ahead. Else, if there's no any error, if everything is fine, return a plus b. So this is the main logical thing or logical process that I want to use. Let's go ahead and iFace create an interface by going gradio.interface. Then let's pass in here f function equals add underscore even, comma, inputs equals a list of Gradio.number, comma, Gradio.number. So we are here passing two number inputs, comma, outputs equals Gradio.number. Then iFace.launch, launch my app, and let's see what happens. So now we have here a Gradio layout. We have two inputs. A is passed in here 4 plus 8. You can see 4 is even. 8 is an even number. Submit it. We don't have any issues. But once we pass the A input as 7, then now Gradio is angry at you, telling you, hey, error, first value is not even. You have to make sure that it is even. Once we make it even, you don't have any error. Then the second value B here, if you pass here 7 or 9, submit, then B is not even, it says error. Second value is not even. Update it and then go ahead. Okay, so this is how you can raise errors using Gradio and in a nice format. Now if you want a lower degree of danger, for example, you don't want to display this type of danger, which is red. If you pass here 11, you can see it's a red error. It indicates that there is something dangerous. If you want to lower that degree, we can easily go ahead and just update this function here of error into warning. And here, warning. And then, since this is a warning, you don't have to raise it. So you don't have to raise this warning, okay? Now we have a normal warning. Let's run that again. Run this again. You can see now. Here we have A. Let's pass, for example, 8 plus 20. They are all even numbers. Submit. You can see here, there's nothing to worry about. Once we make A, for example, 11, submit it. You can see now there's a warning. First value is not even. So this is a warning. Then we have here B. Once we make B, for example, 13, okay? And also A is 11. So none of these numbers are even. We can go submit, and you can see here we have two warnings now. First value is not even. Second value is not even. And at the last, you can also raise. This is a warning. You can see there's some type of danger still, but if you want to raise some info telling the user everything is fine, but keep in mind that this information is whatever you want to tell the user is. Pass here, for example, 5, pass here 6. You can see now there's an info message. First value is not even. And that's it. That's Gradio. I hope this Gradio tutorial is fun. So now you should be able to know, you should know how to use Gradio to host or to create layouts and also incorporate machine learning models into it. You can see we've done a lot of the layouts, how to process images, and also a lot of the stuff about Gradio. Welcome to the Spaces section. In this section, we'll discuss the Spaces tab inside Hugging Face website. Here, when you go to your profile and then move to your profile, it will direct you to the first section, which is called Spaces. And currently, I have 4 spaces. Hugging Face Spaces is a free public platform for hosting and sharing interactive machine learning ML applications and demos directly on your profile. It functions similarly to GitHub, but is specifically designed for the ML ecosystem, allowing users to build a project portfolio, showcase work, and collaborate with others. Key features and functionality of Spaces are as the following: easy deployment, interactive demos, version control, hardware options, and flexibility, and many, many more. Community and collaborations, and many more. So let's dive into how to create a Hugging Face space and deploy your own model. So here you can go to your profile, and then it will show us this drop-down menu. Let's go to new space. Then it will direct you to this page. Create a new space. Spaces are Git repositories that host application code for machine learning demos. You can build spaces with Python, libraries with like Gradio, or using Docker images. So spaces are Git repositories. So they are like the GitHub repositories that host application code for machine learning demos. They are dedicated for machine learning. First, here we have the owner. You can choose your own profile or other profile that you have. Then let's name our space here in this input, new space name. Let's name it as Diffusion Model. So this is my space name. Then here we have an input that says put some short description that describes the purpose and the functionality of this model. Let's go, for example, diffusion model to generate MNIST numbers or MNIST dataset numbers. MNIST dataset numbers. Then we have some license. Feel free to choose whatever license you would like. In this case, I will choose the most common one, which is MIT, the MIT license. Then let's scroll down. Here you can see select the space SDK. Let's choose Gradio. Actually, we will use Gradio to build this interface and then deploy it or host it to Hugging Face spaces. Then let's go to here. You can see we have space hardware. You can choose CPU basic or 0 GPU or custom hardware. In this case, I will stick to the default CPU basic. And here also we have choose a Gradio template, whether you want blank, chatbot, text to image, leaderboard, or Tracheo. I will keep it the same, or the default option as blank. Then here you can see we have public or private. This depends on your own preferences. I will keep it as public to be able to share it with other people. Let's go and click on the button create space. You can see now we have a space here created successfully. Let's go to files. You can see here we have git attributes and we have here readme.md. These are the default files that Hugging Face creates it for you. And you can see if you go and click git attributes, it will show you all these different options. Here you can see we have the .pth, short for PyTorch, .pt, short for PyTorch, also another extension for storing model weights for PyTorch. Also we have .pkl, pickle, and also we have this .onnx, short for Open Neural Network Exchange. And we have so many extensions, and if you go to here diffusion model, it will direct you to the same page. And also we have readme.md, .markdown, where it contains some meta information about your project or about your Hugging Face space, title, diffusion model, emoji. They choose this emoji for you. And then we have also color from red, color to blue, SDK Gradio, the SDK version 6.1.0. And if you want to change this emoji here, you can go to edit. So feel free to change it. And then you can scroll down and then change this emoji to whatever you want. Then you simply just go ahead and commit the changes here. After you change it, you can commit it and go ahead. But now let's go ahead and just use our diffusion model to deploy it on Hugging Face spaces. So the first step is we need a command line terminal. Let's go and search here for terminal. You can see here we have the terminal window opened. The first thing is we have to check our git version. Git, and then let's go zoom in a little bit. -- version. So now let's check what is the version. What is my current version of the git package? You can see here you have git version as 2.52.0 Windows 0.1. So if you don't have git, running this command will result into an error because you don't have git. And if you don't have git, please go here to Google and then search install git. And here you have the main website, the first website that shows. It's called git install. Click on it and it will direct you to this web page that says install. Then you have here many options. There are different OS systems. We have Windows, we have also Mac OS, and we have also Linux. If you are on Windows, click on Windows and then download here. If you are on Mac OS, you can download from here. And if you're on Linux, you can download from here. Okay, I already have git installed, so you can see here the version has been printed successfully. And let's go ahead and clear our tab here. Let's go to mk directory. Then let's go and name some of my folders. So feel free to name it whatever you want. We can go and name it as, for example, my diffusion _model. And now it created that folder for me. Okay, and you can check that by going ls. Here you can see we have so many folders here. One of them is called my diffusion model. So this is my folder, my _diffusion model, the same that I have created over here, my _diffusion model. Now let's go ahead and clear that. The next step is ls /downloads then /diffusion. So whenever or when you want to deploy a model on Hugging Face spaces, you need a custom or a particular structure that you have to construct and build. For example, here I have in this notebook, I trained and built a model, diffusion model, to convert from text into an image or to draw an image out from text. So you provide some text, for example, 3, 4, 5, and then it generates those MNIST numbers. First, we have some imports here, import the necessary libraries. Then also here we have set up the CUDA if torch CUDA is available, otherwise use the CPU. And then we have the batch size, embedded dimension, time steps, epochs. Here I set epochs as 100, and I already trained that model for 100 epochs. You can see here also we have the transformations. We have to tensor to convert the MNIST images into tensor, and also we have lambda that performs a specific function on our images. Here we have stored the MNIST dataset class inside a variable called train data, and the same, we have passed this train data variable into the data loader class. Then we have a train loader variable that contains a data loader object that is compatible to be passed to the PyTorch model, and the PyTorch model will be able to train on it. Here we have also the UNet class. You can see we have the architecture of the model. We have the first encoder, convolution 2D. We have some convolution 2D layers that performs the operation of convolution. Also here we have some decoder that does the transpose operation of convolution. And also here we have the for method that calls these layers step by step, and then it defines the forward computation of the neural net. After that, here we have set the optimizer as Adam to optimize our weights, and here I've built and written a training loop that trains our model. You can see we have the forward pass to pass into the model, and then we have here you can see we have forward pass, loss calculation, optimize a zero grad, doing some backpropagation, and then optimize a step to optimize and improve our weights. And then I let the model train for 100 epochs. You can see here we have epoch 100 out of 100, and the loss became 0.06. So we started the loss from here 0.09 until it decreased until it became 0.06. Then we have here the loss curve. You can see it's going down and down. So the loss curve is getting lower and lower. After that, here we have a sampling function. So this function is really important. It is considered the prediction function. So here it takes from me, you can see a word, a prompt, then n equals 8, steps equals 100, guidance scale equals 3. And then it performs this unconditional labels for CFG, and then it returns out an image. As you can see here, if we type over here, for example, the number 7, then it generates here the number 7. You can see here it looks like a 7 number. If you run again, here we have a 7, an image that looks like 7. Okay, so the model is trying to generate and to synthesize the image of 7. You can see here we have 7, and if we write here 1 in natural language way, it will turn it into an image. You can see we have 1 here, the number 1, and also if we provide here 2, it will create and it will generate the number 2. If we go again, here you can see we have 2 number. So we have a diffusion model. We have trained it for 100 epochs, and we use this architecture that is leveraging the UNet model. You can see here we have the class UNet, and this class here has so many convolution layers and transpose convolution layers that is working on our images and trying to convert and trying to turn our prompt from a natural language into text, into image. So converting text to image. After that, we have another sample here. If you pass here, for example, the number 6, then it will generate here the number 6. You can see here we have a lookalike number 6. So here you can see we have here an image that looks like the number 6. And if you type over here also, for example, 4, then it will generate here some numbers that looks like 4. So you can see here, we have 4, number 4. Okay, and let's move on to the next step. And then I saved my model into some files by going import os.make directories. So create a directory called checkpoints, and then set the parameter exist OK equals true. Then save the model.state dictionary inside this file that has extension .pt, and also save this model, the model weights, save it into a file with the extension .pth. So .pytorch. And then I saved it. You can see here we have here the model saved. If you go to here, you can see I have here 2 files. The first has the name text 2-digit function underscore mnist.pt, so .pytorch, and the second is text 2-digit diffusion mnist.pth, and they are all the same, so differing with different extensions, but they represent the same set of weights. Because remember, PyTorch library supports 2 different types of extensions, PT and PTH, and they are considered the same. Then we have here, you can see model.loadSet dictionary, then pass into here the function torch.load, and then pass here one of these files, the path that is pointing to one of these files. It will load in the weights and create a new instance of the model with the same set of the weights as our trained model earlier. And here we have also the function of the loaded model. If you pass here the number, for example, number 1, then it will generate some images that is representing the number 1. That is representing number 1. And if you pass here, for example, 8, it will generate the number 8. You can see here we have some images that looks like number 8. Let's move on to here. And then we have some function to normalize input. So you pass in some text. Then we have here return the text and also raise some value error. Please enter a number. So if you don't provide the number, it will raise an error. Then we have also here, you can see a function Gradio generate that creates some try and except block. So try word, then normalize the text, except exception. If you have some error, then return none and return the string of the error. And also here we are returning the image and returning a string indicating that generated digit as word. And at the last, we created a Gradio interface that takes from me a Gradio interface. The input in the form of a text box, we enter some text, and then the model tries to generate and convert this text into an image, and then it returns that output in the form of image. And you can see the label as generated mnist digit type equals numpy. And then if we provide here a number, for example, number 2, submit, then it generates here number 2. You can see it tries to generate number 2. And if you provide here 1, submit, it tries to generate number 1. So you can see here we have 1, submit again, 1. And if you provide, for example, number 6, it tries to generate number 6. So you can see some images looks like number 6. Okay? You can see here we have number 6. Now let's move on to the next step, where here we have built also another Gradio interface, but using the manual way of doing that. Now let's move on to the next step. So once you train a model, once you have a model and built it, train it, you have to construct a file that is called model.python. This file will instantiate the backbone architecture of your model. So here you have the same code as the unit class before, but we have put it inside a separate notebook file, inside a separate cell, and then you can see here, after that we have defined a function called create diffusion model. This function takes from me several parameters that sets the values, the default values for some hyperparameters, and these hyperparameters will be defined and used inside the architecture here, the unit. For example, embedding dimension, number of classes, time steps, and whatever hyperparameters you need to set. At the last, or finally, we return a version of the model with no any weights, just a model, the model architecture. And also we need a file. Then feel free to go ahead and file, download, and then download that file in the form of .python. So you have to have a copy, or you need to have a copy with the extension .py.python that is containing a Python script that creates for you a model architecture, a plain model architecture without any weights. Then we plug those weights to this model architecture. And here we have a notebook called app.ipython notebook. This is also a notebook that contains some code for constructing the app for Gradio. So here we are putting all the code together. So you can see we are from model. So from this model, from this sub package called model, please go ahead and import the function create diffusion model. And that's it. This is our function, create diffusion model. So we are keeping our code here neat, beautiful, and easy to organize. So from model, import this function. Also from time it, import default timer as timer, because we need to time our model time, the time it takes to make a prediction or to generate an image. And also from typing, import tuple. And then we have here CUDA device to set the device as CUDA if CUDA is available. Otherwise, it's set it as CPU. And we have the same logical code as you can see, but at the last we are creating the Gradio interface. You can see here we have Gradio.interface, then pass function equals predict, and inputs as a text box, label, enter some digit, and then we have outputs in the form of an image. Then we have this Gradio interface. So here we have a file for training and building the model, and also we have a notebook for storing in a code that instantiates the model architecture. And here we have a file or app.python that contains all the code and combines it into one file to create and instantiate an app for Hugging Face spaces to work properly and to work in a proper way. Here you have to go file and then download this file in the form of .python. Then you have to have a folder called, for example, diffusion or whatever name you would like. This diffusion folder will contain the app.python that we saw earlier. Also, it will contain model.py. You can see we have the file app.python. Also, we have model.python that contains a code to create an object of the model, to create an instance of the model. And also we have a file, a special file, called requirements.txt that contains the requirements and the necessary libraries that you need to require when your Gradio app runs. So when your Hugging Face space runs, it will require some libraries, some packages, some modules to be installed. And here you are telling Hugging Face, hey, Hugging Face, I will upload to you this model. Please make sure you have these libraries installed already. Torch with this version, Torch Vision with this version, 0.24, and Gradio with this version, 5.50.0. And also here we have two files. Actually, you don't need two files, but here we are providing Hugging Face with two files. The first ends with the extension .pth and the second ends with the extension .pt. They are all the same. Feel free to choose whatever you're preferring. If you prefer pth, use that. If you prefer pt, use that. You don't need to have two files. But here we have the weights. We plug these weights to the architecture. Then we trigger that code inside the app. And we have some requirements to tell Gradio and Hugging Face that we require these libraries to be installed in order for our app to work in a proper way. Let's continue with our prompts to deploy our app or our model to Hugging Face spaces. First, you can see we are inside the directory my_diffusion_model that we have done earlier. Let's go ahead and ls, so list everything inside the /downloads/diffusion, so the diffusion directory, and it will show us what is the content inside the diffusion directory. You can see we have app model requirements.txt text._2digit_diffusion model _mlist.pytorch and the other extension .pth, the same files that we have inside our diffusion directory inside downloads. So remember, I downloaded these files, so they are now exist in the downloads directory, and it should be the same. Now let's move on to the next step, where we have to go to copy these files. So remember, currently, if you do ls, it will show here nothing. Let's go ahead and copy. So we have to git clone. Then we have to pass in the path of the repo of the Hugging Face. We can go here, app, and then we can copy this URL, go into my command line. You can see now, once I do ls, here we have nothing. But once we get clone and then pass in my path of the repo and then clone the repo, you can see now it's cloning into diffusion-model, and you can see here we have also enumerating objects. Now once we go ls, now we have this folder which is called diffusion-model, and if you go change directory diffusion-model, it will direct us to that directory, and then we could have ls, and it will show us that now we have cloned our repo. And you can see here, currently my repo just contains two files, readme.md.get attributes, and they are showed over here. You can see now we have these two files, readme and get attributes. So we have cloned our repo successfully. Let's go ahead and clear my page and move on to the next step. Now the next step is, remember that ls /downloads, so you need now double, then we go downloads / diffusion. I have here the contents app model. I need to copy these contents and paste them over the diffusion-model directory by going cp, short for copy, -r recursively, and then we have here /downloads, and then we have here /diffusion, and then move everything inside the diffusion by putting star, then space dot. So we move everything here into our current working directory that is representing diffusion-model directory or folder. Let's go ahead, and you can see now it's copied it successfully. And if you go and show ls, now hooray, we have app.python, model.python, readme.markdown, requirements.txt, and my weights files. So now we have got all the necessary parts, the necessary files that we need to run our Gradio app on Hugging Face. Now all we have to do is just go ahead and try to commit or push these files onto Hugging Face. So the first thing, let's go get space remote-v. So what is my remote origin? What is my origin? You can see here I have origin https://huggingface.co/spaces/ my username /diffusion-model, and we have two permissions available. We have fetch, so the permission fetch, and also push. You can also push to the Hugging Face spaces. And here you can also go ahead and get lfs and then install. So we need the get lfs. Why? Because currently my model file is larger than 1 megabyte. So if you have large files, at least they are above 1 megabyte or above 10 megabytes, you need to install the lfs package by going to Google and then get lfs install. If you don't have it already, you can install the get lfs. You can see get large file storage and open source get extension for versioning large files, and you can download that from here to be able to upload large files onto Hugging Face. And you can see here you can go easily get lfs large file storage install. Then we can also get track, get lfs track, and then have this file. So let's move on to our command line. Get lfs install. You can see now I have it already installed. Updated git hooks, get lfs initialized, and you can track files easily by doing this: get space lfs and then track every file. For example, my model file, and we can go here to my folder and then copy the name of the model file. So remember, we don't need the model.python, but rather the weights file, because the weights file could get large and large. Then we can go here and paste it over here. Now we can go, you can see now get lfs track. You can see here the path .pth is tracking text to digit _diffusion _mnist.pth. So now our model file weights is tracked in a proper way. We can move ahead and also continue with the prompt. So get space lfs track every single file that ends in the extension .pth. We can go ahead and you can see .pth is already supported. So now we have tracked our files. We can go ahead and do the next step: get add.get attributes, and feel free to read here into the documentation. We can see here we have also get add.get attributes. You can run that command and it will execute over here. You can see here we can run and it added the get attributes, and also let's get add star, so add everything. And then if you check the status by going get status or status, you can see now all of our files are green. That means we have tracked every single file we have inside our folder diffusion-model. So now all we need to do is just go ahead and commit that by going get commit, and then here dash M, so pose a message or send a message that says initial commit. So feel free to read here, to put here or write here whatever message you want to put or write, but in the first commit, let's keep it simple and write here initial commit. You can see now it will commit that to the Hugging Face, and then let's go ahead and git push. It will push that to the Hugging Face spaces. You can see now it's trying to push my files, and now it's uploading. So keep in mind, sometimes it will ask you for a token ID or a token that you need to provide here, and that is easy. All you have to do is just write the command git remote and then set URL. So you can go git and then write here remote set dash URL, then pass into here origin HTTPS, and then put here your username. So your user dash name, you can put here whatever username you have. Then we have colon token. So here you can replace the token, your token ID at huggingface.co/repo path. And keep in mind, this repo path should contain your spaces like that, spaces slash your username slash your repo name like that. Okay, then you can run that and it will ask you to provide the token and it will authenticate. And also then you can run the next command, which says get pull origin, and it will push your files into Hugging Face spaces. With that being said, now we are done with the command line. Let's go to here and check our, you can see now our Hugging Face space is now starting. You can see now it's starting and trying to start and launch our app on Hugging Face spaces. So it might take some minutes, for example 2 minutes to 30 minutes to 3 minutes, and you have to wait until it finishes building and starting. Then you can be able, or then you can review your app and view it and also actually start using it. Now you can see my Hugging Face space is now running successfully. We don't have any errors, we don't have any issues, everything has run smoothly. And if you go to your username, here you can see we have now many spaces, and our space that we have done in this section or in this course is this space, diffusion model to generate MNIST dataset numbers. And if you click on it, you can see here it is committed 4 minutes ago, or it has run for 4 minutes now ago, and here we have running. You can see now my repo or my Hugging Face space is now running smoothly, and this is my dashboard, or this is my Gradio interface. Here we have some input text box where you can write here a human readable number name, for example 3 or for example 1. Then you can go ahead and submit it, and it will generate here some numbers. You can see submit again. If you pass here 3, submit. It tries to write here the it tries to draw the number 3. You can see here it's trying to draw number 3, and if you pass here number 4, for example, submit, you can see now it is trying to draw number 4. And if you pass here 2, for example, it tries to draw or to write number 2. So this is my diffusion model. You can see here it wrote or it draw here number 2, and feel free to upscale this model to train it further, or to upscale the architecture, or even use transfer learning techniques to better make this model work properly. Okay, and here you can see we have the generation time in seconds. So you can see here every time we generate, here we have a differing amount of time that the model has taken to produce or to draw this image. Here we have the generation time as 0.34. And if you pass here, for example, number 6, it also will generate and submit number 6. You can see it draw number 6, an image that looks like number 6. Okay, now let's move on to, you can see here my Gradio interface now is working properly, and that's it. That's how you can upload. And also here we have the share via link. You have the ability to share this app or to share this Gradio interface via a link. You can go here, open this link, and it will direct you to the same Gradio web interface hosted on Hugging Face spaces. And you can see it belongs to my username, my account, and it's named diffusion model, and currently I have here 0 likes. Hopefully you give me a like here, and then we have this text box and it generates some output image here. And then also I have some other spaces here that I would like you to see. If you go to Hugging Face and then my account, you can see here I have so many spaces. I have the generation space, GANs model, Food Vision Big, and also I have Food Vision Mini. Let's go to Food Vision Big. Now you can see my app here, or my Gradio interface, is working smoothly. You can see it's running, and here we have this area where you can drop in here an image, and it will classify this image for you into 101 different classes of food categories. If you submit it, here we have pizza. And also if we grab another image, for example, you can see here I have examples. If you choose it, it will use that example to demonstrate how the workflow works. And if you go to Google and search over here tiramisu, for example, images, it will show you some tiramisu images. Let's drag some of these images and drop it over there. We can go like that, drag it, drop over here, drop the image here. You can see now we have a tiramisu image. We can go and submit it. Then it classified that as tiramisu. That's it. I hope you find this tutorial helpful, and thanks for watching.